everyone. In this next segment, we're going to go into what's called ensembles of ensembles, model stacking. There are two general types of ensembles. One is ensemble with different types of classifiers. Basically, you have different types of classifier, it could be logistic regression, decision tree, random forest, and then you combine them depending on the type of problem that you're trying to solve. If it's classification, it could be by major voting. If it's regression, it could be by average. The other type of ensembles is with a single type of classifier, whereby bootstrap samples are taken out of the population of data that we have. We train them, and then the results are combined to create an ensemble. Okay, so this is quite suitable for highly flexible model that's prone to overfitting. Now, the different types of methods of combining, it could be either voting or average, or it could be by another so-called meta classifier, which is on top of these different classifier that we have. So it could be binary outcome 0 or 1, and the meta classifier is applied on top of the individual classifier. The third type is actually application of meta classifiers based on probabilities. So rather than binary, probabilities are obtained from individual classifiers, then an overlay, which is another classifier, is applied on top of it. So we're going to look at some of these. So let's start with downloading our library, and let's wait for this to run. So let me just check my runtime. Okay, so we are using the TPU. It just need to start up, and we need to upload our file. Let me just select that. This is directly from my local. So every time you run your Google Notebook or Jupyter Notebook, you do need to actually run this every single time, because once the instance is shut down or closed, the data is killed, okay, or it's being discharged. So these are the data preparation. You've seen this before, so we don't need to go through that. Okay, so now model number 1, decision tree classifier. So we instantiate, fit it, and we look at this in terms of output. Notice that it is very flexible, so it's 100% when it comes to the training data. And if you look at the output, in terms of its outcome, is 79%, and with the ROC at 55.9%. And let's compare this to random forest. If we look at this, again, random forest is very flexible. 100%, and if you look at the so-called test score, it's an improvement at 85%, and the ROC, funny enough, has actually gone down. It's not very good at picking this class here. Okay, so it's very poor at picking up all the false class, and partly because we don't have a lot of data for it. So let's take it one step further. If we make use of the so-called probability, okay, record. This is one of the way. We are looking at the probability as per this random forest. Remember, this is random forest. Random forest is RF. This is actually tree, CLF. So we're looking at the probability as provided by the decision tree. Okay, so for the decision tree is 0 or 1 in terms of probability, and if we look at the random forest, it actually generates slightly different values. So if we look at the way we concatenate this, we basically combine them and we just have them side by side so that you can actually view this. Okay, so you have the attributes. This is the attrition. That's our target variable. This is, remember, we converted to 0 or 1. And the random forest has gives you probability. Decision tree does not. So the next step then is to prepare this a little bit so that we can actually make use of these and apply a meta classifier on top of it. So we can use a very simple one, logistic regression, and then we fit it on these two so-called features. So we are using the probability prediction by the decision tree as well as the random forest as our features now. We have our target, which is still the same, which is whether the star for the employee, stay or abandonship, if you can call it that. And if we run these, combine and perform our prediction, and we look at the so-called cross tabulation. This is our, okay, we have an error here. Expected X is, did we miss a cell? Yes, we did miss us. We misrunning a cell. Okay, run the cross tabulation. This is essentially our confusion matrix. Okay, so it's not too bad. There are quite a lot of with errors on both sides. So if you look at the so-called combined output, in terms of the output, is that the precision as well as recall, again for the false class or negative class, is quite low, and this is really what's dragging our performance down overall. Although the accuracy is okay, 79%, but the confusion matrix tells us that some more work needs to be done on the precision as well as recall for the negative class. So that's really the first lesson on ensembles. We're going to come back and look at another approach. Welcome back. Let's take the ensembles of ensembles one step further. We download our file, reread that into our memory. Okay, so let's have a look at the attrition versus the overall. The number of no is 83%. The number of yes, meaning attrition, is much smaller at 16%. So we're going to import three different types of classifier: random forest, bagging, as well as ZBoost. And we know from this is that the proportion, let me just change this a little bit, 83.9 and 161. Okay, so that's our class weight. So okay. Alright, so having done that, so this is in terms of the Panda series list Y value count versus overall counts. Okay, so this is in terms of on our training data. This is our overall on our training data. The number of no is gone up to 84.9, and number of yes is gone down to 15%. So for a start, we create random forest, instantiate our AdaBoost, and fit our AdaBoost. All right, and we have a look at the score or the performance of AdaBoost. It's 80%, but the ROC is much lower, and that's in part because of the recall is so poor here. And now let's look at bagging classifier. That's actually using the AdaBoost as the base estimator, and instantiate that and run our performance evaluation. So let me just wait for that fitting to be done. Okay, fitting is done now. Now we're looking at the training as well as the actual test scores. Okay, overall looks okay, but the recall, as you can see, is not great. The number of false being wrongly classified is still very high, but the ROC is actually better. So let's have a look at our test result. The test result accuracy has improved, but the recall is still absolutely atrocious. We've done our best based on the methods that we have, ensembles of ensembles. We do need to actually take note of the unbalanced class problem and see how we can improve upon that. But that's really the purpose of this lesson, however, is to illustrate to you the idea of ensembles of ensembles. So let me just recap a little bit. We have two different methods. One is ensemble with different types of classifier, which is what we've shown in the last lesson. We did decision tree and random forest from memory, and then we apply logistic regression over these two. So that's really your different types of classifier, and then you'll have an ensemble of it. If it's single, what we have done is basically we run multiple, and then we actually apply a bagging on top of it. So that's really based on a single type of classifier that we did for this. This is a single classifier. We did random forest, AdaBoost, and we apply bagging classifier on top of the AdaBoost. Of course, you can actually replace it with random forest just to see how well it works. If I recall correctly, the AdaBoost is actually using random forest as the base estimator. So we actually have 3 layers here. We have the random forest. We're going to use random forest as our AdaBoost. Use the random forest as the base classifier for AdaBoost, and then we have another bagging classifier on top of the AdaBoost, and that's basically the still one single classifier, which is random forest, but one built on top of the other, and that's really an example. Let me come back here of this single type of classifier. I hope that has been insightful and useful for you. Thank you for watching. That's a lot of contents that are packed in under this ensemble's methods, and I hope you watch it again and again until you actually come to an understanding of it. But more importantly, I'd like you to really get your hands on it, to actually practice and to see, I mean, really through practice, then you understand and develop a much better understanding of it. And thank you again for watching. Welcome back, everyone. In this episode, we're going to look at k-nearest neighbor. The beauty of k-nearest neighbor is that it still belongs to the what's called the supervised classification or supervised learning family, much as what we've talked about so far, which is the classification, the regression. These are all under the supervised family. For k-nearest neighbor, it's works for both classification as well as regression. It's what's called a lazy learner. It's instance-based, and it's the basic idea of this is that it's lazy because it does not try to learn a function from the training data like all of the methods that we talked about. For all of the methods, much as if you think about linear regression, you have y is equal to mx plus c. That's a function that the algorithm tries to learn. The same with logistic regression, sigmoid function, decision tree, random forest. These are all trying to create what's called a function. K-nearest neighbor is totally different. What it does is that it memorizes the pattern from the dataset and it uses that to classify. And it runs on instance, meaning it only works for that instance that you, train and predict. Once you actually shut it down, it disappears. Okay, so it's not, it doesn't actually stay. So hence it actually can be quite time consuming to run this because you have to train it every single time you run it. The other part about this algorithm is that it's called non-parametric because there's no function. It doesn't try to learn a function. It's distribution free because there are no assumptions about the data need to be made to follow any, or neither does it require the data to follow any specific distribution. Right, so that's the beauty of k-nearest neighbors. What is it used for? It's been used for predicting cancer, whether it's malignant or benign, for pattern recognition, a recommender system, computer vision, and on it goes. The one disadvantage of k-nearest neighbor, or KNN for short, is that it is not efficient on big data. As I mentioned before, it doesn't learn a function, so every time to perform any prediction, it needs to search what's around the neighborhood to classify it. And it's really susceptible to overfitting as well as the curse of dimensionality. It just the computation just takes forever as a result, especially when you have large data set. So let me actually turn on the GPU for this and continue on to highlight that these are more references for you to refer to, and a couple of steps in terms of how do you actually build the model as for prediction, or the way that KNN actually learn and create so-called a way to perform prediction. Choose the number k, select a distance matrix, find the k-nearest neighbors of the sample, and assign the class label by majority vote. Okay, having read that, you probably think, I'm none the wiser in understanding how to use k-nearest neighbor. So let's do this. What KNN algorithm assume is that What much is what we say in English, birds of a feather flock together. That's one way to call it. Or your neighborhood defines your preferences, or your friends define you. That's usually the intuition here. So because it's based on the assumption that most of the time similar so-called characteristics of the data point are close to each other. And so it uses this similarity, and the similarity is based on distance, by the way. Sometimes we call it proximity. And we use that and basically to classify the so-called observation. So that's pretty much the basic idea. So the way that we so-called model or build our model using KNN is that you, of course, ingest your data, then you select how many K or what the K. So in our case here, we select 50K. K equal to 50, I should say, number of neighbors. And basically you calculate the so-called distance between the example and the surrounding so-called entries. So basically from that, it uses that to predict or classify what is likely, the most likely class of your observation. So to keep it simply, to make it really, really simple, if I distill it down to just one simple sentence, if in that 50 points, 45 of them is red, 5 of them is blue, then a point that you observe in those 50 is more likely to be red. Okay, so the default class for that is red. So 45 red, 5 blue. That's basically how the KNN works. It's really, really that simple. Let's walk through the code and I'll illustrate how it works. So we import the libraries, load our Irish dataset, and right now we're just looking at petal length and width, and basically this is transforming the classes into integer. Right, having done all that, so we import our k nearest neighbors classifier, and we say we need to choose, well, you need to find 50 neighbors. Okay, look around you, 50 of them, to make sure that you those are your neighbors, to have certainty that you belong to this clusters or this group. Okay, so that's the neighbors, and then you fit the training and the training data, and this is how it goes. So in terms of having fitted, what we need to do next is to actually perform the prediction. Once we've done the prediction, the next step then is to actually plot it to visualize. Because right now, having done all these, you have no idea without visualizing it. Of course, we can use performance matrix, but sometimes, quite often, it's actually quite useful to use visualization techniques to actually see what's actually going on. And what the algorithm did, KNN in other words, provided these boundary line. This is another boundary line that it actually segregated the black one from the red one, and these are presumably white. It decided this is the most reasonable boundary. Of course, with KNN, how it learns is actually it refer to the class and understand the classes around it, the characteristic around it. There are a few ways to actually perform or select the so-called distance matrix. In this, we use Minkowski. Okay, so let's look at the different types of distance matrix that you can actually utilize. You can use Euclidean, which is the distance to the power of square, okay, and then square root of that. You can use Manhattan, which is absolute. You can use Chabovsky, which is maximum of absolute, and on it goes. Minkowski is what we actually use. For more, please refer to the documentation. Okay, let me quickly walk through these three types of distance matrix. Euclidean, which is the most common one. It's called L2 norm of two vectors. So when you have a bidimensional plane, the Euclidean distance refigures as the straight line connecting 2 points. And you calculate it as the square root of the sum of the square difference between the elements of two vectors. So if you look at this, it actually, hopefully, if you are still familiar with high school math, this is actually Pythagoras' theorem. a squared plus b squared, and then square root of that. So that's Euclidean distance. Manhattan's distance, on the other hand, I'm just going to explain to you from an intuition perspective. This distance is also known as the taxi cab or city block distance. So think of it as Manhattan. If you don't know where is Manhattan, think of a city. It's in the form of square grid. In order for you to go from A to B, you need to actually go around the building. So that's basically what's called the Manhattan distance. Chbosky, on the other hand, takes the maximum of the absolute difference between the elements of the vectors. Okay, so that's really the basic idea, is that it takes the maximum of the absolute difference between the elements of the vector. So it just takes the maximum, okay, of the absolute difference. That's pretty much it. Okay, with that I'm going to stop, and we'll go into further application of this in the next lesson. Alright, welcome back. Set apply the KNN algorithm to what we call project cancer detection. This data set is from the Wisconsin or diagnostic data set. Okay, so you can actually obtain that from UCI, breast cancer Wisconsin diagnostic data set. So you can actually get it from here under the data folder. You can read more under the data set description as well. So let's get started. Let me delete this line of code. So we need to import NumPy and pandas. The name of the columns is already predefined. I basically just transfer them here. We obtain the data via wget, and after we downloaded it, we read it in as a CSV, and then view the data using pandas data frame, first 5 rows of data, and here you go. So this is the actual data itself. So let's perform some data pre-processing, looking for any null data. There's none. Looking at the information itself, they're all integer with the exception of bare nuclei. If we look at bare nuclei, there is 699. There's 11 unique so-called observations. So if we look at the value counts, what you have is you have 1, 10, 5, 2, 3, 8, 4, and then you have a question mark 9, 7, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so you have it classified properly, and then you have one here, which I have no idea what that is. So what we want to do is, probably the first question that pops up in your mind is, well, what do we do with the question mark? One way is to drop it. The other way is to actually impute something to that question mark. But since we have no information about the question mark, it could be 0, it could be 11, it could be 20. I guess, well, probably the best way to do is to actually just drop it. So before we drop it, let's have a look at the line of codes, or there's not line of codes, the data set with question mark in terms of as the entry for nuclei. If you look at this and you look at the data, it's pretty hard to tell from this what does it actually all mean. And since we can't tell what it means, the best way then is to actually just drop it. And it seems to affect all, mostly class 2 and then some class 4. If we look at the actual value counts itself, overall there are plenty of 2s, plenty of 4. Dropping these 16 observations is not going to make a huge difference. So the way to do it is to just replace it with not a number, and then we drop none. Okay, so by doing that, that's gone. Right, if we run this same value count again, you'll notice that the question mark is gone, and then it's now integer 64. The other issues that we have is that it's rather bizarre that the class is either 2 or 4. I prefer to work with 0 and 1, so which is why I did use this really simple formula. Take the value, which is either 2 or 4, divided by 2 and then minus 1, then what I have is 1 or 2. Then 1 is benign, 0 is benign, then 1 is malignant. So we have 444 benign, 239 cases of malignant. Okay, so we've run, let's run this line of code. then we can actually see that. And these are the column names that we have left. We can probably drop the ID column, but here we go. Yeah, we drop the ID because it's fairly meaningless. As for class, why do we drop the class? Well, we drop the class because that's our target. If we don't drop it, we're going to have 100% prediction, because our features is what we're actually trying to use to predict our target. Since we already have features in the target in our features, we're going to get 100%, so we have to drop it. Instead, we put class into Y. So we have X having all the columns, as our features, and class as our target. So we do need to actually transform our data and just data pre-process it and transform it using a standard scalar, and then perform the train test split. And let's have a look at our data. So this is our data after the data having been transformed. Okay, the next part then is do the train test split, keeping 20% for test. We perform another so-called min-max fit transform of the data. And if you look at this, these are the two different ways of processing it. You can choose either one, it doesn't actually matter all that much. Right, so let's import our KNN. And this one we use defined by 5 neighbors, and fit our data, and then run the score and see what is the performance matrix of our KNN. So if you look at the training result, it's 97.25, which is pretty good. If you look at the 0, it's pretty good. Look at the 1, it's pretty good. We do have less data for the 1s, so it's not unusual that the value is lower. If you look at the so-called confusion matrix, it's fairly good. The ROC is pretty good. In fact, they are very, very good. If you look at the accuracy and the standard deviation is very good, then I'm pretty confident that when we run the test, you're going to get good result. So, and yes, and sure, we do a 95% and 95.06, which is a slight drop from the training, but it's not such a massive deviation. Let's take it one step further and perform a grid search. I won't go through all of the details. We can actually select multiple different neighbors just to see how how it works out. Whether n is 1, n is 5, or n is 10 is best. And we look at the best estimator. Is basically telling us, what is it telling us? 7 neighbors the best. Interesting, and the matrix is using Minkowski. Is that one of our parameters search? No, I think we just search n neighbors. You can actually look at the distance calculator as well. Looking at the accuracy, no, 97.25, ROC is 96.83. It's still doing the so-called running through, so 96.53, and that's done. Now let's look at our test score. It's 95, so it's 95.62. That's not actually better, despite the fact that we did the grid search. Yeah, it's exactly the same. So that hasn't improved. It's come to pretty much the best that it can do. So the best parameter is 7, and if we look at the mean test scores, you can actually see that here. If you look at the grid search, so basically the grid search is very, very powerful. It has a lot of useful information here, and you can actually dig in and look at the raw data. There's some 94%, 94.5% here. So, and yeah, so let's compare this to the other method that we have. We have SVM, random forest, as well as XGBoost. Remember, the so-called result for this is, let's use ROC, 95.06. 96.15 for SVM. For random forest, it's not as good. Well, I didn't really actually create one for XGBoost, although I actually wrote it here. I'm going to leave that with you as an exercise. And that's pretty much the end of our discussion. Thank you for watching. Welcome back, everyone. In the previous session, we cover a few very key concepts of k-nearest neighbors concepts, the iris demo, as well as the distance matrix itself. So in this segment, this lesson specifically, we're going to start on an interesting project called Project Cancer Detection, not cancel detection. Obviously, typing is not my strong suit, as you can see. The dataset that we're going to make use of for this purpose is called the Wisconsin dataset. So let's just have a look at that. Already provided a link for you to actually access this as well. So you have the breast cancer Wisconsin diagnostic datasets. This is this provided in 1995, so it's a little bit old, but nevertheless is a very useful data sets for us to actually learn from. The actual description of the data itself is provided here. It's quite long. There's a fair bit of information here. So what I've done here really is actually extract all of these relevant information over, and let me just change this to raw so that you can actually look at it carefully. Okay, so do go ahead and download the data and save it to your desktop. This is the data folder itself. If you have a visit, these are all the data sets. What I download is the data here, which I believe is this one, WDBC. Yeah, this is all the data that I've downloaded. So this is the largest one here, 121 kilobytes. Okay, the data is already downloaded. So for now, what we want to do is actually import that. So let me just import it so that we can actually have a look at the data side by side with our descriptors so that we can actually compare them at the same time. Okay, so the other thing that I've done is that because typically with these data, when it actually comes through, it does not have the so-called column descriptors. I've actually used all of these column descriptors. I've renamed some of these. So you have the sample code number, I call it ID. You have the clump thickness, uniformity of cell size, uniformity of cell shape, marginal adhesion, the single epithelial cell size, bare nuclei, blend chromatin, normal nuclei, nucleoli, mitosis, as well as the class. So basically, it's all of these I've provided as the name of the column and removed the header. So let's have a look at our data. This is the first 5, and what you have now is the actual ID itself, the clump thickness, the uniformity, and all the way to actually the class itself. Now we do need to actually do some data pre-processing, so let's start with that. We do need to actually see if there are actually any so-called null data sets. Now this doesn't always actually pick up everything, so let's look at the actual info itself to see if it actually does inform us of some of these. Other things that you can actually observe is that, hey, you actually have a non-null object here, so it's not integer, and that's where scikit-learn library will actually have a problem with it. So it's object here. The strange thing is that it actually shows you that it's number here. So what's going on? So this is where your ability to play around with the data to understand how it works really actually important. So we do need to do some preliminary investigation. Oops, describe. Suddenly got into English mode. Okay, describe. So we have 699, and what the other thing that we do want to know is what are the actual value distribution value counts. So okay, this is where our culprit is. That's really the reason why it is actually an object rather than integer. Although it says it's integer here, the info here actually picks up some object in here. What are the object? There is the question mark here, and there's 16 of them. Okay, so that's really the key thing here is that, so the question now is, how do we drop okay, so we want to actually just remove that altogether. So the first thing now is that, yes, we are still looking at the bare nuclei. Okay, nuclei, okay, is equal to this question mark. Okay, can it pick up? Yes, it does pick up. So now we just want to actually have a specific selection of these only. And this is the all of the rows and the samples of within the data set itself that actually have this issue here. Now, before we go on and start removing these rows, we just want to actually have a look at the class itself that relate to it. You have 2, 4, and the rest are 2s. Now, the good thing is that we do have a lot of data, but nevertheless, it pays to actually just study this a little bit just to see if it actually will skew the data too much or not. So that's the reason why we do need to actually do some of these investigation. And if you actually remove, if you're in an unfortunate situation whereby you have all of these question mark and all of these question mark happens to associate with one class, and if you remove all of the question mark, it removes the whole class itself, then you have a problem. That's where you need to maybe collect more data and figure out how best to actually remove or work around that issue or impute data. So for now, we are fortunate in that we don't have that issue. Our data sets actually have 458 observations of 2 and 241 observations of 4, so it's not going to be too severely affected by these that we remove here, and there's 16 of them, so we're removing 14, 2 and 2, 4, so it's not too bad. It's not good, but it's not too bad. It's not going to turn into a disaster. So the bare nuclei, still the one that we actually have issue with. So we're gonna change or just replace the question mark with nan, not a number, and true, and then we're gonna use the dropped df dropped na function that comes with pandas. Okay, so that will remove that. So okay, so just note that for class. So remember, we actually have we've done that part of the cleaning now. We want to move on to do a little bit more cleaning in terms of our class. Notice there's a 2 and 4. Remember I mentioned before that with data pre-processing, you need to understand the number, how the machine learning algorithm interpret the numbers. Here you have, although in this case it's not too bad because that's our target variables, it's still not ideal. 2 and 4, we would have preferred 0 and 1. This is where you need to use a little bit of your imagination and figure out how best to work around this. So this is what I come up with, but a couple of things before we move into before I move into showing you how I actually convert that into 0 and 1. For now, we just need to understand our data a little bit. Okay, note that for class, okay, 2 is benign, okay, benign, and 4 is for malignant. Okay, the good thing is that the actual data itself is not too skewed. It's 458, about 2-to-1 ratio. So 458 to 241, yeah, it's about 2-to-1 ratio. It's not too bad, not ideal, but it's not too bad. So we just so this is how I would actually solve the issue of 2, 4 and convert it to 0 and 1. I'm gonna less the whole column by 2. All right, that's the first thing that I will do, and then just basically, sorry, let me I guess probably the best way is to just show you rather than keep talking. I'm gonna take the df class. Okay, I'm just gonna write a formula here. Okay, take the whole thing and then divide it by 2 and then less 1. Okay, that doesn't come out well. Let's see if this comes out well. Again, that doesn't come out too well. So let me just do it this way. Fraction, FRAC. Okay, yep. Open up another fraction. Okay, that's better. So I'm gonna just take the, in fact, I like this to be text. Okay, that's better. So I'm gonna take the whole column, which is the class column, the whole thing divided by 2 and then less 1. So if you take the whole thing divided by 2, so that will convert it to 1 and 2, and if I less 1, that becomes 0 and that becomes 1. So that's what we're going to do right now. So the nuclei, and just do the value count first before we actually do the actual transformation itself. So if you look at this, notice that the what do you call it, the question mark has indeed gone. All right, so the next thing now is that we do need to actually change this to just transform this right now. Okay, so let's do the class. Let's go to class. Okay, divided by 2 minus 1 as I shown in the formula itself. So now if we take df class and look at the value count. Okay, let me move this up so that you can actually see. Okay, now I notice that it's now 0 and 1, and we have removed completely the issue that we have earlier. Okay, so which is 2, 4, now we convert it to 0 and 1, something that we prefer to work with. Okay, now let's store the data into our x and y as we familiar with. So we're gonna copy the whole x, the whole data frame. So let's just show the data frame's columns name first of all. Okay, so the columns come with these names. The class obviously cannot be in the x itself. X is our predictor, so we don't want to include that. We also don't want to include the ID. ID obviously has no information at all. It's just a case ID. So we're gonna remove the ID itself and class itself. So we're gonna make use of pop to remove that. Okay, and store the rest into x, and I'm just gonna remember this because we're gonna need it later. Okay, right, that's done. The next thing now is our y. We just need the value of the class itself, and that is pretty much it. Okay, right. Finally, the one last thing that we do want to do is to scale our data. So sklearn pre-processing, and we're gonna import the standard scalar. Okay, and we're gonna x is equal to standard scalar. I'm too lazy to instantiate it, so I'm gonna just do this in a chain. So transform, you can instantiate it if you want to, but for me, I just want to actually immediately and directly convert it. So we have the standard scalar, that's the first portion here, which is standard scalar. Bracket here is our instantiation dot fit transform, not only fitting it but also transform it concurrently. We're storing x, the values, and directly into actually the x itself, so just replacing it all together. Okay, right, what is the warning here? Data conversion error. Warning, data with input type object was converted to float 64. This is the issue that we have. So let me just df info. But they've already removed the issue, so there are no more issue anymore because we've already removed the question mark. Hence, it actually is able to actually proceed without much problem. All right, finally, we are ready to do our training. Okay. Again, I'm sure you know by now what we're gonna do. We're gonna split our data into training and test split. Okay, and we store this into data frame 1. So pandas data frame, and we'll take x, which is this one. This is already this is the scale data. But we just want to leave the now I'm just want to put some the name back, which is what we store earlier, x, the column name, which is this, the purpose of this. We store the name, and we just want to just do a bit of visualization. Okay, just so that we actually see what has occurred. this is what happened with the scaling. The scaling has changed the data. Remember what we had before was just these numbers here, and obviously the machine learning algorithm is going to have a bit of issue dealing with these. Yes, it's not so bad when it comes to KNN, but nevertheless, we want to do this in case we want to actually compare KNN against other machine learning method. But for now, we're going to make use of that and split out train and test data as we normally do, so that we can actually start training our data, training our model. So why change? Well, that's actually kind of a misnomer, because we, as I mentioned before, KNN is not really a function-based or training-based. Okay, but for now, let's go into this. We still need to nevertheless do this train test. I'm going to use 80% for the training and set our random state to 42. The question that you had earlier when I was explaining that wasn't really well explained, by the way, is why do you actually want to still do this? The answer is actually go back to our cross-validation lesson that we did in section 3 in the regression. Remember that we split our data into train and test. Within the training itself, we also do perform cross-validation, leave one out, or cross-validation tenfold, typically 3 if you want to as well. But the idea here is to actually run multiple training and also test within sample to see how our model will perform within sample, and then later on, before we move into the actual test itself. Although we're not actually trying to get the KNN to learn a function, what we are doing is that we are assessing the performance of KNN in sample and also out of sample. That's really the purpose and the whole idea of actually doing this whole exercise. Okay, now we've already talked quite a lot. We've already covered a lot of ground. I see that we are running a bit of short in time rather than forcing this through. I'm going to pause here. I do want you to actually do a simple exercise. The exercise is a little bit different from what you've been used to. You notice that here what we've done is we use standard scalar. And this is the part that I want you to remember a little bit of what we did in the past, which is what are the other types of pre-processing library we can use or method we can use outside of standard scalar. There are 2 others. I'd like you to think of them and apply them in this situation and see, and also visualize it to see what actually occur or what happened to your data. So pause the video, try that out. This is really an exercise to help you recall a little bit of what we've learned in the past. So pause the video now. When we come back, I'm going to summarize the lesson. Welcome back. I hope you did give that a go and try that out to see what it actually was like. Yes, there is the min-max and there's also a normalization. Okay, I did the min-max just using 2 lines imported and using the actual chain operators of pandas. In essence, the min-max, the fit transform of the original data from the data frame itself, and finally remembering or copying the actual columns itself. We're just visualizing the top 5 samples, rows of data. So notice that compared to the standard scalar, it's actually quite different. Okay, and this is the really interesting part. And but nevertheless, the whole point of this exercise is actually just to give you a view of how things actually works. Okay, hopefully you do remember the lessons that we've learned earlier. So in this lesson, just to summarize, what we've covered is that we started on the project or cancer detection. We have downloaded the data from Wisconsin, and we understood our data, did a little bit of very preliminary or very just a light touch of EDA, just to understand our data a little bit, tidy up our data, and just basically doing a bit of data cleaning, removing some of the data, just making sure that we pre-process it properly and using standard scalar here so that we can move on to fitting our model, which is what we're going to do in the next video. Thank you again for watching. I look forward to seeing you in the next video. Welcome back, everyone. We've now pretty much closed up the supervised learning and starting a new chapter on unsupervised learning. In the unsupervised learning sphere, one of the use cases is called dimensionality reduction. So that's pretty much our focus for this discussion. So there are two so-called common PCA that we're going to talk about here. There are many others, but in this portion we're just going to talk about PCA, which is principal component analysis, and LDA, which is linear discriminant analysis. PCA is extremely popular. It's using what we call the singular value decomposition of the data and project it to a lower dimensional space. In our next lecture, we're going to look at how that is done. It is a statistical procedure that utilizes the technology called orthogonal transformation. And basically what it does is that it converts possible correlated features, also called predictors, into linear uncorrelated features called principal components. The number of principal components usually is less than or equal number of features, and the first principal components explain the largest possible variance. Each subsequent component has the highest variance subject to the restriction that it must be orthogonal to the preceding components. And the collection of the components are called vectors. One thing about PCA is that it is really sensitive to scaling. Okay, so keep that in mind. So when it comes to LDA, it's most commonly used as a dimensionality reduction technique in the pre-processing step for pattern classification and machine learning applications. The goal here is to project a database or data set into a lower dimensional space with good class separability in order to avoid overfitting and also reduce computational costs. So that's the beauty of LDA, is that it projected into a lower dimensional space so that the classes can be separated. Okay, so that's the beauty of this. There are others which I won't touch on: MDS, isometrics mapping, and t-SNE. Now, this is a really basic introduction to linear algebra. If you're familiar with this, this is pretty much the end of the brief introduction on dimensionality reduction algorithm. You can stop here and move on to the next lesson if you like. If you want to learn a little bit about linear algebra, let me just quickly walk you through this. In the high school, probably in A level, you probably look at these many times before. You have two matrix, A and B. This is 2 by 2 and this is 2 by 2. And you're trying to multiply the two, and basically the way to actually multiply A and B is using this step. So this is by parts, and this is the actual so-called result of it. So it's 1 multiplied by 1, and then 2 multiplied by 100 to gives you that. And then the next one is 10 multiplied by that, and then 20 multiplied by 100. So that gives you the lower one. So on and on, you repeat as you go. All right, so that's really the use your hand, work it out, workout example. If you're using Python under Python NumPy, so these are the A and B. This is what A looks like, this is what B looks like. And using NumPy, there is actually a built-in multiplier, which is what we call dot product. For the multiplication of matrix, you get this outcome, which is right here. And then basically that's the purpose of NumPy, with numerical Python. It is built and extremely efficient in the application to matrix multiplication. And this is useful for an understanding when it comes to the likes of machine learning overall. But right now I'm introducing it for the specifically in dimensionality reductions, which we will look at next. Welcome back everyone. Let's look at principal component analysis, and we're looking at the linear version of it. I provided a couple of links there for you in terms of scikit-learn documentation as well as the parameters. I mentioned before that it uses what's called singular value decomposition of the data to project it to a lower dimensional space. Surprisingly, PCA has been around since 1901. We talked about orthogonal transformation technologies. We talked about converting possible correlated features into linear uncorrelated features called principal components. The number of principal components is always going to be less than or equal to the number of features. The first principal component explains the largest possible variance, and all the subsequent starts with always the highest variance, but there is one rule, which is that it must be orthogonal to the preceding components. One thing about the orthogonal rule is that if you're not familiar with orthogonal, think of it as perpendicular. When you have a collection of the components, they are called vectors. And finally, PCA is very sensitive to scaling. Couple other notes is that it's used in exploratory data analysis. It's good for visualizing genetic distance and relatedness between populations as well. Right, the method is that eigenvalue decomposition of a data covariance matrix. Don't worry about those. We don't have to worry about the math. We can actually still perform the PCA without having to actually understand what is eigenvalue or eigenvector. Singular value decomposition of the data matrix after, of course, mean centering or normalizing of the data matrix for each attribute. What you get in terms of the output is the component score, sometimes called factor scores, also called the transform variable values, and the loadings for each of these factors. Other thing is that it is often used for data compression and information preservation. It's good for visualization, noise filtering, as well as feature extraction and engineering. So let's dive into an example. So importing the usual libraries, and we are creating random numbers. And how many are we creating? We are creating 2 by 2 as well as 2 by 50. So this is dot multiplication of 2 by 2 to 2 by 500, sorry, and transposed. So this is the data that we have. So let's just run that. Okay, and let's look at the purpose of doing that is so that we can actually plot this out this way. And this is really a random number, and what we can see here is that this is negatively correlated. Is it 1-to-1? Maybe, but it's definitely negatively correlated. So as x increases, what you have is that y decrease. So they're inversely correlated to each other. So as y decreases, as x decreases, y increases. So let's identify the principal component of this. We import the PCA, and we look at define, let's just say 2 components. And if we print out the components, you can see the components are provided here. And you can also look at the amount of variance being explained. The first factor explain this much, the second factor explain this much. But it's a bit hard to understand that, so we convert it to percentage. 92.8%. The first factor explained 92% of the data, and the second factor explained the remaining 7%. If we plot that out using the line, what you can see here, the white line, is there any way that I can actually make the white line thicker? Let's just make that 4. Okay, if you look at the white line, okay, this is the first line that explains most of the variance, and the second one is orthogonal to a PC1, principal component 1, explain this much. By the way, the length of the white arrow signify the so-called percentage variance explained. Okay, so there are 2 principal components that were selected here. The length denotes the difference or the significance. This transformation from data axis to principal axis is an affine transformation, which basically means it is composed of a translation, rotation, and uniform scaling. So that is in a control environment. So let's look at a slightly different context. Okay, so we have the X, which is the 500 from before, and if you look at the transformation of this, the orange line, that's green. Are you sure that's green? Am I colorblind? Okay, that's interesting. This says green. Looks orange to me. My color blindness must be getting bad. Anyway, the blue dots are the original data, and this is the principal component of component number 1. And this represents the so-called principal component. Okay, so that's pretty much what I wanted to cover, and the main idea of this dimensionality reduction here is that if I stripped away the blue, what I have remain is the green, and this pretty much signify close to 92% of the data that we referred to earlier. Yeah, so 92. We haven't lost much of the so-called contents. Yes, we have lost some, but we kept the essence of it. So in this lesson, basically what we cover what is principal components, and we also apply this. We will also apply this to a so-called scenario, or generated scenario, and finally we look at a transformation in terms of the reduction, dimensionality reduction. So if we strip away the blue and we keep only the green or orange, and that's pretty much the reduction in terms of the so-called information. And this is one way for you to actually compress your picture, for example, if you want to actually reduce the size. Quite often this algorithm is used for compressing your hard disk as well. And thank you for watching. Welcome back. Let's apply this PC8 or dimensionality reduction of extraction of the principal components onto our familiar wine dataset. One thing that we do need to do with the wine dataset is that we do need to actually download it directly from the UCI website. So I already provided the code here, so all you have to do is download it. Once it actually is saved, it will read directly into our data frame because the data is in the form of a CSV. Okay, so just to view, to make sure that the data has come through correctly, we just need to pull out the first 5 rows of data by using .head. As you can see, has come through. What we also need to do is provide the so-called column names or the feature names, which I've extracted from the source as well. So once we add the column names by using df.columns or assigning the call names, which is this one here, to df.columns, and if we actually look at the data, this is what we have. The reason I chose all the rows and only from the first column rather than the 0th column, because as you recall, Python start counting from 0. So 1 technically is actually column number 2. Then you have the first column, which is denote as 0 in Python, and and this is actually technically second column. Onwards are all here. Okay, so coming back to the first column, which is column 0, is actually the class. Alright, so looking at the class itself, we stored it into Y, and you can actually see that here. So the first thing then is to actually perform what's called training and data splitting. We need to transform our data by using standard scalar. And we're looking at decomposing this into 2 principal components. Notice that we do perform PCA fit to our transformed data and look at the explained ratio. The first one explained 35%, the second one explained 18%. So if we round that out by using rounding to 3 decimal places, you can see 35.9 and 18.7. Right, the next thing then is to actually plot this. We want to see the loading of the 2 components for each of the so-called features. And what I've done here is that I have transposed it, I should say, so that it's actually in this table format rather than lengthwise. I had it in row-wise. And the way that we structure this is that we have the components and the column names. So running this gives me this value here. So for 0, this is factor 1, this is PCA, this is PCA1, this is PC2, sorry, principal component 1 and principal component 2. And looking at these, you can see that the diluted wines, no, it's actually the flavonoids, has the strongest effect on the first component, and the non-flavonoid phenols has the strongest negative. Yep, strongest negative, followed by malic acid. Right, no perceived ideal number PCO we want. Okay, now preconceived ideas. Okay, so that's basically for that. For this, we actually specify 2. Let's just say we don't actually have any idea how many components. We're just going to run it, and the actual PCA itself perform the computation for, well, basically as long as it can, or usually 10. If you look at this, this actually is slightly longer than 10, but what we're more interested in is the actual explain variance ratio. 36, 18.7, 11.6. You notice that they drop quite markedly as you go down, and you can actually make a choice and say, do I want 80% of my variance explained, or do I want to go all the way up to 90% or 99%? It's really your choice, actually. 80% is probably sufficient for some. For some, they might want to have 90% of the variance explained. So that's that I'll leave it up to you based on your business case. So if I actually plot this out, visualize it using a simple line chart, you can see that if I want 80% of the variance explained, I need 4 components. If I have 6 components, it go up to 90%, and that's basically the idea here of plotting this out so that you can actually visualize this. So that's pretty much the end of this video on application of PCA or dimensionality reduction onto our wine dataset. And you could see the process flow, load the data, ingest it into our RAM, perform transformation in terms of standard scaling it, then perform PCA. If you know how many components, specify the number of components. If you don't know, run the full spectrum, and then plot the chart, like a line chart like this, so that you can actually have a visual where you actually want to draw the line yourself. Okay, the final part is in terms of looking at the actual loading itself. So this is what I've done. If you look at this, this is the actual loading itself. This time around, I ranked them from the most negative to the most positive for each of the components. With that, I'm going to stop. Thank you once again for watching. Welcome back, everyone. In this segment, we're going to go into kernel PCA. It's a deviation from linear PCA. Linear, as you know, is capable of dealing any linear relationship, but not so good when it's actually dealing with non-linear. And that's really the reason why we are make use of the kernel tricks and utilizing this in combination with the PCA or principal component analysis. And essentially, a couple of things that I want to highlight is that this notebook that I'm about to share and discuss is inspired by the notebook by Matthew Blondel. Hopefully I say his name correctly, and Andreas Müller. Okay, so it's actually based on the Scikit-learn website. So I just want to highlight this, give them the credit for actually for the original source code for this. Alright, what I've done here is that I've implemented this in Notebook. We do need to first of all import the libraries that we need, and we need to make use of a false data set or a simulated data set, not so much false, similar data set for the purpose of this exercise. I say simulated because this is really much like in a lab environment. We're creating data and just want to observe how does our linear PCA as well as our kernel PCA deal with and the effects of them on the circles that we create, the simulated circles. The reason that we don't want to start working with the real-world data is because for the real-world data, there are a lot of underlying interplay that to begin with, we don't know what are the relationships between them. And so we can't really observe the effects of the two separate algorithms on their own. However, if we're actually creating simulated data sets and we apply the algorithm to them, we can actually see the effects at play. And then in a pure environment, then we can actually tell what their individual contribution towards understanding the underlying data set. So we are, from the scikit-learn decomposition, we're importing PCA as well as the kernel PCA. And we are creating circles and store this in X as well as Y. And we doing two parts here. First of all, we're instantiating our kernel PCA using the RBF kernel trick. And then we fit and transform the original X and store it in X_KPCA. And then we actually inverse transform the KPCA and store an X back. They will be utilized later. But ultimately, most of what we're going to use is actually the fitted and also transformed X. For the PCA, the linear PCA, we do likewise, and we name it X_PCA. So let me line this line of code. Right, to see the effects of these two, we do need to add some sort of standard or benchmark to compare it against. So looking at this is just a really normal simple plot. When y is equal to 0, we just call it red. When y is equal to 1, we just call it blue. And then we plot them accordingly. And this is what it looks like before it is transformed. That's our control. So you have the red on the outside and the blue circles on the inside. So let's have a look at what happened when you actually applied linear PCA. Okay, having run that line of code, what you can see here is that there aren't actually any discernible difference between the two. Principally, we are actually using the XPCA here, which is not the original X, but the transformed X by the linear PCA. And unfortunately, because linear PCA can only deal with linear relationship, it's not able to actually of much use really in our situation. There are slight variation, but by and large the actual underlying data looks exactly the same. The first and second component looks very much the same as the control that we have here. Taking it one step further, and let's have a look at what happens if we apply the kernel PCA on this. We are using the X_kernel PCA to transform X using the kernel PCA algorithm. You can see that there is actually a clear distinction here, and that just visually you can see that there's a clear separation between the red as well as the blue. And that's really the key difference between the kernel PCA versus your linear PCA. It's able to actually perform this separation. I probably shouldn't use the edge color of black because it does actually looks like this guys and makes it rather hard to actually tell. And if I remove that, you can see it's all red and it's all blue. Right, that's pretty much where I want to cover, and in the next lesson we're going to start looking application of this into a real world example. And thank you for watching. Welcome. We are going to apply the kernel PCA into a real world dataset. Specifically, the dataset that we're going to work with is Iris, something that you are very familiar with. And if you have gone through all of the lessons diligently, we're going to exclude the Setosa class and just looking at Versicolor as well as Virginica. And again, what we're doing here is that we do convert the two classes into integer so that the algorithm can utilize it properly. So again, what we're doing here is that we do need to first of all instantiate and then fit and transform our X. Okay, so the next part then is to select our machine learning model. We are using logistic regression, and we're instantiating and also fitting the actual data itself. This is just on the untransform or non-transform x. This is just basically the original x and y. And let's visualize that and see how the algorithm, which is logistic regression, deal with the underlying separation of the two classes. You can see the black represent one class and the yellow represent another class. And so that you can see that it does a reasonably good job, but there are some parts that there are crosses over that's not labeled properly. So in essence, if you count 1, 2, maybe 3, 2 to 3 mislabeled. So let's see what happens if we actually perform the fitting on the transform x using the kernel PCA. So let's just plot this out once again. Notice that this time round we are actually using the kernel transform x, and let's have a look at what happens if we apply the logistic regression to it. You notice that the x having been transformed looks vastly different from the original x. This is the kernel transformed x PCA, meaning we have applied the kernel PCA onto the original x, and you notice that it's been transformed to this format. And you can see the separation now is very clear, although this mislabeling is still quite high. You have 1, 2, 3 mislabeled, which is not in terms of number mislabeled. Wait a second, I didn't count the black. So 1, 2, 3, 4 mislabeled here. So I suppose you can say that only 1, 2, 3 it has improved it somewhat, and it's probably difficult to separate out the blacks from the yellow amongst the yellow, and it's difficult to probably separate out the yellow from amongst the blacks here. But nevertheless, from this simple example, hopefully you can see the power of using kernel PCA to actually separate what it can be deemed sometimes non-separable data points. And this is something that you can use as a form of data pre-processing in comparison to the dimensionality reduction that we looked at previously. With that, I'm going to stop. Thank you for watching this portion of the lesson. Welcome back, everyone. In this segment, we're going to look at linear discriminant analysis and try to compare it against the PCA. LDA is short for linear discriminant analysis, is a supervised dimensionality reduction algorithm. What it does is that it projects the input data into a linear subspace consisting of the directions which maximize the separation between classes. This is most useful in what's called the multi-class setting. So we're going to apply this into our Iris dataset. We are using only 2 rather than 3. Nevertheless, let's have a look at how or what the outcome and effect is. Just looking at 2 classes for now. The linear discriminant analysis, or LDA, can be imported from scikit-learn discriminant _ analysis sublibrary under the sklearn. The usual, we instantiate and then fit our data, and let's visualize this in this simplest form, just to see how well the LDA actually perform here. So looking at this, because the classifier is making use of the LDA, okay, as you can see here, it is actually LDA, and we perform the predict using the x and y that's provided. You can see how this line here is as predicted by the LDA. Of course, this is a rather challenging situation. It doesn't perform as well as the kernel PCA, but it's still pretty good, and is quite capable of separating the 2 classes as much as possible. Right, so what I want to do is take it one step further. You can see what it can do earlier from the earlier example. You can also see its limitation as well. And quite often, people tend to ask me, how do you, or when, under what situation do you choose the PCA, under what situation do you choose the LDA? It's not a really straightforward pick this or pick that. Quite often it's better to actually just try both, observe the outcome, and then pick the one that works best in your situation. There isn't a, I guess, silver bullet, you can call it, to solve the problem at hand, or knowing which tools will actually give you the best outcome. So look at this. There are some distinguishable difference in terms of the how the two are constructed. What PCA does is that it combines attributes, okay, and basically it select a combination of the attributes in the form to create what we call principal components, and from that it uses that to see how much of the variance it explains. So basically, if you look at this, it identifies the combination of attributes that account for the most variance in the data. What about LDA is slightly different. I try to identify specific attribute or attributes that account for most variance between the classes. So therein lies the difference. One combine attributes, the other one does not combine. It just identify the attributes. Okay, it might be S, might be multiple. So looking at the whole iris dataset now and just visualizing it, let me show you how difficult and how challenging it is to tell the difference between PCA versus LDA. If you look at this carefully, of course Setosa stand on its own. You will leave that aside. We just want to compare the separation between the two versicolor as well as Virginica. If you look at the PCA, they tend to be fairly compressed. But if you look at the LDA, it seems to, well, I can almost make it out that if I use kernel support vector machine, it may be able to separate out the teal from the orange, whereby in the situation for the PCA, it's probably, I would say, unlikely that it's able to do that. And because the sparseness between the orange and teal dots tends to be much more sparse, it's easier to draw a line with lesser number of errors than the PCA drawing a straight line here. Okay, so that's really a very quick observations and summary of the difference between the two, and hence really this come down to this key point here, I guess, is being teased out from this simple example. LDA is a supervised method, and it tends to work pretty well for multiple classes situations. Okay, it seems to work better than PCA. With that, I'm going to leave that thought with you and for you to actually consider, and probably more than likely, and I think from my earlier discussions, I'll encourage you to use both and then observe from some of the visualization to see which one that you ended up using, or might be both. Thank you once again for watching. Welcome back, everyone. In this lesson, we're going to look at applying the data PCA as well as LDA into a new project called Project Abalone. Project Abalone is a database that's provided by UCI, and if you look through it, there are quite a fair few instances, 4177 of them, and there are 8 attributes. It is also multivariate. It's a classification based problem. Okay, so this is quite an interesting database. So it's a pay to actually have a look at the details and try to understand it and see how we can actually apply PCA and LDA on this. The purpose of this whole exercise is to predict the age of abalone from the physical measurements. Quite often the age of abalone is determined by cutting the shell through the cone, staining it, and counting the number of rings through a microscope, a real boring and time-consuming task. The measurements, which are easier to obtain, are used to predict the age. Yeah, so that's one way to actually do this. So looking at this, we import our libraries as usual, and then we need to download the data. We're going to download this directly, and then we read it into our memory by just using the pandas read CSV. There are no headers here, so this just labeled this way. And we need to slice off the first column, and hence we use 1 onwards, and so that's the data clean up this way. So we're going to transform our data and perform what's called the pre-processing, and then standardize it, and then we import our PCA, just a linear one, and then transform it. Now at this point, let's go back to our so-called intention. But there are 8 features here. Probably from time to time, if your PC or you don't want to utilize so much compute power and you just want to actually use a combination of the feature to reduce down to specific so-called principal components, is there some way to reduce the best perform what's called dimensionality reduction down to 1, 2, or maybe 4 or lesser than 8 ultimately is your goal. So we're trying to find how many principal components that we can actually combine or utilize to achieve explanation of 80% of the underlying variability of the data. So that's why we are applying PCA here. And if you look at the cumulative sum of the PCA, interestingly, just purely the first principal component itself already achieved 84%. The second component, once you add it in, it can explain 92%, 92.6% of the data. So if you look at a plotting out of this, you can do see that we start with about 84, climbs quickly to 92, and fairly quickly achieve 100%. So this is really one way to use PCA to actually see how many principal components you can utilize to explain the underlying variability of the data. So that's really the purpose of this project, to see how you can actually quickly identify how many PCA to achieve the percentage of variability explanation that you specify up front. And hopefully that's been useful for you. Thank you for watching. Welcome back everyone. Let's continue with our theme on unsupervised learning, and the specific topic that we're going to look at is clustering. What exactly is clustering? It's really the approach of grouping a set of objects in such a way that they are in the same group, and this is called a cluster. In some way, the purpose of it is that they have similar characteristics. Okay, so that's really the basic idea. And Wikipedia says this: the task of grouping a set of objects in such a way that objects in the same group are more similar to each other than those in other groups. So that's basically what Wikipedia actually highlighted. There are some examples in terms of application for this. There is, of course, the natural language processing, NLP, clustering them or similar documents together, computer vision in terms of identifying cats, dogs, cars, dolphins, things like that. Stock markets in terms of clustering similar companies together rather than the traditional labeling of it. Market segmentation or customer segmentation. So that's really some of the application for clustering. As mentioned briefly before, unsupervised learning really is one that we don't provide it with target. We just allow the algorithm to identify the underlying patterns and cluster them together. There are a few types of clustering. There is the connectivity-based clustering, which is based on distance. And this one we will talk about, which is hierarchical clustering. There is centroid-based clustering, which is k-means algorithm. These are done by representing each cluster by a single mean vector. There is also distribution-based clustering. These are modeled using statistical distribution, using the expectation maximization algorithm, EM it's called. There's also density-based clustering, which is dbScan. For these is define clusters as connected dense regions in the data space. Alright, for a start, I just want to highlight that we are using the ML Extend or Machine Learning Extend. This is created by RSBT, and if you just have a look at his contact details, Sebastian Raska is the person who created this extension to the scikit-learn. Alright, so it's really useful when it comes to the day-to-day data science tasks, especially machine learning tasks that you want to do. So if you look at this, you can actually very quickly see ensemble bolt classifier, which combines CLF1 to 3 very, very quickly. So it's a really excellent library and package that I strongly encourage you to actually make use of it. Alright, coming back to our Jupyter Notebook on Collaborate. The reason that I want to highlight the ML Extends is because we are using the package library itself and also some of the basic ideas here in terms of the combination of classifiers. So if you look carefully, we have three classifiers. We have classifier 1, logistic regression. We have classifier 2, which is random forest classifier, and then we have classifier 3, which is a support vector classifier. And we have an ensemble vote classifier, which provided here, and the weights are located as such: 2 onto logistic regression, 1 and 1 onto random forest, as well as SVC. So in terms of the data that we have, we just basically extract from iris data, and we are also performing the so-called plotting, so that you can actually visualize what transpires here. So in terms of the plotting, we are plotting the 1, 2, 3 plus the ensemble, and this is a full loop, so you're going to have 4 charts here, the actual fitting of it, as well as plotting of the so-called decision regions, to allow you to actually see the various so-called how does each of the algorithm separate the different classes. Okay. All right, so let's dive into this. So you have logistic regression. Let me just zoom in a little bit. So you have the logistic regression, which you have green, and then you have the triangle, and then you have the blue. There are some errors there. Random forest, notice it's not a straight line, so it's non-linear in nature, so the blue is separated out clearly. There's a bit of difficulties with the green. Ensemble is a combination of all three. Kernel, as you can see, is non-linear as well. Random forest is very zigzag. It's very similar to decision tree. Okay, so let's run this. Okay, so that's all sorted. Don't worry too much about the deprecated module. It will be updated once there's a refresh comes through. So the lesson based on these is, these are what we call control, to actually allow you to have some references. So let's look at Ward's agglomerate hierarchical clustering. There are a few types of aggregation or creation of clusters. You have the agglomerative, which is bottom up. Each observation starts its own cluster, and pairs of clusters are merged as one moves up the hierarchy. You can also have the divisive, which is a top-down approach, and all observation starts with one cluster, and splits are performed recursively as one moves down the hierarchy. If this sounds like decision tree, then yeah, maybe that will be the direction that will help you in terms of understanding. So in terms of the step-by-step, you can actually also refer to the notes that's provided here. You can have, in terms of the shortest distance, which is single linkage, distance between two clusters to be the minimum distance between any single data point in the first cluster and any single data point in the second cluster. So it's based on shortest distance. The second one is complete linkage for this distance, which is the distance between two clusters to be the maximum distance between any single data point in the first cluster, any single data point in the second cluster. So first is based on the shortest distance, second one is based on the furthest distance. You can also look at average. You can use a centroid, which is distance between two mean vectors, mean being average. And there's also one more, which is Ward's method, which is based on ANOVA based approach. Analysis of variance. So it's an iterative process. What it does is that it minimizes the total within the cluster variance, so it's looking at the overall. At each step, the pair of clusters with minimum between cluster distance are merged. Right, so let's look at these step by step. We import the usual library, we create blobs, we store it in the XY, and if we plot it out, this is what you can actually see here. So there's 1, 2, 3, 4, 5 clusters clearly. Now the question is, can our hierarchical clusterings pick that up? So to begin with, we import this from scipy.cluster.hierarchy, and then we're importing Ward dendrogram as well as linkage. And the distance is based on linkage, and we are using the Ward method here. So let's start with the dendrogram. Let me run this. This may take a wee while because bearing in mind this is based on Ward's distance, so it needs to calculate every single point versus the other. So looking at this is a rather large dendrogram. it's a little bit hard to visualize. You start off with here and you split into two, and then this further split into two, and then continue to split from there. Okay, technically this is how we would read it, and the other alternative way to actually view this is to actually turn it by 90 degrees rather than top down. This way we can actually look at it horizontally, which is just as difficult to look at, partially because well, it basically exceeded our screen. One of the technique that we tend to use is to actually truncate the dendrogram. Coming back here, let me zoom out a little. One thing that you immediately can hopefully get a sense of this is that, look, when do we actually stop dividing? Of course, at the nth degree, at the end of it, they're all individual dots or points on their own. We can cluster them, and then, for example, this portion here is a cluster on its own. If you combine them, this is a cluster on its own. If you take these whole lot, it's a cluster on its own. This is a matter of choice, really, and you can either cut it this way, which makes it 3 clusters, or we can actually cut it this way, which makes it 5 clusters. What do I mean by cut? When I say cut, recall that these are measured by distance. Okay, I can specify 75. Okay, if I specify 200, that means I only have 1 cluster. If I say, okay, the distance is 175, okay, before I separate them, anything that's greater than 175 in terms of the absolute, there's no unit here. Greater than 175, we split them into 2, which is what you have here. Anything that's above 150, then we have 3. Okay, well, you can say 75, and there's also 3 as well. If it's 25, then we have 5. So it's a matter of choice for you to decide whether you want it to be split to 3, to 5, or more. That's totally down to the actual business decision that you have to utilize based on the so-called context that you're working on. All right, so come this point, what we did is that we say, I'm gonna draw a horizontal line at 25, which is 1, which gives us 1, 2, 3, 4, 5 clusters. So this is a cluster on its own, this is a cluster on its own, this is a cluster on its own, this is cluster on its own, this is another cluster. So they're giving us 5 clusters. Time to zoom back in. And that will give us, if we plot it and look at it this way, in terms of truncating it, what you will get now is this. You will get this much simplified hierarchical dendrogram. So truncating it this way makes it easier for you to identify in terms of how many, rather than looking at a big hierarchical cluster dendrogram, now truncated is a lot easier to observe and read as well. Why is there 6 here? It's because we specify p is equal to 6, so they give us 1, 2, 3, 4, 5, 6. All right, you can of course specify a smaller number that would actually change the so-called dendrogram itself. So I have not run these cells. Let me run that, and let me first plot it with 6. Okay, so that gives that. If I change it to 3, they will automatically find where the point is and just cut it for you. You don't actually have to do all the work. It will do it all for you. Okay, so that makes it so much easier for you to utilize this functionality. Okay, the last part then is that, okay, fine, we have cluster these into, let's just say we've been able to identify 1, 2, 3, 4, 5 clusters here. The question then is that given a point, how do you know which clusters does it belong? The beauty of using the SciPy is that you can actually retrieve the cluster by using the fclusters function, you can retrieve by either distance or the number of clusters. So here what we've done is that we specify the maximum distance of 25. It will actually based on the 25 and it will work backwards. Okay, so based on 25 we will have 1, 2, 3, 4, 5. Okay, minimum distance of 25. And these are basically the so-called clusters, or what it's saying is that this point belongs to cluster 1, point number 3 belongs to cluster 5, so on and so forth. And what we're doing next is just to plot it out so that you can actually visualize it. And what you have here, you have X and you have the 0 and 1, so that's basically 0 and that's 1 there. And we actually, for the clusters 1, 2, 3, 4, 5, we use the number to denote the cluster's individual identity. So because this is based on the color map prism, you will have 1 being one color, 2 being one color, 3 being one color, so on and so forth. So hence what you get here in the end is actually 5 colors. Okay, continue on from there. What we did earlier is by distance. So this is okay. We can also separate them by clusters. Okay, so let me just do it this way. Now I'm specifying 5. Okay, and the K has already been specified, and what it will do is actually it will automatically calculate that yourself based on the clusters that we use. Okay, so this is based on K being 5 clusters, whereas previously this is based on max distance that we provide here, the criterion being distance, versus here the criterion being maximum number of clusters. Right, that's pretty much all that I want to cover for this portion here. We started off with talking and basically an introduction to MLXtend for you to utilize it for Ensemble. If you want to, you can actually also have a lot of useful contents for the purpose of clustering as well. Then we move on to hierarchical clustering using the Waltz method, and we show you how from pure generation of data using matplotlib to using the dendrogram followed by the truncation of dendrogram, and then finally retrieving the clusters of each of the points. So that's basically the core idea of clustering and using hierarchical clustering to do that. That's all I want to cover for now. I look forward to seeing you in the next lesson. Alright, let's look at another clustering algorithm. This time it's called k-means clustering. How k-means clustering works is it analyzes and finds patterns or clusters within data. It's based on distance measure. If you go through with the scikit-learn documentation, it clusters data by trying to separate samples in n groups of equal variance, minimizing a criteria known as the inertia, or within clusters sum of squares. It does require you to specify the number of clusters. The good thing about it, it does scale really well. How does it actually work? It divides a set of samples into disjoint clusters. Now, each described by the means of the samples in the clusters. The means are what we call centroids. I know that centroids are not points from, although they live in the same space. So that part's important. It's just the mean, the middle of the so-called cluster of points, but it's not a point on its own. The k-mean algorithm aims to choose centroids that minimize the inertia or within cluster sum of squared criterion. Hence the name k-means. You have to specify the number of k, then it actually calculate the mean. Let's go through these step by step. We import from scikit-learn cluster k-means. We specify 9 classes and fit the data and perform the prediction and plot it and just visualize that. You will notice that it stated 1, 2, 3, 4, 5, 6, 7, 8, 9 clusters here. And of course, when you look at it this way, well, some of these clusters are really close to each other, so 9 might not be the right numbers. You can also plot using the MLXtend, which is the library or the package that I mentioned earlier, to see how does it actually divide the 9 so-called clusters, and you can actually visualize from this. Of course, there are some challenges. The global optima result may not be achieved. The number of clusters must be specified beforehand. Nobody knows how many clusters there are, so to force you to have to specify beforehand makes it a rather difficult challenge. It is also limited to linear cluster boundaries, and it can be quite slow for a large number of samples. So these are the challenges. So how do we actually choose the number of clusters? This is where we actually make use of what's called the elbow method. It uses intrinsic matrix. An example is the within cluster sums of squares error, and scikit-learn has already provided it through k-means, which is after you've fitted it, and the dot inertia. So as I compute this, it will give you the number. So what we can do is that we can loop through the number of clusters. 1 cluster, 2 clusters, 3. Basically we're specifying the k. K is equal to 1, k is equal to 2, k is equal to 3, all the way to k is equal to 8. And then we can actually keep a copy of all of the inertia and look at, okay, if we specify k is equal to 1, what is the inertia? K is equal to 2, what is the inertia? Then I'll explain to you how do you actually pick the number of optimal clusters. So if you look at this, how would you pick? The way the elbow method works is where you see the kink, all right? See that you notice the sharp drop and then a plateau. So they are essentially what this is actually saying based on the elbow method. One place that you can actually choose the so-called k is 3. That's actually a natural choice. Second one is 4. The third one is 5 before it becomes fairly flat after that. So 1, 3, 4, or 5, of course, you can actually inspect it further. We know the answer to this. It is 5. But nevertheless, when you look at this again, say, is there an answer for 3? Possibly. Okay, maybe that's definitely 1 on its own. This is potentially you can argue for 1 on its own here, and these two could be 1. You could also argue that it's 4, 1, 2, 3, 4, or 5, as we can see here. Right, so that's really the elbow method. Plot it and then look for where the kink, basically the edge of your elbow. Another method is what we call silhouette analysis using a mathematical formula. How do you actually make use of this? The value of the silhouette range between -1 to 1. Close to 1 indicates that the data point is very similar to other data points in the cluster. Okay, if it's close to -1, indicates the data point is not similar to the data points in this cluster. So let's import the matrix called silhouette score, and then we loop through once again. Range this time around from 2 to 8. You can actually basically use the silhouette score and calculate the difference between x and the labels itself, and finally plot that. Now, how do you interpret this or make choices? Based on silhouette analysis, this portion here, this peak before it drops, is either 4 or 5. So essentially that's how you actually pick using the so-called silhouette analysis method. The third and last method is called the mean shift. This will actually identify the so-called number of clusters and recommend the number of clusters for you. Those that we talked about beforehand, be it the silhouette, be it the I have a mind meltdown, be it the elbow method or the silhouette analysis, you actually have to perform that decision yourself. Whereas for mean shift, it is non-parametric. It will actually identify it for you. All right, so let's do this. Okay, couple of things we need to do. We do need to import mean shift. Then we have to estimate bandwidth. We also need to import cycle. So to do this, we perform the instantiation, okay, of the estimate bandwidth, and then we also instantiate the mean shift. Okay, and followed by looking at the cluster centers and then print it all out. Okay, so this is what's specified as the centers of the cluster, the x and y axis of them. What we can do, follow this, is that we can print the number of clusters in input data. It recommends 5. we can actually visualize this and see that 1, 2, 3, 4, 5 is what's recommended by the mean shift algorithm. How does it work? It identifies central location by these following so-called, you can call it algorithm, but let me just walk through that with you. So for each data point, it identifies a window around it. Then it's followed by calculating centroids, and then it updates the centroid location. It continues to update this window, meaning expanding it, and it keeps shifting the centroids, the means, towards the peak of each clusters. So it shifts to the left, it computes a value, shift to the right, it computes a value. So it learns to actually identify where the mean is. So this is what you call by mean shifting until it identify where the center is. So it'll keep doing this until the centroid is no longer moved at all. A pretty neat algorithm at that, and it seems to be able to identify this really well with 5 centers. It doesn't always work that well though. For this case, the centers are really distinctive, so it actually picked it up very well, and sometimes it fails. Not all 3 methods worked, so sometimes you have to use all 3 just to actually use one to confirm the other one is correct, to give you some confidence as well. With that, I'm going to stop here. Thank you once again for watching this lesson on clustering and the 3 different methods of identifying the center. The 3 are the elbow method, the silhouette analysis, and also the mean shift. Thank you once again for watching. Welcome back, everyone. In this segment of the training, we're going to start looking at a very simple neural network. This is really to get you started on the different components of neural networks, and we will start with this very simple problem statements. So let me just hide the table of contents. You can bring it up by clicking on that. Let me start with this really simple problem statement, and then we'll build on that. To begin with, we have some really simple sample data generated by the following function. Y is equal to 3x plus 50, and I hope that your high school math doesn't fail you. Y really is the dependent variable, 3 is the slope, and 50 is the intercept. In machine learning, we also call it bias. Let me just bring it back to the simple function here. Let me just bring that up just so that you can see how this was actually calculated. Okay, let me just right, we have x value, and the intercept is 50 right throughout, and the dependent variable, or y, that we are looking to predict. As I mentioned, the formula is y is equal to 3x plus 50. And to start off, x is minus 20, multiplied by 3 gives you minus 60, plus 50 gives you minus 10, so on and so forth for all of these. Let me just bring that up. Hopefully that's a little bit clearer now that I've enlarged it. So essentially we created all of these data. So if you look across, there's I think 8. We will use the last row of data, this row of data, as the so-called value that we want the model to predict. These will be the value that we will provide, meaning x and also y. We will provide it to our algorithm as the sample data. Now coming back to the Colab, now of course in this case it's a contrived example, one that we created and with the exact data. In real life, however, we have no knowledge of the real functions. In our case, we define the function ourselves. But in real life, we don't have any knowledge of that. We of course only have the data, and the data that we usually see is the input data, which is this column of value here. Let me just highlight in green, and the so-called corresponding dependent variable. So these are basically the only 2 columns of data that we have. We basically have minus 20, minus 10, minus 5, 35, 1, and 53. We only see the mapping. Of course, the X could be many features, but let's just focus on one feature for now, which is 1X. It could be X2, X3 in real life. So in real life, we only have these data available to us. Of course, in a situation when we know the real function, you can just write the code for it. It's nice and simple, but of course, we don't. Okay, we have to estimate the function using the data given, and that is really the challenge. And we are using machine learning in the specific case that we're doing here, neural networks or deep learning, to solve this problem. So let's go through these line by line. To start with, we import the libraries. Before we do that, let's just check our runtime is using Python 3 and GPU. Okay, so once we run that, we basically need to import NumPy and also TensorFlow. We're using TensorFlow 2.0. And next thing is the data, preparing the data, the Keras, which is what we're actually using here under TensorFlow. Expect the data to be in an array format, the NumPy array format. And so we need to restructure these X and Y pair into this format here. So X is NumPy array, and we actually set the data type as float. So let's just run that. Let's start with some really basic definitions that you might find useful. I talked about X just now. In machine learning language or jargon, we call this feature. It's also sometimes called the independent variable if you come from the statistics space. It is sometimes also called the inputs. And the Y is our dependent variable. Quite often it is called the label, also called targets, and sometimes called the output to the actual model itself. So if you read these terminology, don't get thrown off. Just understand that there are multiple names for the same thing. And the sample or example is really the pairing of the feature when the label or the X and the Y provided to the machine learning algorithm during training. So in our situation here, we have 2, 4, 6, 7 pairs of feature as well as the label, which we will feed to the machine learning algorithm to train it. And hopefully it will actually be able to extract the pattern and be able to generalize and predict the answer. Right, the next step then is to define our model. We will just start very simply with just the dense layer, and I'll explain what the dense layer means in the next lecture. And we will only use one neuron for this. Right, in terms of the model, we do need to specify layers. Okay, I'll come back to that a little bit with a pictorial example. The step then, first of all, is to create an instance, also called instantiate a layer by calling TensorFlow, TF is short for TensorFlow, .keras.layers.dense. And we also need to specify the input shape, meaning the input data that we have, we need to let Keras know what is the shape of it. Okay, without specifying it, Keras will not know, it will just throw an error. So we do need to provide the information, what shape, what dimension. In our case, there's only one single value, which is a float. And the units are equal to 1, specify that we are creating a neural network with only one neuron. Okay, one neuron. Sometimes this is called internal variable. Of course, the more complex our problem is, the more neuron that you need to specify. The neuron can be width by width, meaning each layer has however many that you define. It could be 1, 2, 4, and upwards, or multiple layers, meaning each you can have one layer of 5 neurons, or you can have 3 layers, each having 5 neurons. So that really is defined using the unit itself. Okay, the units define how many neurons in one layer. Okay, for our problem, we will only make use of one layer. The input shape is our first layer. Okay, so with us specifying it as 1, we are defining our neural networks to take only single value, which is a floating point number. Again, because this is our only layer, it is also our final layer. The units then specify the number of output from our neural network, which is also a single value, which is defined here as 1. Again, this is a single float point number. Now, you need to take care in a multi-layer network, the size and shape of the output layer as defined by the units will need to match. So if you have multiple layers, so when you go to layer 2, for example, and the layer 2 takes 3 as the input shape, then your units here at the end of your layer 1 it will also need to be 3. Of course, layer 2 follow what was defined in layer 1. If layer 1 specified the units is 5, then your layer 2 input will need to be the matching exactly the same as 5. So let's start with defining our layers. We only have one layer, and this layer we call it layer 1, layer underscore 1. TensorFlow.keras.layers.dense, and the units is equal to 1, and the input shape is equal to 1 as well. Okay, and we provide this as a parameter to TensorFlow.keras.sequential and have that in a bracket and instantiate this and call this model. So our layer 1 we call it layer underscore 1, and our model we call it model. So again, let's just run this. Okay, you can actually, there's two ways to define this. You can do it separately, defining the layer separately from the model, or you can actually have it inline like this, TensorFlow.keras.sequential, like this part, and the inside here, you just typed out the whole thing, TensorFlow.keras.layers.dense, defining the units as 1 and also input shape as 1. Alright, that's really defining it. Nothing has happened in the background. So the next part then is to actually compile our model. In the compilation of our model, we need to specify two things. One is a loss function, the other one is an optimizer function. The loss function is a performance matrix. Okay, it is used to measure the errors of our model against the actual outcome. It is also called a loss function because of the difference between our prediction and actual is called loss. So essentially, the loss function measure the scale or the difference between the prediction and the actual. Of course, the smaller the better, the bigger is not ideal, but the difference is really what's called the loss. And hence we call this function to measure it called loss function. And the optimizer function is the function or the mathematical function that is used to adjust the model parameters to improve prediction accuracy. Okay, so that's the function that we use to adjust the internal value of our neural network so that the accuracy can be improved as the learning progresses. Right, there's one more thing that we need to define, which is not a parameter, it's actually a hyperparameter. It's called hyperparameter because it's nothing to do with the actual machine learning model, but it does have an impact on how fast or how slow our model learns. So that's why it's called hyperparameter. It still impacts on the learning, but it's not one of the parameters of the actual machine learning model. For the learning rate, I've defined it as 0.1. I've also tried 0.001, which converges really slowly and insufficient in the time that we want to do. 0.01 is faster, and 0.1 is the fastest. Okay, so in terms of the model.compile, we need to provide, as I mentioned before, the loss function. In this case, we use the mean square error, which we will discuss in later lesson. And for the optimizer, we use the TensorFlow Keras optimizer, the optimization algorithm called ADAM. In terms of the learning rate, we provided 0.1. So again, let's run this and compile our model. I provided a bit more so-called links for you to refer to. One is about selecting the right evaluation matrix. It is dependent upon the nature of your problem, whether it's a classification problem or whether it is a regression problem. So the matrix that you use does matter. And the Adam optimizers is one of the many optimization algorithms that you can use. Again, I'll provide a link here for you to explore a little bit more that's suitable for your problem. All right, the next step then is to actually proceed to train our model. In TensorFlow Keras, the way to actually train it is called fit method. Now, just remember that our actual model was y is equal to 3x plus 50. The slope is 3 and the intercept is, the slope is 3 and the intercept is 50. These are the two coefficients that we're asking the neural network to estimate, because we didn't give it the actual formula. And in real world, we don't know the formula anyway. So we need the actual machine learning model algorithm to actually estimate it for us. So the neural network, what it does is that it starts off with a random value, since it has no idea where to start anyway. So it just have to use a random value. And this random value is also called weights. And use it and the input y to compute x. Okay, so it will combine, be it multiplication, it will be multiplying x plus the bias to compute y. So basically it's using it in combination with the input parameter to calculate y. So because the weights start off with a random value, of course the prediction will start off with large errors. That's the first step. Then what the algorithm does is that it takes the error value or the loss, and then it calculates it using the loss function. We have one too many s here. And take the prediction and the actual value. So basically, using the loss function, it calculates the loss value, take into account of what the prediction is versus the actual value. The next step then is the optimizer. Then make an adjustment. Okay, of course it is subject to the learning rate that we define. Okay, and make the adjustment to the weight, and the ultimate goal is to reduce the loss. And each time that we allow the model to see all of the data set is called an epoch. Okay, each epoch is the full iteration of the example that's provided or that we have. And with each epoch, the algorithm then start over again in terms of its learning. There are 4 parameters that we need to provide for this fit method. We need to provide our independent variable, x, our dependent variable, which is what we were trying to predict, y, and epochs specify how many cycles should be run. And then we have another argument which has nothing to do with the model itself, but more to do with the method that we're using, is to output the so-called the results and display it onto the console. In this case, we put false so that we are not bombarded by the result. We're doing 1000 epochs, and we need to provide the x and y. So let's just run this and store this in the results in the variable called history. Right. Okay. Right now, having run that, we have no idea whether it's done well, whether the model is good or bad, or how did the learning go. So what we do next is to actually visualize the model training. The good thing is that Keras comes with the history, as I mentioned before. You can actually make use of history to visualize our performance. And what we usually do is that we measure the loss or the loss magnitude and measure it or plot it against the number of epoch that we run. Okay, and from there, then we look at how the performance of the loss curve looks like. So if you look at this, it started off, as I mentioned before, because the weights, the internal variable started off with random value. Of course, the loss will be large. As it start learning, it drops. Okay, as we go through more and more epoch, the actual loss drops. Okay, and basically what our algorithm has done is that it's learning. Okay, it's learning to minimize the loss, and after adjusting the weight, it continue until the losses start to actually taper off. Of course, the learning still goes on. but the point here is that around this portion here, about 80, just shy of 100, most of the learning is done. It continue to actually learn. And the next step then is for us to actually, let's just plot this. The next step then is to actually look at the under the hood in terms of the prediction. Recall, you probably won't, x was 100. When x was 100, the y value is 350. And if you look at, we're providing x as 100 as input here, and we're asking the model to perform a prediction, it comes out with a value that's pretty close, 351 instead of 350. So the errors is actually very, very narrow at this point. And if we actually look under the hood and look at the actual underlying weights, notice that there are two variables here. Both of them are float. The first variable is our slope that we wanted it to estimate. Comes up at 3.08 versus 3, which is really, really close. And 44 here versus 50, again, it's really close. Considering that we only really provided it with 7 data points, it is able to actually come out to predict and also, it was able to estimate so closely. That's quite remarkable indeed, even though there are not a lot of data for this. So that's really the basic that I want to explain to you in terms of what the machine learning model or the neural network that we've done here. The simple process here is to highlight to you how powerful it is. That's the first thing. Second thing is that it was able to actually estimate the real function really, really closely. And the third thing that I want to highlight is that in terms of the dense layer, which is what we're going to talk about next, we don't even have multiple layers. We only have one dense layer. And from this single dense layer, we were able to estimate the algorithm itself. Okay, so we will talk about the dense layer next. Finally, we've walked through the process, okay, from importing our libraries, preparing the training data, all right, and defining our model in terms of the step-by-step process. And after defining our model is the compilation, providing the loss function as well as the optimizer, actual fitting or training it, and finally visualizing it to see how the learning has taken place or how it has done, and a bit on the prediction side. And hopefully these 5 things that we've covered here has been helpful, and I hope that you have a better and deeper understanding of the what we've done. And yeah, play around with it. In particular, the one part that I would like you to play with it is this learning rate here. I had to do all of these, and what I've noticed is that there's no one bullet fits all. It's something that you have to actually experiment with to actually find what's the ideal learning rate. So with that, I'm going to stop. Thank you for watching. Welcome back, everyone. We're going to start looking at the actual architecture of a neural network. We're going to start with something that's a little bit more complex. This is a simplified neural network, but it's much more complex than the one that we just coded up in Colab. Looking at this, you can see that there are 3 layers. There is the input layer, there is the hidden layer, and there is the output layer. So let me walk through them one by one. The input layers are the features. Okay, in our example previously, we only have one feature, so in that case you would probably represent it as x1. In this neural network architecture, there are 3 inputs. Okay, so there's x1, x2, as well as x3. Moving on to the next layer, which is called the hidden layer. The reason it's called hidden layer is because it's not exposed to the input. Neither is it actually exposed to the output. Hence, it is the hidden layer. Now, with the hidden layer, we don't have any direct influence over the hidden layer itself. And the output layer is the output of our machine learning model. And that's the layer that actually provide the outcome of our machine learning prediction. So if you look at this, the output layer has one output, meaning it will generate one single value. So if you look at the whole architecture of this neural network, it takes 3 inputs, it will come out with one output. The other thing that I want to actually highlight is notice that the lines, each input is connected to the next layer fully. Hence, this is also sometimes called the fully connected layers. And this layer is also called the dense network, and likewise for this as well. And let me just walk through in terms of the mathematics of this. You don't need to understand this because you don't need to actually calculate it. It will be all done by TensorFlow. The estimation, the computation will be all done by TensorFlow. We'll start with the N1, which is this neuron here. It takes the input from X1, X2, X12, X3, so these three. And X1 is multiplied by the weight of 1, which is this represented by this line here. And X2 is multiplied by W12, X3 is multiplied by W13, and then plus a bias term. B1 here stands for bias term, much as same concept as the intercept in the y is equal to mx plus c from your high school. All right, so the W11, W12, and W13 in the beginning, as I mentioned in the previous lesson, is that these weights are randomized. Okay, when it's first, the algorithm doesn't know what's the right weight, it will just initialize with any random weights, and then it will just compute the N1. Likewise for N2 as well. The result of N1 and N2 is being provided as an input for N3. So if you look at the formula right here, is represented right here. N3 takes in the input from N1 and multiplied by another weight, and N2 is multiplied by another weight plus another bias term. Looking at this, you can see that this is actually a much more complex in representation of our so-called proposed problem. The problem that we originally envisaged was y is equal to 3x plus 50. There's only one input, and there's only, again, one so-called slope plus one intercept that we needed to estimate. But when you look at this, there are 3 inputs. Obviously, it's not a problem that is representation of the problem that we proposed, and it's far too complex to represent our problem anyway, and it's likely to not. It will be overkill. It will give you the false answer as well. So let's look at something much simpler that we code up in our Colab earlier, and this is the model that we propose and compile and fit as well. With this, what we had was one input layer, which we defined it in our tf.keras.layer.dense. We had an input shape of 1, which is this one here. And for the output layer, we had the units equal to 1. Again, that's one output, which is what's shown here in our output layer. So this is our dense layer. From input to this, that's our dense layer. Of course, it's not very dense. It's only really one input here, one output, one neuron and one output. And in terms of the representation, this is what it looks like. N1 is equal to the X1, which is the input, multiplied by the weight, W11, plus the bias term. And if you look at the representation of this, is much closer to the problem statements that we have. Of course, the problem statements were created by a real function, and it's not like the reality is that in real life you're not going to be able to see that real function. So we are using the algorithm to actually estimate the function itself. The final point that I wanted to make here is that neural networks quite often are much more complex than either of these. There can be multiple layers, and each layer have many more neurons than 1 or 2. It could be 3, it could be substantially higher. And there are also other so-called steps that you can perform in between layers as well. Right now we only have one hidden layer. It can be 4 or 5 and many more, but we'll see different architectures for the flexibility to solve the problems at hand. With that, I'm going to stop, and thank you for watching. Just to summarize, we talked about a more complex neural network architecture versus a much simpler one which solve our problem. I look forward to seeing you in the next lesson. In the previous lessons, what we did was that we looked at a dense layer and we looked at a regression-based problem. So in this lesson, we're going to step aside and look at a classification problem and add a few new concepts onto it. So essentially, we're going to cover, we already covered regression, so in this lesson, we're going to cover classification. We talked about another type of layer or method called flattening. In the previous lesson, we talked about a dense layer. We also talk about what's called an activation function, ReLU, as well as softmax. We'll cover a regularization method called dropout and why we would do it. And finally, training and testing as a concept, but we won't actually use it or look at it in this lesson. But these are the basic concepts that we will talk about, we will highlight as well. I want to just talk a little bit about the purpose of flattening. In the datasets that we're going to be looking at is called MNIST dataset. It's provided and created by Yann LeCun. And you can actually follow this link along. It is called MNIST database. It's prepared, as I mentioned, by Yann LeCun. It's basically have 60,000 examples and 10,000 examples. And it's what's called handwritten digits from 0, 1, 2 all the way to 9. And it has a corresponding label to go with it as well. It has the image of the handwriting or the digits as well as the label itself. So these are all the different tests and that people has performed. You can also find this in Kaggle. Let me just go there. All right, digit recognizer. It's very famous. It's one that people use to actually, well, it used to be the Hello World. Nowadays, it's pretty much the baseline for people to actually understand how it works. Anyway, so this is the digit recognizer. So this is a good place to actually get started. I'll let you read a little bit more about this, and I'll come back to the actual Colab code itself. Right. So these are the concepts we're going to cover. So let's get started. For a start, we will usually, as we always do, import the libraries. The next part is that we do need to import the data. The good thing is that the data is provided in the Keras datasets. It's under TensorFlow Keras datasets MNIST. We just need to import that by loading the data, and then the data is being sorted into training set as well as the test set. Just to give you a little bit more metadata about these datasets, the XTrain has 60,000 in terms of shapes. It's 28 by 28. These are the features. As you can see, these are the XTrain. These are the features. In the previous problem that we looked at, we only had one feature. The one feature was the float data point that we provide, whereby for this, it's pixel. We have 28 by 28, meaning 28 pixel height by 28 pixel wide. So if you multiply that out, there's 784. So this is the actual shape of the data that we have for both the XTrain as well as the XTest. For the Y-train, because it's only just label 0, 1, 2, 3 all the way to 9. So that's why it does not have a dimension. The actual shape itself is actually 1. And likewise for the test as well. So if you look at the unique value for Y-train and Y-test is 0 all the way to 9, as I have mentioned. Right, the next part is just to let you see what does the image look like. The XTrain here is we're looking at the first data point on the XTrain. So you can see that this shape what looks like a 5, and if you want to verify that, you look at the corresponding label provide the index, which is 0 as well. If you print that out, and it will show you the actual label is 5 indeed. The one thing that we do need to do is to do what's called data preparation. Because our data come in the form of unsigned integer of 8, we do want it in float. So what we do is actually we and because the unsigned comes in the 0 to 255, it is in grayscale, so we do need to convert it to float, so of between 0 and 1. By dividing by 255.0, which is a float, it forces the whole answer to become a float. Okay. Yep, already run this. So the first step that we do is that we flatten the pixel itself. The pixel in MNIST come in the form of 28 by 28, 28 high and 28 wide. So what we do is that we convert it from a 2D array to a 1D array of 784 pixels. That's really what the flattening performed. The second layer is a hidden layer. It's a densely connected layer of 512 neurons. Now, naturally, this 512 can be defined as another number. In this case, in terms of our net model, it's 584. It may be somewhat on the high side. This is something that you need to play around with to actually come to an optimal architecture that works for you. Now, there are 512 neurons here, and each neurons takes input from all of the 784 nodes before. Recall what we have was, as the first layer of input, 784 pixel, and each pixel was 256, consists value of 256, but once it converted to float, takes a float instead of the 0 to 255 value. And once we actually have flattened it, now what we have is actually a fully connected layer from 784 to 512. The output layer is another dense layer, and this time around what we have is a 10 node, what's called a softmax layer. Each node represents each of the digit class. Because we have 0, 1, 2 all the way to 9, we really have 10 classes. We use softmax because softmax generate the probability of each class based on the actual input itself. So that's really what's nice about softmax, and that's why we actually use it. Right, let me just correct a typo here. It should be layer. Right, so let's compile our model. So this is the portion where we have Keras sequential, we have the flatten, where we define that the input shape is 28 by 28. We have the dense layer with 512 units. There is the activation function called ReLU, as well as the activation function called softmax. Unlike our first example from the previous lesson, where we don't have any activation layer at all, here we have two. The activation, the last layer, it's about generating the probability. So it doesn't actually have any so-called learning per se in it. But ReLU, on the other hand, has a lot of value to go with it. The reason that we are looking at ReLU instead of no ReLU or no activation function, like our first model that we looked at in the previous lesson, is this. The first model was very simple and it's linear by nature. Because it is linear by nature, there's no non-linear so-called functionality or there's no non-linear features or characteristics that we needed to learn. So a really basic, simple algorithm with no activation is sufficient. In our case, however, if you looked at this, you can clearly see there are a lot of non-linear. By and large, it's actually non-linear rather than linear in nature. Hence, we actually use ReLU. Okay, now I said a lot about ReLU. You probably have no idea what I'm talking about. So let me, I did have a link here for ReLU, which is, I believe, up here. So let me just pull that up and bring this back to where we were, which is right here, ReLU. Okay, there's a nice write-up here by Dan. Yep, by Dan. And he introduced and talked about ReLU in detail, and you can see that If you're finance trained or come from an accounting or with exposure to finance, you can see that this is a little bit like option. In fact, the actual function is actually an option function. As anything below 0, negative value, it will automatically default to 0. Anything above 0, it will take the value of its own. So this is actually what's, you can see that this is non-linear in nature, and it introduces what's called interactions and non-linearity. So I will leave that for you to explore a little bit more. Yeah, it's an interesting function. There are other activation functions that you can make use of, but in this case, we are making use of ReLU as well as softmax. We printed the model summary here. So you have the first layer, which is really the flattened layer. Then you have the hidden layer, which has 512 neurons. And finally, we have the dense layer with an output of 10, which is the 10 classes that we have. So this is by design. It's really relate to what you want your output to be. Okay, in terms of the model compilation, we've used RMS-prop as the optimizer, and also sparse categorical cross entropy. This is the right type of loss function for classification. And you can of course try using Atom as the optimizer. I'll leave that for you to try that out. Some of these is just really, again, trial and error. And finally, with the matrix that we use to measure the performance is called accuracy. And in terms of the fitting, we provide the X training data, Y training data. We are only training it for 10 epochs, and the batch size, we set it at 256. The purpose of the batch size is to inform the fitting method how often should it actually recompute and change the weighting. So that's what the batch size is actually for. What I already added a comment here, basically update the model. Some of them are hidden variables after every batch of 256 image. Notice that each epoch we train 60,000 images. That's the 60,000 images that we have, the training images. And looking at the loss, it started off quite high and it drops all the way to 0.13. In terms of accuracy, it started off 91%, it reaches 99.66%. You can argue that that's actually really, really high and looks really good. But as I mentioned before, there may be a danger of overfitting, and we shall see when we compare against our second model. And in terms of the loss magnitude, only 10 epoch were already close to, well, 100% really. And if we look at the lost performance of the accuracy, and if you look at this, the test accuracy based on the test data for the model is 98. Now, 98 doesn't seem like a big deal, but when you look at your accuracy in training is 99.66, you will be actually somewhat be disappointed when you see your value is 98.1. It's a good 1.5 percentage drop. And this is what I'm trying to highlight to you, is that you should actually pay attention to these small details, as it's highlighting to you that your model is likely to be overfitting your training data. Let me just sidetrack a little bit. Much like how we learn when we take or go for an education, be in primary, secondary school, and tertiary, of course. As you learn the materials, as the teacher provide you with the example, when you actually go into an exam, the last thing that you want is the teacher to give you the exact same question as the tutorial questions. Well, why is that? The reason will be that that's called memorization. It doesn't actually test your ability, and test that you have actually learned the concept. What you can essentially do to survive or do well is that if they are all same questions that you've seen before, basically what is that situation will be what we call memorization, which is not learning at all. What you really want is that you learn a different set of questions in tutorial, come the exam is similar but different. Okay, similar concept, or the concepts being tested are the same, but the question stem, how the wordings are, the numbers, everything should be totally different. And that will be a proper test of the learner or the student's ability have a grasp the concept rather than memorizing the answer from answer or training data that they've seen previously. So that's really the first part. The sidetrack that I want to highlight is the same concept when it comes to training your machine learning model. Now let's look at a second model, model number 2. And if you looked at it, you will see that there's a slight variation here, which is that we have a smaller architecture. Rather than 512 neurons, now we only have 128. We also have another additional layers here called dropout with a value of 0.2. The rest are the same. Okay. Adams used rather than RMS prop. Other than that, everything else are exactly the same. Okay, why those change? This is obviously a smaller architecture, so its ability to learn is obviously less than the 512 neurons, but it may be sufficient for our task here. 512 might be a bit too flexible to learn the problems that we are facing. And the other part about the dropout is that the 20 or 0.2 here is 20%. It's forcing carers during the training phase, 20% of the neurons get dropped randomly. What that's actually forcing the neuron to do is obviously to work harder. That's the first thing. Second thing is that it does not allow it to memorize the so-called training data it has seen before. So that's what the 20% dropout is for. And that kind of variation, the dropout of 20% variation is to actually what we call regularization. It's a way to make sure your model is a lot more robust to avoid the memorization problem that I highlighted. And the second thing is that you really are driving it to learn the general concept or be able to generalize towards when you actually start looking at the test data. So let's run this. Okay, the Atom is just a change just to see if there is a speed or change in terms of the optimization. Doesn't seem to be, of course, partially because our training is not a large data set, and also it's not a very complex data set. If you look at the time, 1 second, 18 microsecond, they're exactly the same. There's hardly any difference. But the part that comes out quite strongly is the accuracy is only at 97%. It's still climbing. Although this is still climbing, but you can see that the climb change, or the percentage change from each epoch has slowed down. Whereas for this, it's still at 97%. It seems like there's actually more room. It still has more room to grow or train. And let's plot this out to see. Yep, this is definitely a lot steeper than what we looked at. Let's look at the model out of sample accuracy. It's 97.82, which is actually very interesting. Let me just hide this so that we can see. You notice that because of the regularization that we did, which is via dropout, and also the smaller architecture, you can see that the accuracy within the training and also the out of sample is very, very close. 97.88 to 97.82 is basically no change at all. And that's telling me that number one, this is the appropriate amount of learning, maybe more, but definitely not overfitted as compared to this earlier one that we saw, where within the training is 99.66% versus 98.18%. So the difference inform you that the first model is overtrained and basically has gone into overfitting. Right, let's go one step further in terms of prediction. Let's look at the first data, the X test, the index that we're looking at here. The shape, we just need to reshape it to just basically 1, so that because our architecture is expecting 784. And if you just feed 28 by 28 without informing it this is one sample, it will throw out an error. So we reshape this and we feed it into the prediction. And what you can see here is that, of course, this is 0, 1, 2, 3. But what it's telling you here is that it's 99.93% sure this is a 7. And it's 1% unsure that it is a 2, 0, 1, 2, 3. Okay, there's 5% probability that this is actually a 3. Okay, let's have a look at the prediction. It is actually a 7 based on the highest value, and if you look at the actual label itself, it is a 7 as well. Okay, so that's really the prediction step. Let me just quickly summarize what we cover and some of the concepts we touched on. We talked about the fact that we looked at the regression example in the previous lesson, and this is a classification problem, and it's a 10-class classification problem. We looked at what is a flattening layer. We also looked at the activation ReLU as well as softmax, and we talked about the purpose of dropout. We briefly touched on training and testing. We will go into a little bit more depth in the future lesson on training as well as testing. With that, I'm going to stop. Thank you for watching. I hope you have learned something out of this lesson. Welcome back. In this lesson, we're going to cover binary classification. In the previous two lessons, we looked at regression based problem where you are predicting continuous variable. We looked at classification problem as well, but it's 10-class classification problem, which is slightly different from binary classification problem. When it comes to binary classification problem, we have a two-class structure. So it's either this or that, 0 or 1, cats or dogs. In this case, we are going to continue with the MNIST dataset with some slight variation. The variation is that instead of predicting whether it is one of the 10 digits, we're going to convert it into whether the digit is a 5 or not a 5. So hence turning it from what you will call a 10-class or multi-class classification problem to just a binary class classification problem. So let's get started. We're looking at installing our basic libraries, download the data, and preparing the data. The one thing that we do want to actually bring to mind, just a couple of backend features of Keras, is that you need to bear in mind Keras by default takes on what's called a channel last image data format. The funny thing about the image world is that there are two types of channel first and channel last. The channel first basically means that the first channel is default to have the value come first, then the image rows and columns. Channel last will have the one comes at the end of it. By default, it's channel last, so this is something that we need to keep in mind. So let's run this. So we do need to do what's called a if class. I should really change this to last. Okay, then it should really be channel last, and it gives us the input shape of image row, image columns, then 1. The next step then is to convert our data into what's called the converting it to a float rather than 0 to 255 and unsigned integers. And this is the part that I was talking about. If it is not digit 5, then y is converted to 0. If it is digit 5, then y target is converted to 1. I'm going to skip this. Right now, our y value is in the form of integer 64. That's enough or sufficient for our use rather than having to convert it to float 32. Let's come to the network architecture. We have the first layer being flattened. followed by a dense layer with 128 neurons. The activation function we're using is ReLU. And then we have another dense function with 2 class, specifying 1 basically means is 0 or 1. And finally, our activation function, instead of a sigmoid, which generate probability, is now there was softmax, now is sigmoid. Sigmoid is basically default to either 0 or 1. And while we're running that, we have the model summary that's going to be printing out the model architecture. I'm going to run these at the background so that we don't have to wait for it to run. And the optimizer we use is the simple stochastic gradient descent. And the loss here, instead of the sparse categorical cross entropy, you are using binary cross entropy, because we only have a binary system or binary class here. And finally, we also put in the accuracy here. So this is the architecture. We have 3 layers: the input layer, the hidden dense layer, and finally output, which is just with the output shape of 1. Moving down here, we are splitting our training data furthermore into train, validation, and test. This is something that will be more and more prominent as we're going forward. Right now, we're just keeping it really simple. The first 50,000 is going to be used for training. The remaining 10,000, meaning from 50,001 to 60,000, that 10,000 will be used for the purpose of validation. This allows us and allow the algorithm to actually continuously tune the model. They will be trained using the training data, and then the validation will be used to validate. And if this is to avoid the overfitting problem that we mentioned before, we also don't want to touch the test data, because if you're touching the test data, technically it's supposed to be only touched once at the end of your model. If you touched it, then what you have done is actually you allow your model to peek into the answer already. So really what you want to do is actually set aside some of your training data for validation to verify that your model hasn't been overfitted, then run the test on the test data for one last time. So we're doing it for the validation. As you can see here, the first 50,000 is for training, is renamed to xtrain_1, and then the 10,000 for validation. We've run these. Now this is the actual training itself. We need to provide x, provide y, how many epochs, which we have already defined here, 20 epochs, and 128 is our batch to update the weight. And finally, we have this new parameter called validation data, which we will be feeding in to validate our data, which is the in terms of the parameter you need to provide is in the form of a tuple with x value and validation data. So as you run this, you notice that there are more information than before. You have the loss, you have the accuracy as before, but now you have additional information, which is the validation loss as well as accuracy. Let's go to the end of our training. You will see that the accuracy is 98 and the validation accuracy is also around 98.24, so that's looking quite good, and because they are fairly close together. So that's looking at the raw data. We can also visualize it by plotting it out. And when you plot this out, you can see that our training loss is continuing to decrease, and the validation loss has plateaued a lot sooner. So around here, about 10 epochs, the decline of the training is much faster than the validation itself. What this is actually telling you is that we are starting to overfit our training data. Actually, correction. The validation is that's correct. Validation is actually a solid line, and the dot is the training loss. And what this is really telling you is that we're starting to overfit our training data, although the validation is still going downwards, just not as fast as the training. And that's something that we can correct by using some of the regularization technique that we talked about before, dropout being one of them. Right, so let's plot the training accuracy versus the validation accuracy. So this is from a slightly different point of view. This is plotting loss. This is the training and also validation accuracy. From an accuracy point of view, it's pretty much the same picture. The accuracy for both are still climbing, which is quite healthy. We can actually continue to train like this to actually see what the final outcomes are. But nevertheless, this is actually very useful. Just to summarize what we've covered in this lesson, we looked at binary classification rather than 10-class classification problem we looked at. We prepared data as before. The slight variation in terms of the introduction here is what's a new feature called the Keras backend, just to check what is our image in terms of the data format. Be it channel last or channel first, that part is important. Well, of course, we convert this from 10 class to a binary class problems. We looked at sigmoid instead of softmax, and we also look at SGD, which for all intent purpose for something like a simple architecture and simple data set like this, they aren't much very different than the other so-called optimization algorithm. The part that I do want to highlight is that with something new is the training as well as the validation and test data here. This is where we actually have departed from the previous lesson, and this is a new concept, is that the baseline is that we always keep our training for training, and then we set aside some data for validation, and finally test data for the end of our modeling development or the model development. Thank you once again for watching. I look forward to seeing you in the next lesson. You might be forgiven for thinking that deep learning can really only be used for integers or value-based problems. What about text and sequence of text? 2 years ago, probably not a well-known fact by now, it's fairly common knowledge that deep learning can be applied to text-based problems just as easily as integer-based or value-based problems. We're going to have a look at one such problem, which is binary classification. We are applying this to the IMDb database. What is IMDb? IMDb is actually the so-called repository, I guess you can call it, or the website that collect all the viewers' view of a movie. And they do provide these data for you to utilize. It's a really rich database where you have a lot of information and ratings and reviews. And people write comments about it. So if I dig into Kaggle, this is one example of it, whereby entry 1 says one of the other reviewers has mentioned that after watching just da 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 da. Then you actually have the so-called labeling, whether it is positive or negative. So essentially, these data allows you to have the so-called perspective of written text versus the label to go with it. With that, what you can do is you have essentially a supervised machine learning problem. And the question then, of course, for most people would be that how do I actually provide that text into the machine learning algorithm for it to decipher the meaning of those sentences or text or the words? The idea is fairly simple. In NLP, this is essentially a natural language processing problem, although it has been simplified in that some of the pre-processing steps has already been done for you. The word has already been converted into integer, and so you don't actually have to perform that additional step itself. But if you're given in totality just pure text and the label, then what you will have had to do is that you will have to make use of some of the libraries to actually convert the word into unique token. Right, having said all of that, essentially what we're doing here is still what's called a binary classification problem. Of course, the features is slightly different now. The features, we are using the word as our features, and we are using the word as, of course, you can tell from this that this is a really long and a massive matrix, and it's substantial in the size in terms of the features. Of course, the target or the label is still very simple. It's just whether it is positive or negative, 0 or 1. You can read more about the IMDb movie review sentiment classification data set here. It's 25,000 rather than the full 50,000. And let's run the library and import the data. So this is actually from the Tkeras datasets IMDb. We're gonna just limit the so-called training here so that it doesn't run for too long. Just make sure that you do have the GPU and also Python 3 running. We're only looking at 5,000. You can increase that more if you like. We are saying that we are really looking at the maximum number of features of only 5,000. Looking at the data itself, we have 25,000 rows of data. If you look at the actual underlying data itself, the first two entries, what you can see here is that these are all in numeric format, which is what I mentioned before. The words has already been converted to integers, so it's basically a sequence of words. And each integer represents a specific word. And where you have 0 and 1, 0 stands for negative review, 1 stands for positive review. Again, looking at the first two, this will be a positive review. The second entry will be what's called a negative review. Of course, from time to time, you might want to dig in and have a look at the individual word and the actual index to go with it. This is rather long. I'm going to hide it after that. So you can see here, sorted is 18522. Plugin is 52,294. Let me hide that. And of course, you may want to be looking at it the other way, because all you have is the 16 here. You say, okay, what does 16 stand for? Then you can actually look up the value and the corresponding word to go with it. The next step that you might want to do is plug this into pandas and have it sorted in numerical order for quick searching. Right, so we're gonna run there's one more thing that we need to do is that because the features are in the form of integers, what we want to do is hot encode it to a matrix of 0 and 1. And 0 when no such word exists, 1 when the word exists in the data itself. That way we have same length. That's the first thing. And the second thing is that this is a lot more friendly for the algorithm to actually be trained. So essentially this is a helper function. You provide the data and you define the maximum features, which we defined previously is 5,000. So we're gonna basically start off with creating a dimension of 5,000 zeros, a row of 0, and based on the length of data for 25,000, remember correctly. So basically we're creating a matrix of 25,000 by 5,000. 25,000 long rows, 5,000 wide in terms of the features itself. Okay, and we do that for train and test, and we'll do that, and for y we're converting it into a float. Okay, right, the important part, the architecture itself. We have the first layer, it's a dense layer. Okay, our input shape is 5,000. It goes into first layer, which is actually a hidden layer. Of course, the input layer is 5,000 rows, followed by first hidden layer is 16 neurons with activation is ReLU. Second layer of hidden layer is also another ReLU. And finally, the output layer is a sigmoid because we want it either 0 or 1. We're using stochastic gradient descent with loss function being binary cross entropy. Looking at this, let me just reset this. Reset the runtime, yes. And then I'm gonna clear output and start running from the top. Okay. All right, so just touch quick notes here. What are the activation function that we're using here? We have ReLU, as I mentioned before, it's non-linear, so the neural network can learn non-linear feature. It also will be a purely what's called linear or affine in nature, which is not very useful because in the problem that we have is clearly non-linear. So this is looking at the data here. We have the input layer followed by 16 neuron. First hidden layer, second hidden layer is also another 16 neurons, and finally the output is a sigmoid, whether it's a positive or negative review. Splitting the data again to train and validation, fitting the model with 50 epochs, and the batch update is 512. And we'll let that run, and we also provide the validation in terms of the tuple, xval, and yval. Okay, now that the training is done, looking at the accuracy of training around 86 to 88, and the validation is around 85 to 86. Not too bad. Let's look at the performance plot. You notice that the training loss continue to go down. You're starting to see the separation between the validation loss and also the training loss. There are some overfitting going on here now, and looks like our we need to actually work out how to actually solve this problem, either by increasing the amount of data that we have or creating different features. The training and also validation accuracy paint the same picture. Right, just to summarize, we've looked at the application of neural network in this lesson here on non-numeric data, which is text-based data, and basically it came in the form of sentences with the rating or target being positive or negative. That labeling part has to be done by human, of course. The sentences, each word has been converted to a token, and then we convert it into a matrix so that we can feed it into our neural network. And that's pretty much everything that we've covered. Of course, the slight variation now is that we have a slightly more complex neural network with 2 layers. Let me just hide this. Coming back to our architecture, neural network architecture, this is 4. Okay, if you take out the input and output, we have 2 hidden layers for this neural network. And that's all for this lesson. Thank you. Welcome to the course on Introduction to Neural Networks. In this course, let me walk through the guideline and the outline with you. This course, we will cover the introduction to the foundations of deep learning, and in preparation for more advanced courses such as computer vision, recurring neural network, LSTM, and the likes. Now, at the end of this course, the learners, the students, will have a really firm understanding of the basic concepts of neural networks, such as what a neuron is, the architecture of a neural networks, other nomenclature such as layers, nodes, feed-forward networks, backpropagation, and dropout, and many, many more. I really wanted this course to actually help you to set the foundation so that when you actually embark on more advanced neural network architecture, you will be able to understand it. But this is where this course lies, is the foundation to help you to understand really as an entry level to the world of neural networks. Now we will provide many examples from really simple artificial neural networks to topics that was covered in the classical machine learning. I'll highlight them so that you can compare in terms of the performance. The classical machine learning is self-contained, is provided within this course as well, so that you can actually compare and contrast the performance of the 2 different approaches. Now, some of the networks, some of the topics that we are covering will be topics such as neural network architectures, the actual architecture of the neural network itself, the feed-forward networks, backpropagation, dropout, and also comparing and contrasting artificial neural networks versus classical machine learning. With that, I'm going to stop here. Thank you for listening to this introduction. I'm really excited to get started with the first topic, which is what exactly is deep learning. I look forward to seeing you in class next. Welcome back. So what exactly is deep learning? Now, before we embark into the details of deep learning, I want to compare and contrast between the classical programming and also machine learning. Now, machine learning is a bigger space or subset, and deep learning is a smaller subset of machine learning. So the purpose of the next slide, which is this one here, is to help you to understand the difference between what the classical programming versus machine learning is. Now, classical programming quite often requires a couple of things. You need the data, and on top of it, the rules. These are usually rules written by experts. You can understand it as if-then statements. So it could be a very, very long if-then statement, and that's where you actually get the answer being provided to you, the user of the system. Quite often these are called expert systems back in the 80s and even in the early 90s. So basically the idea of classical programming is that as the data come in, the rules provided by human, which is converted into software codes, will provide the answer to the users. Now, machine learning comes from a different paradigm or angle. It requires data, just like classical programming, but it needs not rules, but answers. Answers can come in the form of image, or labels, or target. So the answers provided to the machine learning algorithm as well as the data. Now from there, the machine learning algorithm learned the patterns. It deciphered, it uncovered the patterns, and it generated those rules by itself. Now this is where the human intervention part is not included. The actual understanding and learning part is done by the machine learning, hence the term machine learning algorithm. And that's the foundational idea and the difference between classical programming and machine learning. Classical programming needs constant human intervention as the world that it actually deals with evolves. New rules need to be written. Whereby machine learning, because it's supposed, well, the angle is to generalize. Once it learned, for example, the picture of cats, it ought to be able to actually identify cats, even though it hasn't seen cats before. The image of that or the type of the specific cat before, a specific breed before, it should be able to and ought to be able to pick out that it is a cat. And that's really where the exciting part of the machine learning algorithm comes in, is that it can and continue to evolve because of the generalization that it has learned from previous data. And the other part that's exciting about machine learning is that it can continue to evolve and change and continue to learn as new data come in. Of course, you can have it learning all the time, or learning on once a day, and learning on a monthly basis. So basically those are the flexibility in terms of the production or go live system. But classical programming is not the same. You will not be able to do that. It just won't allow you to actually, well, constantly change. That part requires the human intervention to come in. So that's the real key difference between classical programming and machine learning. Now with that, I'm going to stop in this lesson. In the next lesson, we're going to go into how does machine actually learn? And we're going to talk about this concept called learning representation from data. With that, I'm going to stop here. Thank you once again for watching. Welcome back. In the last lesson, we talked about the difference between classical programming and machine learning. And we talked about the fact that the machine has this portion which it learns from the data without rules being provided to it. So in this lesson, we're going to go into how does the machine learning algorithm actually learn? How does it do the learning itself? So there are three basic ingredients that are needed. The first one is that you do need to provide training data. Now, copious amount of data, lots, in other words. And you also have target or examples of expected output. I mentioned previously cats, it could be dogs, it could be pandas. Basically, the idea here is really it has something to learn towards, a so-called goal that is actually learning towards. A little bit like goal-based learning. So you provide the answer and you provide the raw data, it learns a representation of it. And it's different from human. From the machine learning algorithm point of view, it's just statistical representation, 0 and 1s, in other words. The third ingredient that is needed, or you need to provide, is what's called a performance measurement, a way of measuring to check the accuracy of the model. Now, this performance measurement, or the matrix, provides the feedback to make adjustment. Another word for the adjustment part really is actually the learning part. So you can think of it this way. It's a little bit like, like adults, but most of the time we think of it as young child learn, is that you give them a picture of one and you ask them what this picture represents. If they say 1, they got it right. Okay, if they say 2, then they've got it wrong. Then you correct them and say the answer to that actually is 1. They'll learn to actually correct themselves. So what have you done? What you have done is that you provide some training data. Of course, you initially train them on the examples of digits 1 to 10, and then you give them the answer as you were teaching them, 1, 2, 3, all the way to 10. And after that, a way to measure the performance. Of course, in the measure of performance is slightly different in the machine learning world, is that it uses specific algorithm to tell or inform the software or the script that it is correct or incorrect. But in the human world, the parents or the teacher will inform the child whether it is correct or incorrect based on the understanding and the knowledge of the teacher. So this feedback loops allow the learner to continue to learn, and that's the key part of the ingredients that's needed to provide to any machine learning algorithm to learn from the data. Now this is from Cholet. Cholet is actually a Google researcher. He's the creator of a deep learning library called Keras, hugely popular, second most popular after TensorFlow. TensorFlow is provided or open source by Google, and of course his employer. And Keras is another deep learning architecture, or you can call it library if you like, or toolkit for you to actually write algorithm to conduct deep learning. Now this is what it states: a machine learning model transforms its input data into meaningful outputs, a process that is learned from exposure to known examples of inputs and outputs. Therefore, the central problem in machine learning and deep learning is to meaningfully transform data. In other words, to learn useful representations of the input data at hand, representations that get us closer to the expected output. So the idea really is that you are learning from the data input and also the output, and continuously learn from the mistakes until you can generalize with examples that you have not seen before. Right, let me give you some example of what it looks like to look at representations. I'm going to give you two examples. One example is one of regression, and another example is one of classification. Regression, for some of you, you would have been exposed to it in either high school or A-level or universities undergraduate courses. It is popular, it's frequently covered in graduate courses. And when you're working with regression, you are basically working with numerical data. Whereas if you are dealing with classical classification problems, you are dealing with categorical. It could be binary, 0 and 1, yes or no, or categorical, it could be in the forms of different country names, UK, US, China, Japan. That's categorical. It's not continuous in the form of a real number. Other example, categorical, it could be the letters A, B, C, D, all the way to Z. So in that situation, you have 26 categories. So let's look at the example of regression. Now, if you just ignore that line for now, if you are given a data that looks like this, basically a whole bunch of dots, you are asked to use X to predict Y. The question is, how would you do that? Now, if you look at it without that line there, you probably will have a general heuristic understanding or an appreciation that as the value X goes up, the value Y goes up. Now, whereby in the situation of regression, the line of best fit, which is that solid blue line there, is drawn to represent the underlying relationship between X and Y. Now, it's not going to be perfect. The reason it's not going to be perfect is because, number one, there's a lot of noise. So that's why there is actually a line there. This is what's called linear regression. And if you remove all the dots, if you are given any number or a sample of X, it could be also new data, then it will be able to predict what Y is with some certain level of confidence. Fairly accurate because that line is the line of best fit. It is learned by using what's called sums of squares of errors. For now, we don't need to dwell too into that. The basic idea is that it's trying to minimize the errors. So you can just quickly, very quickly appreciate and understand that that line is a line of best fit. It is drawn there because it minimizes the errors relative to all the other lines that you can draw. Right, so that's really an example of representations. In this case, this is linear regression. So what about an example of classification? Now, this is an example of deep learning. CNN here stands for convolutional neural network, which is a really fancy term in the real world, and the layman term is actually computer vision, how the computer sees the world. Now, specifically this picture, it's a layer 5. Okay, I know that we haven't talked about what layers are. For now, just take my word for it. This is how the computer sees the world in layer 5 of the deep learning neural network or deep neural network. You can see that it's just patterns. You can't exactly decipher what it is, but that's basically how the computer deciphers the world and how it deciphers the actual imageries that is actually presented to it to learn. You can just imagine that if there are many layers involved here, it's basically learning layer upon layers, different representation of the world. The first layer could be just straight lines, corners. The next could be diagonals lines. And the third layer could be circle. The fourth and fifth and on start to actually decipher and learn more complex structures and patterns such as waves. As you can see here, there are a whole lot of there are no words to describe this pattern. Some of them looks like feathers, some of them look like the picture of the ocean, some of them just looks like petty few. So there's really a lot of representation. There's no way to tell what these are, but this is an example of the features that it extracted and a representation of the world. So for now, I'm gonna stop here. So in this lesson, what you've learned really is how this computer sees the world. It's an example of learning representations from data. Not that we're going to be able to understand it from a human perspective, but this is how it helps the computer to actually make sense of the world. Whereas the picture before is for regression, for this computer vision, it's a little bit more complicated. but the purpose ultimately at the end of the day is for us, from the perspective of this lesson, is to understand that computer sees it from statistical representation patterns. Okay, with that I'm going to stop. The next lesson we're going to go into what is deep learning and look at a little bit of the structure of what does it mean by deep learning. Thank you once again. Welcome back, everyone. So let's dig into what exactly is a deep learning. So in this segment, we're going to talk about the architecture of deep learning and what does it actually look like. Now, some basic fundamentals. It is not deep in the sense of knowledge. The deep here actually refers to the depth of layers. Each layer is learned, basically each layer learned a specific representation of the data. Now, I appreciate that the picture that I'm showing here, it's a little bit not clear. And if you look at it, this is the AlexNet. It's a computer vision deep learning neural network architecture. Let me just walk through the network with you. If you have a look at this, we start from the left side. From this side, this is where the input image comes in. Okay, and followed by, this is one layer, and these are the so-called dimension of the layer, 55 by 55. Don't be too concerned with that for now. And then followed by another layer, and then another layer, by another layer, followed by another layer, and then the last few layers are called the dense layer, fully connected dense layer. So don't be too concerned with those, just understand it as this. You have the input data, and then you have the output in terms of what the target is. And in between, what you have is a whole lot of neural networks that actually learn, each layer learn a specific presentation or representation. I mentioned before, this is layer number 5, and if it's first layer, then will be most likely will be straight edges. It will be the right line or the left line, and then the horizontal could be the second layer, and then third layer could be the circle, and on it goes. So that's specifically what each layer learned. And each of these layers, the depth of the layer actually provides the capacity for the network to learn more. I guess if you think of it in statistics term, it's called degrees of freedom. If you think of it as a straightforward equation, then instead of y is equal to mx plus c, which is one x there, one variable there, what you have here is many x, as an example. Not exactly the same, but just as an example to give you an idea of what each of these are. Now, I appreciate that this is probably still very raw and in terms of your understanding, but look at this as the architecture for now. I'm going to show you another one right now. This is another computer vision layer. It's called VGG16. This is an example of, again, another neural network architecture. Specifically, this is for, again, for convolutional neural network. If you look at this, what you have is that you have the input layer where the raw data is being fed in, and what you have then is actually for block 1. Block 1 has a convolution layer 1, second convolution layer, and then a pool layer. So this layer here consists of three, I guess, layer you can call it. This block consists of 3 layers. And then this is followed by another block which has 2 convolutional layer and a max pooling. And then followed by block 3 and block 4 and then block 5 and on it goes. What is not shown here are the last 3 layers of fully connected dense layer. This may not be 3 layers of fully connected dense layer, but the basic idea is that before the output there must be fully connected layer to actually finish off the so-called neural network. And that's really what I wanted to show you in terms of the deep learning part of it. This is the architecture of what a deep learning neural network looks like. and I hope that it gives you at least, if you haven't seen it before, this is just a start of what it looks like. I hope that it helps you to actually at least have a better grasp of it. Now let me illustrate a little bit more of the architecture of what a neural network looks like. And quite often this is a toy example whereby of the architect of what a neural network looks like. And it's not too different from the real world, whereby what I've shown you earlier is a much more complex and more state-of-the-art, in fact this is probably about 3 years old now, state-of-the-art neural network, but in its infancy this is what a representation of what a neural network looks like. So you have the input, these are your input, it could be in the form of your raw data, sample data, and what it is that it's being fed into what's called an input layer. So these are the 3 layers that's actually facing the world. So you have these 3 layers, and notice that each of these are connected to the next layer. And these 1, 2, 3 layers here are called the hidden layers. These layers are hidden, it doesn't actually interact with the outside world. I guess you can actually say that. The data is actually being fed directly into the input layers. Now when you look at this, it kind of reminds you of our brain. In fact, the idea of neural network is that it is inspired from biology or from our brain or brain cells. Now, if you look at it again, this is the input features or the feature vector. If you're looking at lots of data that's coming in, also called features, it goes through the input layer, which directly feed into 3 hidden layers before it comes to the output layers. And finally, the output is the predictions that it actually that the neural network will actually generate for you. And that's generally the basic idea. The basic idea of what a neural network is. So let me actually illustrate a little bit more. I think it's worthwhile to spend a little bit of time to understand how a neural network actually works. So let me start with the bottom one, which is directly from, let me just pull that up. Okay, directly from Stanford. These are Stanford class on convolutional neural networks for visual recognition or computer vision that I mentioned earlier. If you look at this, this is what I wanted to show you. And what they have very kindly and nicely shown here is the filter, which is also the layer itself. This is the second layer. If you look at it, this is actually from AlexNet. And you can see that it actually is, well, you have the edges, it's kind of like horizontal or vertical, and it's fairly smooth. All right, so let's look at the next one. And we're going to go into this 2D convolutional network visualizations by Adam Harley. And this is really quite something else. Okay, let's wait for this to run. Now what he's done here is that this is a 2-layer neural network, and it's asking you to draw the number here. So let's just draw this, and I'm going to draw a 4. Okay, right, what do you see here? What you can see here is that this is the input. This is the next layer. All right, it feeds into this next layer, and it actually, each and every one of these tells you what is actually going on and how it actually, each of these pixels relate to which part. And it shows you, okay, from here, notice that it links to that layer, and notice these are the edges, and it goes on and on. Finally, it becomes a single layer, and then this is the fully connected layer, and finally the prediction is 4. And notice that this is quite remarkable, and of course from the perspective of from a person who's learning, this is quite remarkable because it's really easy to understand. You can actually show the input layer or hide it. You can look at the convolutional layer 1 and hide it. And this is the downsample, which is also what's called max pooling. And then there's layer 2, and this is the downsample, also called max pool. And then we have the fully connected layer 1, fully connected layer 2, and finally this is the output itself. And I think I really encourage you to play with it. It really helps to develop a lot of intuition and to see how how it actually works. From the picture that I showed you earlier, this input layer has 3 nodes, whereas for this you can see that it has 1, 2, 3, 4, 5, 6 nodes. Okay, and from there to the next pool layer it has 1 to 1. But going to the next one, it actually comes from multiple sources, okay, as you can actually see here. Right, let's look at the next. And I also want to encourage you to play with this tensor playground that's provided for by Google. Okay, so if you look at this, there are a few things. Now let's start with something extremely simple, such as this. So it's a bit on the small side. So let's just start with, okay, no hidden layer. Okay, so in this case, it can actually separate out. Let me, yep, we have 0. Okay, we have 2 features. Okay, you notice that it's a straight line. It's a vertical straight line for this, and this is a horizontal straight line. And you can see that the neural network was able to actually learn the segregation line separating the orange from the blue. So let's just train this. We haven't trained it, it was just randomly generated. Let's just train this. Okay, and after a few hundred epochs is basically means that it actually sees all of the data. Okay, it sees all of the data how many times. So now it has in the data 700 times. So let's just pause it. Okay, and you can see that the learning rate is 0.03 using this activation function called tangent H. And if you look at the test loss and the training loss, there's absolutely none whatsoever. If you think about loss as errors, then you can understand that, hey, what we have is a scenario whereby this model, basically we have 2 features here, x1 and x2, is able to actually predict the 2 classes of blobs or clusters very easily, the blue one from the orange one. Okay, so you can see that actually, well, learned that really well. Okay, let's move on to regenerate another example. Okay, they're all in that same. So let me add a lot of noise. Yeah, like that. Regenerate. Okay, and restart the training again. Notice that again, it's quickly learning. The test loss is down to 0. The training loss is pretty low as well. And again, let's pause this. It quickly learns the pattern and it finds the best line to actually segregate the 2 classes. Right. Now you say, okay, that's straightforward, it's a simple pattern, it should be able to pick that up. So let's have a look at this. Now we have 4. Okay, you can't possibly draw a straight line to separate out the blue one from the orange one, because no matter, just convince yourself, no matter how you draw one line, you are not going to be able to segregate the 2. So is 2 features enough? Let's run our machine learning model and notice that it's not getting any lower. It is just struggling, and the losses are really high at 0.5 and 0.5 for both the test and train. Okay, this is not working. Just basically having 2 features, one vertical one, one horizontal one, is not working. So let's just add one more, x to the power 2, and run this and see. Is it working? No. Okay, again, it's not working. Let's add another feature, x to the power 2. Okay, it's trying very, very hard. This is part of the thing that I really want to encourage you to do. Try this. Play around with it to see if you can actually get an intuition and understanding all of this. So again, not working very well. Let's add another features, x1, x2. Hey, this is looking better. They're looking much, much better. And notice that the losses are now down to 1%. Okay, so all right, so these are the traditional way of what's called feature engineering. Now, via feature engineering, providing different kind of features, it's able to actually predict the data. So far, what we've done is nothing deep about this. It's just very one layer of predictor. There's nothing deep about this. So let's move on to something like this, circle. Okay, we have all of these. Let's see if it actually can learn. Right, seems like it's actually very quickly be able to learn that pattern pretty well, which is really good because we have 5 features. It seems to be able to do that. Now, what if I add a hidden layer? Okay, just 2 neurons to see if it actually can improve that. Remember, the lowest earlier was 0.05. Okay, and it seems to, well, hasn't done that well. Okay, it seems to getting lower, might need more. Okay, maybe we'll add a few more hidden layer to see if it actually can learn the pattern better. And with that, you can see that it's starting to drop. Let's see how it actually improves. It's not much better than before. So what we do is that maybe we'll add 2 hidden layer and add 3 neurons, 5 neurons for it and see what happens. Okay, now you can see that it actually is starting to drop. It seems to have a better capacity to learn. Still though, the test loss is actually a little bit on the high side. In fact, it's actually climbing now, the more that we train. Okay, so let's just do this. And so, and again, this is the part that I want to highlight. This is the art part of neural network and deep learning. You do have to play around with it. It's not straightforward science here. There's a bit of tinkering, play around with it to see if it actually works really well. And you might have to stop at some point to stop it from continue to learn because it seems to start to overfit now. Okay, and it doesn't seem to do so well in this. So maybe we actually try ReLU, and we'll try it is classification. Okay, we're going to leave that one out and let's try this. Okay, so once I change ReLU, the test loss and the training loss drop immediately. Okay, it was hovering around 8% earlier, it drops immediately and now actually starting to climb again. So we're starting to go into the overlearn territory. So final pattern is this. I know that as you watch me play around with this, it looks really exciting, but trust me in this, it's much more fun as you play with it than me playing with it. You will actually get the intuition much faster by playing with it yourself. So if with this, it's really, well, it seems to be improving, but it seems to also struggle. So we're going to add a few more layers to help it along. Okay, let's see if this many layers can actually help. Okay, so let's see. So it might take a while. Yep, that's right. There we go. It's learning the pattern. Okay, the test loss has dropped down to 5%. Now is 4%. It's continuing to learn. Okay, but I think by now you probably get the gist of what I'm trying to actually convey here. You do need to actually, well, a couple of things that we've done. Let's summarize. We have the input data. We have the features, we have the many layers, these are the hidden layers, and finally we have the output layer. And there is the learning rate, which we'll cover in later lectures, activation, we didn't use this regularization, we talk about that this is classification. But again, I want to stress that please spend some time to learn this, and I'm going to pause this because it's probably getting a bit of a distraction for you. Now these are the few things that I wanted to highlight and want to actually demo to you. There are ready tools out there for you to help you to develop the intuition. And really that is what deep learning is about. I've shown you what AlexNet looks like. This is the VGG16, which is 16 layers. And this is what a neural network looks like. And finally, we stop with the neural network visualization. I hope that has been useful, but don't just listen to me talking. Go and play with it. You can't break it. All of these, I have the link provided for you. This was the best way for you to develop intuition. Thank you once again for watching. I look forward to seeing you in the next video. Welcome back. Well, in this lesson, we're going to look at what we've learned so far and look at how does the neural networks get trained. Now, the key thing that we cover so far is that machine learning is really having an input as well as a target and the actual algorithm itself learned the so-called patterns and the statistical representations that link the input to the target. Now the key thing is about finding the question marks here to link the inputs to targets. In order for the algorithm to learn, neural network to learn this, you do need to provide many examples in order to to allow it to learn the patterns. From the previous slides, we can see that there are many layers to deep learning neural network. Now, these layers learn the relationship between the input and target from being exposed to many examples. Hence, the picture there illustrate. Now, the question that naturally arose or arise is that how does the algorithm learn? We covered this, but I just want to show you another different picture. Now, we've looked at this from a slightly different perspective. We've seen it from inputs, and we also look at it from outputs. In this case, we call it predictions. Now, in between are the layers that we discovered or we explored earlier. The difference now is that there are these two elements here. These two elements are what determines the so-called the learned contents of the neural network. We will go into a little bit more of these in depth a little later. But for now, just understand that these are basically the actual input with the weights and in order to get the actual so-called predicted output. Now, this is what is also called feed forward. Let me just highlight it this way. And I'm going to give you an example as an illustration. All right, let's just have a pen and we use blue. Let's just say we have an output of 1.2. Okay, so that's the target output. Now, and let's make our life a little bit easier. The input, let's just say, is 0.2. And let's just say the so-called weight that is given here along this level or this layer is 0.1, and for this is 0.2. Okay, assuming that when we are looking at these neural network layer, the so-called provided input here is, let's just say, if we look at a simple example of, let's just say, choose a pen here. Okay, the input is 0.2, and then we have a weight of, let's just say, 1 to begin with. So when you multiply the two together, what you get is 0.2. And let's just say you have another weights here. The output here is 0.2. Let's just say we don't actually have an activation layer, so ignore what I just said in terms of the details. We don't have this level. Let's just say it's 0.2 straightforward. So the 0.2 get fed forward. So 2 times 1.2, 2 times 0.2 gives you 1.2. And let's just say the so-called the actual value that we are looking and aiming for is, let's just assume that is actually 2.0. So this is the actual value. So right now, based on the weights of 1 and 2 here, let's just call this weights of 1, and the weights of 2 is 0.2. How then do we get the neural network to learn so that it actually achieves this 0.2? Now we know that the input is fixed. This value is determined by the weight, as is this value is determined by the weight. So the key difference now really comes down to the actual weights itself. Indeed, for neural network, the weights are the actual memory of the neural network. They are the key for what is being learned by the neural networks. Just as the picture that we saw earlier in terms of the filters, the different filters, let me go back. These pictures, these are the weights, the actual weights that's learned by the neural network layer. The difference is that we, instead of scalar value, which is like what we given here, 0.2 and 1.0, what we see here is a matrix of numbers which, when you look at it, seems to have a pattern. Well, that part of it is because our eyes are always looking for pattern. So let's come back here. Now the question is that how do we actually get the neural network to learn such that it will eventually achieve a good accuracy? And that's where I'd like to introduce you to this picture here. The picture that you saw earlier are these portions. Okay, so you looked at this portion so far. You have the input, come to the neural network layer and the weights to it, and then another neural network layer, and then multiply the weights and gives you the prediction. On this side, we have the actual Y, and on this side, you have the prediction. Of course, unless you are lucky, it's not very likely that the first time around when the neural network see the data, it's going to be able to predict exactly. So there will always be some difference. And this is where I like to introduce to you what is called a loss function, which measure the difference between actual and predictions. And this is what is called, the loss function measure the actual difference, and the score is the output. Now, as in terms of the score is concerned, it tells you what your errors are, meaning how far away is your model from providing a good prediction. That still doesn't solve our problem of how to actually improve the model, and that's where the optimizer comes in. The optimizer is the algorithm that actually feedback to change the weights for all of the weights in each of the layers. So that ended up closing the whole loop by itself. So you have this portion here is called feed forward. Okay, FEED, FORD, FORWARD. So feed forward. So this part is the feed forward in terms of the providing the data and the actual prediction. Now the portion whereby it goes back to actually improve using the optimizer is called the back propagation. Okay, and in order for it to continuously improve, you need the error function or loss function to measure the error, and this is the actual value. Loss score is the actual value and tells you the distance between your actual value and also the prediction. So that's basically how a neural network learns. And it's actually very mathematical in that sense. We will actually go through an example. That example will make use of quite a fair bit of math. If you want to skip that, that's fine. But in terms of the application of it, you don't really need to understand the actual math of it. But the math part I will provide nevertheless, just so that for those who are curious, who wants to learn how the actual number actually works. Right, so the last slide that I want to cover in this lesson really is shallow versus deep learning. Shallow learning is the classical machine learning, such as your linear regression, your logistic regression, even your support vector machine, and also decision trees. Those are all shallow machine learning. It's what we call, the way that it learns is it learns greedily, meaning in successive manner. It's stacked. Now, if you stacked all of the shallow machine learning algorithm, you may think that it will actually achieve the same as how a neural network will perform, because it does seem like that if you stack them, let me just come back here. If you stack them, it looks like that it will look like a normal neural network. But the truth is that it's not the same, because stacking multiple shallow learning together will not achieve the same result. The reason being, the shallow machine learning learn independent from each other. Even if you stack them in successive layers, they will learn on their own. Whereby deep learning, the layers learn the patterns jointly. Okay, so that means they can actually learn much more complex structure and patterns from the underlying data itself. Then lies the difference between shallow machine learning and deep learning. With that, I'm going to stop here. In this lesson, basically what we have covered really is we review what we've covered. We looked at how a neural network works, the feed forward, the measurement of the loss or the errors, and also using Optimizer to continuously improve the learning, improve the machine learning algorithm and the accuracy of it, tuning the weight so that it becomes more and more accurate. And that's the basic idea of how a neural network actually learns. And once again, thank you for watching this video. I look forward to seeing you in the future one. Welcome back. In this session, we're going to look at why now, what's changed, what has actually transpired that led to the renaissance of AI. It's gone through 2 winters, and this latest wave are led by a few factors. Number one is the computational power. Now, the main one is GPU. The cost of training this neural network has come down extensively, especially over the last decade and a half. That's because of the advent of GPU, which allows parallel processing, and that really lent itself really well to deep learning. And the costs, of course, have come down substantially. And the next one is data. Now, I'm sure you've heard of big data, the terms big data. A big part of it is because of the internet. Another part of it is because of the availability of video data. And the other third factor really is mobile. Your mobile phone, which you actually walk around with on a daily basis, that you access your email, send your messages, load up your pictures, taking pictures, so those are the many things that you interact with that allows the proliferation and explosion of data. And all those data provides the actual data that neural network need to become more and more accurate. There are other factors too, such as advances in algorithms such as activation functions, weight initialization schemes, as well as optimization schemes. Now, these will all cover when you come back after you finish this course. You will be able to understand these really well. And finally, of course, because of the success of AI, there are more and more money pouring into this space. And that's really why that we have a renaissance in terms of AI. And once it catches on, it's a positive loop because of the amount of money that's invested into it. There are more use cases, people get more excited, and on goes the loop again and again. Alright, so that's really part of the reason why. A really quick snapshot. If you Google around, you will see a lot more reasons and a lot more in-depth explanation of it. I just want to give you a flavor of this so that you can understand what's changed. Why is it that suddenly it's so popular now? Alright, I'll see you in the next video. Hey, welcome back. In this lesson, we're going to start looking at some of the building blocks of neural networks. Now, some of the key foundation that you do need to know in order to really grasp the concepts is linear algebra. That's the first one. Second one is probability, as well as information theory. And you do need to actually have a fairly good grasp of numerical computation, as well as literacy. Now, the so-called codes that I showed you in the last lesson, it requires a certain level of thinking, of course, but if you study it carefully and if you actually study it diligently, you'll find that the actual sequence and the actual approach it's okay. You can actually come to an understanding of it without much problem. For some of you, you will be able to pick up very easily. It's just a second nature to you. It may be because you have developed that skills over the years. For some of you, don't lose heart. It just, you will still be able to get hold of it. Just need to give it a bit more chance and give yourself a bit more chance as well. Just to revise a little bit what we actually covered in the last example and the code walkthrough, we looked at the MNIST dataset. And the steps that we covered pretty much is the actual standard steps for all neural network and the training of any models. The first thing is loading the data. The second one will be defining your neural network architecture before you compile it with the selection of your optimizer as well as your loss function. In the last one, what we did use is RMSProp, which I did not explain what it is. It's okay, we will explain that in a later future lesson, as well as the loss function. The loss function is cross entropy that we use. Cross entropy is for multi-class. In our case, we have 0, 1, 2, 3, 4, all the way to 9, so we have 10 classes. That is what you will use, which is cross entropy. If it's binary, then you use binary, okay, the loss function. And after that, we do need to compile it. That's the compilation part, which I just explained. And before we feed our data through, we do need to actually pre-process and prepare the data so that it actually makes it more amenable for the training of the neural network. What we did in the previous lesson to actually is to convert all our data into, or squeeze it to between 0 and 1. It actually speeds up the training and you don't actually have errors drawing everywhere. The next thing is that we do need to prepare our label or targets to ensure that it is appropriately labeled, because when it comes to the machine learning, again, it doesn't work well with tags or strings. You do have to convert it to integers, ideally in one-hot encoding format. And the second last thing is to actually train the model to an acceptable accuracy level before continue on. Once you're actually happy with it, then you actually move on to the actual prediction. Now, this process that I've just described here is not a one-off process. It's one that you do need to actually continuously train your data as new data comes in. You do need to train your model because it's one of those things when it comes to machine learning algorithm is that it does go through decay or newer so-called algorithm, better algorithm comes along that you do need to improve it. And also sometimes if you're working with financial data, the taste and the preferences of your customers may change. So those are the things that it's a broader issue to think about and to consider, one that you do need to train your neural network on a continuous basis so that it actually stay relevant. Alright, so that's really what I want to cover. When we come back, we're going to go into a little bit more about the actual tensor itself, which is a description that we use to describe the data. And with that, I'm going to stop, and thank you once again for watching this. Welcome back. In this portion, we're going to go into what exactly is a tensor. We need to actually walk through this because this is fundamentals to what we do need to know. We're going to look at a few key concepts and build some foundations before we proceed further. We've looked at what the neural network, the training of it looks like in our last lesson as well as in previous lessons. Let's build some foundation before we start running. So what exactly is a tensor? I've given you some examples here. These are all tensors. Okay. Now, some describe it as a container for data. Some describe it as basically a form of representing data. The other way to think of it is that it is a form of data type. Much like integer is a data type, array is a data type. Tensor is actually a container or a data type that actually, by and large, most of the time is actually just numerical data. You may be familiar with matrix, such as a 2x2 matrix. That is actually a tensor. So let me walk through some example of the different various type of tensors. A tensor with or zero-dimension tensor is actually called a scalar. In the mathematical world, a scalar basically is one number. Here is an example. 3 is a scalar, which is also a zero-dimension tensor. And if we're talking about vectors, It's a one-dimension tensor, and here's an example of a tensor 3, 6. So that's actually a tensor as well, except that is one dimension. In mathematics, we call this a vector. What about matrix? In the world of matrix, it could be 2 by 2, it could be 3 by 3, it could be 3 by 5. That would be what's called a two-dimensional tensors. And this shapes has the first column is called number of samples, followed by the features. And the next one, it's the time series data. As an example, this would be a 3D or three-dimensional tensor. It doesn't really have a mathematical name to go with it. We just call it 3D. And with this, there's samples, there's time steps, followed by features. And for four-dimensional tensors, it can come in two forms, and these are typically images. It can come in, usually the first one is always samples, followed by height, width, and channels. Occasionally, however, it can be channels, height, and width. We'll get to that a little bit more when we're talking about convolutional neural network. For now, just understand that this exists. And the 5D tensors will be a video. An example will be a video whereby you have the number of samples followed by the frames, okay, the individual frames itself, followed by either height width channel or channel height width. Okay, so that's pretty much the example of what's called a tensor. And basically, really, as I mentioned, is actually a data container, and by and large, most of the time is actually numerical data. Right, so that's really what I wanted to cover. When we come back, I'm going to start illustrating some of these in a notebook so that you can actually relate this to what it looks like when you are working it in Python. Welcome back, everyone. We're going to go through a couple of key attributes as well as some key ideas and concepts of neural network before we proceed to look at the codes itself. So the first thing that I want to cover is the key attributes of tensors. We talked about their different dimension, the different types of dimensions of tensors. There's from 0 dimension, 1 dimension, all the way to 5 dimension or more, depending on the type of data that you're working with. With Python, there is a Python NumPy library. There is a function called ndim. This calculates the number of axes for you. Now, three-dimension tensors has 3 axes, okay, also called rank in mathematics. And there is shape, which is the number of dimensions the tensor along each axis. For an example, if we're looking at a 2-dimension vector, the ndim will tell you that there is actually 2 dimensions. So that tells you that this is a 2D tensors. But what we don't know is that how many so-called, what is the actual shape itself? Is it 1 by 1 or is it 2 by 2? So that's where in NumPy you use dot shape, which tells you in this case is 4 by 9. Another example, a 3-dimension tensor here, the ndim will tell you is a 3D, but again, this is what you don't know. Is it 1 by 1 by 1, 2 by 2 by 4? So that's where the dot shape would tell you that this is indeed a 3 by 3 by 4. Now you probably will vaguely recall that in the MNIST dataset that we were looking at, the training data is 60,000 followed by 28 and 28. So, and also the test data will be 10,000 followed by 28 and 28. So it's actually a 3-dimensional tensor, okay, or 3D tensors. All right, the third thing that I want to cover is the data type, the type of data that is stored in the actual tensor container. You use the D-type in Python. It could be a float 32, it could be a float 64, or unsigned integer of 8-bit. All right, so those are the key attributes. We're going to revisit this using codes a bit later. And the next concept I do want to cover is data batches. Now, Earlier, you probably would have seen that when we were looking at the code, the data batch that we used was 256. Let me just have a quick look. Data batch, where are you? There you go. The batch size is 256. Now, when you're building your data learning models, you don't usually process the entire data set at once. When you look through one entire data set one time, it's called one epoch. The data are usually broken up into small batches, hence the term batch. And how big is the batch will be called batch size. The batch size that we specify in our earlier motivational example is 256, meaning we took 256 sample. Okay, there are some other terminology that I do want to cover. Is that epoch. One epoch basically means all the data. A batch will be a subset of the data. A batch of 128 in Python code will be an example that looks like this. This is from the first all the way to 128. So you're looking at the first 128 batch. Okay, that's the first batch. The second batch will be from 128 to 256, and the next batch, if you want to continue on, is 128 times n. N could be 1, could be 0, could be 2, all the way, and the column here basically specify this is from where until where. That's basically how you specify it in Python NumPy code. And the last thing that I want to cover is to revisit some of the tensor operations, basically algebra, in Python. These are the key concepts that we will be illustrating using Python codes. We will look at element-wise operations, broadcasting, dot product, which is matrix multiplication, and finally reshaping. So let's look at that. We'll start with tensor operations examples. So I already mentioned these are the four things we're going to look at: element-wise operations, broadcasting, dot product, as well as reshaping. Okay, so let's start looking at our first example, element-wise operations. Element-wise operation basically means that one element, whatever operation, to another element. Okay, so that's a little bit like you are doing all the calculations all at the same time, but independently based on the individual index itself. So that's a little bit abstract, so let's have a look at this. So now we have x1 and x2. We're performing element-wise operations here. x1 plus x2. This is 2 plus 1. This is 2 plus minus 1, and 4 plus 3. So that's the actual element-wise operations that you are doing here. It's not a multiplication, it's not a complete addition. This is another example of element-wise operations whereby we are calculating the maximum between x1 or 0. Okay, so when we run that, you'll notice that the maximum is x1, is this one here. Okay, so it's actually an operation between 0 and individual elements of x1. 2 is greater than 0, so 2 is taken as the value. 0 is larger than minus 1, so hence 0 is taken as the value. 4 is larger than 0, hence 4 is the value that's being retained. So hence this is what's called an element-wise operation. So that's really what element-wise operations means. It's actually the individual operations. Later on, when we actually look at dot product, it's a contrast to what element-wise operation looks like. If you are familiar with matrix, then you know that this is not the same, completely and very different altogether. So let's look at broadcasting. Now, broadcasting is, recall the x1, it has 3 elements. Okay, so it's a vector, it's one dimension. Now, how do you add a scalar to a vector? This way broadcasting comes in. The small tensor will be broadcasted to match the shape of the larger tensor. The x1 matrix is basically 3. It has 3 elements. 2 is only one one element. So basically that the 2 will be repeated 3 times or broadcasted to all the individual elements itself. So let me illustrate. So what happened here is that 2 will be added to 2, 2 will be added to -1, which gives you 1, 2 will be added to 4, which gives you 6. So the broadcasting of scalar, the scalar value 2 or 0d to the vector itself, the 1d vector. And hence this is what it looks like. We're gonna create x3, so this is another array that we're creating. If we repeat again, adding 2 to a 2 by 2 matrix, notice that this is a 2D, two-dimension tensor now. What do you think will happen? Have a guess. Yes, you'll be right. It actually adds 2 is broadcasted to every single element, and then the actual operation or addition in this case is performed. Okay, right, let's look at x4, which is what we're creating here. So -1 and -1 and x3 looks like this. How do you think, well, how would it behave, x3 plus x4? Again, pause for a moment, have a think. Don't peek. All right, let me show you. Basically, it's broadcasted to the 2 dimensions. So basically this first, then followed by this. So it's 1 minus 1 gives you 0, 1 minus 1 gives you 0, 2 minus 1 gives you 1, 2 minus 1 gives you 1. So that's how it is broadcasted. There's a limit to this, especially if the shape doesn't match. What we have is that scalar is easy to broadcast to in fact, any dimension for that matter. When you have more vectors to vectors or vector to matrix or vector to 4D, it starts to get complicated, especially if it's odd size. Then NumPy, when it can't actually figure out what you're trying to do, it will show you an error. Okay, so time to actually have a look at dot product. You're probably more familiar with another term, which is matrix multiplication. That essentially is what dot product is. So let me show you, well, let's start with x1 first. We skip ahead. Right, so if you take a simple dot product, NumPy dot, and if I do x1 with x1, do you think that will work? Go back to your earlier days when you were looking at matrix. If you have a 3 by 1 multiplied by 3 by 1 in matrix, would that work? You're right, it won't. Well, in this case, fortunately for you, it actually works. But in reality, it should not work. But because this is a simple case, NumPy is smart enough to figure it out. Technically, you're supposed to transpose this, okay? Then it works. As a good practice, make sure that you are actually working with within the rules of matrix, so that you don't actually have any weird numbers or unexpected result being thrown out. Okay, so let's look at x3 and x4. These are 2 different ones. Okay, now the good thing is that x3 is even 2 by 2, so it's easy to actually work that one out. And when you actually look at dot multiplication here, which is a matrix multiplication here, we transpose x4, and we are able to actually get the result. So again, let's have a look to see if NumPy is smart enough to figure it out if we don't actually transpose the data. Okay, so it's smart enough to figure that out. So that's good. Well, good thing that it's able to figure that out. But don't assume that it will work just fine for matrix that's more complex. These are simple matrix, so a good thing, in that situation, it's not bad that it works out well. Right, let's have a look at, I feel obliged to actually demonstrate to you. x5, okay, so NumPy array. Okay, let's see what kind of example we can use here. We'll just use this, except that I'm gonna change it to, this is a 2 by 2 matrix. 4, 4, 4, 5. Okay, x6 numpy array. Now we have 3 by 2, so let's create a 2 by 3. Okay, so 1, 2, 3. We need to open up one of these, followed by 3, 2, 2, 1. Well, that will do. And we need to close that off. Okay, so numpy. So let's do this. X5 shape, X6 shape. Okay, notice that it's 3 by 2 and 2 by 3. So numpy dot, and if we take X5 and X6, and it creates a matrix that is 3 by 3. Okay, which is exactly what you expect, because when you actually have dot multiplication, it takes the external dimension. So if we do this, I'm gonna wonder if this is gonna throw an error. It should, but let's just see. Okay, all right, good. Finally was able to prove this. Okay, I was expecting it to, but it was smart enough to actually deduce it from your data, but I think that actually come at the expense of slowing down, but nevertheless. So someone who has spent some time writing the assert code at the back. So here it says shapes 3 by 2, and 3 by 2 is not aligned, because when you're actually doing matrix multiplication, I really hope that you do remember your linear algebra. If not, please do revise. This is just a really quick run through of how to actually perform matrix multiplications in NumPy and Python, rather than going through from step 1. So you have 2 and 3 does not align. So when it comes to multiplication, matrix multiplication, the inner dimension must match, and the outer dimension is actually the final shape of our matrix. Okay. Right, so that's really what I wanted to highlight. Okay, so the last one, let me just tidy these. The last topic that I want to cover is reshaping. Let's bring up X3. This is what X3 looks like. If we perform -1 to 1 and print it out, notice that it turns it into a columnar format. Okay, it's now 4 rows by 1. So if we do it the other way, 1 minus 1, when we reshaped it, okay, it converted from a 2 by 2 to become a row matrix. Okay, so notice that this is 4 by 1, this is 1 by 4. Okay, so X3, if we reshaped it to 1 by 4, we're going to get the same result as that. And notice that you can actually define it that way. If we do it this way, it will exactly be the same, because we didn't specify the next one. And you can also perform Revel. Revel does exactly the same as well, so I'll turn it into a row wise. Okay, and that's really the whole basic idea of reshape. Essentially, the reshape is actually specifying the final shape that you would like it to be, and that's the function reshape, and it's useful for the purpose of tensor operation. Right, with that, there's quite a lot to cover. I really hope that you got much out of that, and these are the concepts that we wanted to cover. Very briefly, albeit, we cover element-wise operations, broadcasting, dot product, as well as reshaping. I hope that has been useful. There's just one more concept, one more thing that I want to cover. I think I owe you this, which is the endim and also shape. So let's look at how you actually do this. So x3.endim, okay, it will tell you it's a 2-dimension, and then if you do x3 shape, it will tell you it's a 2 by 2, and the last thing is x3 data type, and it will tell you it's integer 64. Okay, so once again, thank you for watching. I look forward to seeing you in the next video. Welcome back, everyone. We are still in the building blocks of deep learning. So one of the key concepts of neural network and how it learns, let me just come back here, under the optimizer, is that it uses what's called gradient-based optimization. And And another word for gradient really is actually slope. For every layer, deep learning neural network layer, every layer ends with what's called an activation function. Now this activation function comes in different, a few types. You have the sigmoid, you have softmax, and you have ReLU. Again, I'm not explaining this. Sorry, yeah, yeah. I'm not explaining this for now. I will cover that in separate lesson. I just want to highlight that the actual activation function is to actually squash the data so that it actually provide a specific output. Right, let's walk through these one by one, where W is the actual weights. We've seen that before. That's the weights for every node of the layer. B is the bias term. Now if you think of linear regression or y is equal to mx plus c, the B here is actually the bias term, which is the intercept term. And then the initial weights, when you're actually training your neural network, initially the weights are set randomly. Now of course that's not the best place to start, but for now we will take that. And then after that, of course, when you actually set it at random, it's not going to have a really accurate prediction or a very accurate neural network that is able to actually predict everything accurately. So the training part has to come in. Now we then need to make gradual, not graduate, as gradual adjustment. Okay, let me just gradual. We need to make gradual adjustment, or rather we need to gradually adjust and update to the weight to reduce the error. So which is this portion here. So we need to actually continue adjust this so that the loss function gets smaller and smaller, our prediction get closer and closer to y. Here's an example of definition of neural network, or how you define neural network in Keras, whereby you have the import from models to sequential, and also for layers we import dense and activation. So we have two dense layer here with 32 neurons and 10 neurons, and the input shape is specified, and the activation function is ReLU here and softmax here. So these are some of the basic concepts. I will cover this gradient-based optimization in a future lesson. I'd want to actually touch on this for now so that you are aware that this exists. That's the first thing, and you need to understand that this is the actual so-called layout. The other way to look at this, let me just touch on this for those who are a little bit more mathematically inclined. You can think of this portion here, the inside part here, the dot W multiplied by input plus B. You can actually write it as Wx plus B. This is going to look very similar to y is equal to mx plus c, where this is the intercept term, also called the bias term. X is our input data, m is our slope. You'll notice that they actually look very similar, except that this is in the vectorized format. This is usually not in their vectorized format. And of course with this it comes out in the terms of some sort of value, and we have a sigmoid function that's being applied to fx after the value has been calculated. Okay, I'm going to refrain from explaining what a sigmoid is. I will cover that in future lesson, but for now just understand that through this formula, okay, is how the whole neural network gets trained. Okay, we've covered this, and let me walk through the training loops so that you can understand at least conceptually how it's done before we actually implement the actual training itself. Right, you draw a batch of training samples, X and the corresponding targets Y, and you train the neural network on X to obtain prediction of Y. Recall, you draw a batch of data X and Y corresponding Y, you train it to obtain a prediction of Y. Okay, So we are up to this point, level, step number 2. Then you compute the loss or the errors of the neural network on the batch, meaning your prediction, Y prediction, how far is it from the actual Y. Step 4, then you compute the gradient of the loss with respect to the neural network parameters, and that's what's called a backward pass. Again, if you don't understand this, that's okay. Alright, that's not bad at all. We will actually cover that in a numerical example so that you can actually grasp it a bit better. So with this is portion here, you are actually computing the gradient of the loss, meaning you're calculating the slope with respect to the loss with respect to the neural network parameters. Okay, meaning the parameters here is x and also y. Okay, so that we are freezing x and y, and we're actually changing w. Okay, we're changing w, which is the gradient here, until we actually get the optimal output. So let me come back here. I've removed that. So let me help you recall. What we did do just now is this. I draw this, y is equal to wx plus c or bias, or fx is equal to w x plus bias. So let me just change the color a little bit. Black. We are freezing this. We are freezing this. So what's left is this. This is our projection, and then we have a actual y. So I can call this, or let's just call this, I have an actual fx, which or actual value, or sometimes it's also called y, and I have an fx here or y hat here. Because this is fixed, this is fixed, these two parameters are fixed. Okay, so what's left now is to actually change w so that our y prediction is closer and closer in value to y. So that's really what this step number 4 is. And finally, step 5 is, once we actually calculated the gradient, we move our parameters a little in the opposite direction from the gradient. If it's a positive slope, we'll put a minus, okay, so that it moves closer. If it's a negative slope, we change the sign to positive so that it moves towards the right direction faster. Okay, so we move the parameters a little in the opposite direction from the gradient, taking one small step to reduce the loss on the batch. The step here, okay, where's my pen? Okay, the step here has another name called learning rate. We've calculated the gradient from earlier, so the point now is that we actually put a minus with a small learning rate in the direction of the gradient. Okay, the minus here meaning opposite of the direction of the gradient, so that we move closer and closer. Our y prediction moves closer and closer to y. Alright, conceptually, this is the training loop. This is how neural network learn. I know that right now you're not convinced in terms of how this actually can work out. For that, I need to actually show you an example. But before we do that, let me just explain one more concept, which is the stochastic gradient descent. And it is an optimizer, which is along the line of what we looked at earlier. Yeah, it's not here. Okay, we have looked at RMS prop. This is another alternative, which is called stochastic gradient descent. Right, so a couple, again, some terminologies. The first one is SGD, which is the stochastic gradient descent. With this, we actually draw one sample at a time. And if it's a mini batch stochastic gradient descent, we draw a batch of data or a sample set of the data. It shouldn't really be sample, a sample set of the data. The common batch size is 128,512, and also another terminology is called batch SGD. This is all the data. So at the one extreme, the stochastic gradient basically run one forward pass with one sample and then update the gradient. At the other extreme is it gets trained with all the data, then it update the gradient. All right, update the gradient and the weight essentially. Mini batch is somewhere in the middle, whereby it only draw a sample set or a batch of data, which is either 128 or 256, or whatever that you specify. So at the one extreme, you have every time you have one data, and then you actually update the weight, which is computationally very expensive. The other end is all the data, which means the update is quite slow. So you have something in between, which is the mini batch SGD, which is something that's a lot more popular. There are other more sophisticated techniques, SGD with momentum, AdaGrad, RMS-Probe, but we'll cover this in the relevant lectures in the different segment of the advanced neural network models. For now, all you need to know is that these exist, and we will cover these in future lessons. For now, sufficient to know that we are looking at stochastic gradient descent or mini batch of SGD. Alright, with that, I hope that has been useful, and thank you once again for watching. Welcome back everyone. In this session, we're going to look at getting started with neural network. For a start, I just want to revise some basic principles, which is the anatomy of a neural network. And the elements that you will typically see is, number one, you have an input data, which is X here, and then you have a target labels, which are labeled as actual, and then you have the layers, which is this and also this. In this case, we have two layers. So when you combine them, they are called neural network. And then you need to measure the accuracy of your prediction, which is here, and the actual measurement that we use is called a loss function. The output of the function calculation is called a loss score. It informs you how far away is your prediction from the actual scores. And because obviously in the beginning the weights is actually originally just randomized number, we need an optimizer of sort to actually continuously tune our neural network until the weights are accurate or able to allow our neural network to predict accurately. Optimizers, some example will be stochastic gradient descent. We discussed a few others last time. And the picture below really is an example of what a neural network may look like. You have two inputs. You have layer 1, layer 2. These are the two hidden layers, and then this is the output layer, single output layer. Alright, so it's time to actually have a look at some of the really popular deep learning libraries. I've only highlighted 3 here. There are actually a lot more. Theano, I guess you can call it the grandfather of deep learning libraries. It's no longer commercially supported, but it's still hugely popular. Before any of these previous libraries, Theano is really more or less the first, and it's the most popular deep learning libraries that's being used. Ever since TensorFlow was launched in 2015, it basically took off. It's now the most popular. This is obviously supported by Google, and Keras is supported by Cholet and quite a few of the engineers from Google as well. Interestingly, Keras was actually launched in March 2015, whereas TensorFlow was launched late 2015, around November, if I remember correctly. PyTorch is actually supported by Facebook, and but these 3 are really the most popular of all the different various deep learning libraries, as you can see from various metrics. One that I've shown here is just Google search. Right, finally, in terms of the workflow that I just want to discuss with you before we go into looking at some examples. Keras and TensorFlow is what we are using in this course. We're using Keras because it's really probably one of the easiest to grasp in terms of the concept. Rather than get down to the nitty-gritty of it, you can actually visualize it. From previously, I've shown you how it's done. We're going to go into a few more examples this time. looking at the workflow, typically you will need to define your training data. You have your input X and your target Y. So you need to get your input and also the so-called result that you want the neural network to learn. And the next thing you need to do is define your network architecture. From the complexity of the task, you have to make choices in terms of how deep your layer is and how many neurons to learn. And the next thing is you need to select the appropriate loss function, optimizer, as well as performance matrix in order to actually measure the performance of your neural network. And you repeat this task until finally a pre-specified performance is reached. Those are the basic workflow that comes with neural network. And with that, I'm going to stop here and we're going to go into example in the next video. Thank you once again. Welcome back, everyone. In the next few lessons, we're going to look at some of the mechanics of machine learning, some of the key part that we need to cover in terms of wrapping up this course is how do you evaluate the machine learning, the performance of it. Of course, we're going to touch on a little bit of the different categories of machine learning, although we've already gone through that extensively in another course. We're going to talk about how do you split your data, why do you split your data into train, validation, and test set. And we're going to also cover data preprocessing, feature engineering, and how to spot over and underfitting. And that's pretty much some of the key ideas that we're going to cover. And before we finish, we're going to touch on regularization and dropout, and finally workflow. So let's dig into it. The first one that I want to cover with something that is hopefully a review for you. Nevertheless, I do want to cover it for those who have not seen it before. There are really 4 different categories of machine learning. There is the supervised, which is your typical classification and regression problem. It could include also sequence generation, object detection, and image segmentation. By and large, this class is called supervised because you provide the actual target that and also the input data so that the neural network learn the expected output. There is also the unsupervised, which is well, there's basically no target here. The machine learning algorithm needs to distinguish the underlying pattern, clusters, the similar patterns together, or reduce the dimension of the actual underlying pattern itself. And also you have self-supervised. These are autoencoders whereby, again, the so-called target is not provided. It learns to categorize by itself using autoencoders, hence it's called self-supervised. This is a new class on its own. It's a real, fairly new invention, only really a couple of years old. And it really deserves a class on its own because it is quite unique and quite different altogether. And the final one, one that has caught a lot of, received a lot of headline attention, is reinforcement learning ever since the AlphaGo that beat the world champion. So those are the real basic 4 different categories of machine learning. And I just want to revise this once again in terms of machine learning performance evaluation. We've seen this many times before within this course. You have your input data. There's multiple layers of for your neural network, but that's the prediction and the comparing against the actual Y. You use the loss function to measure the difference and generate a loss score. Of course, to improve your neural network, you use an optimizer that's based on the problem that you're faced with, and finally, it continued to tune the weights, which is really the memory of your neural network as well. So the goal of machine learning is that your model is able to generalize to problems that or data that has not seen before. And what exactly is a loss function? We covered this. Really is the function to calculate how far does your prediction deviates or away from the actual. And the loss functions depends on the problem that you face. It could be binary, multi-class, or regression problem. Okay, so just want to touch on a little bit of train, validate, and test. This is really important concepts. I did talk about this a little earlier. So just go straight to the keynotes here. Test dataset is meant for you to be used only once only, and only at the end of the model building. So this is necessary because you want to prevent information leak. This is the only way that you can tell whether your model can actually perform well in the real world situation or not. So test is really the only way that you can actually tell. Hence, you cannot touch it to build your model. That's the key point here. You cannot use the test to build your model. Your model building must be done using training dataset. Of course, you still need to check how good your model is. That's where the validation dataset comes in. So for your model, your neural network model, it would have seen these datasets, the training datasets, many times in order to learn the weight. There's no way for you to tell if it overfit and whether it can generalize to unseen data. Hence, we use validation, a dataset, to evaluate your model performance with respect to various hyperparameters. Okay, so this is an example of what's called a single holdout test set, whereby you have a training set and then you have a test set. I'm going to show you, this is the simplest of them all. I'm going to show you a few variation of this and the best practice as well. So this is a single holdout set, and this is useful, but it does suffer from some flaws in that after you train your data, there's no way for you to tell whether it's overfit or underfit. And that's not good. So which is why this was developed. You have a single holdout, validation, and test set. What I mean by single holdout here is actually, we use a pen, is this portion here. So there's only one of these, so that's why it's called single. Earlier, the previous slide, the example was this one. Okay, now instead of that, the training data we split into, maybe this is just 10% of your training data, the remaining 90% is used to train your data. This is much better because now you have some way to validate to see if your data has indeed, or your neural network model has indeed overlearned or overfit your training data. So that's where the validation comes in. But one of the more common best practice is to do this. It's called k-fold validation, whereby you have one fold to actually test your data. So there's a 10-fold here. This is common in the shallow machine learning. For neural network, this is sufficient. Just one single holdout validation and also a test set is sufficient to validate your neural network. All right, I hope that has been useful. There's just one more key points, a few key points that I want to actually highlight before we move on. That's this slide on traps here. Please be mindful of them. The data representativeness is important. You must have all the so-called target as well as its features represented in your training data. Otherwise, your neural network never get to see an example, so it will never would have learned. And for time series data, don't shuffle because the sequence and the order of how the data comes through is important. You have to ensure that all your test data are posterior, meaning in the future, to the data in the training set. So to use simple English, posterior here basically means future. Data redundancy, also make sure that the same data is not repeated in both the train and test data. This is a mistake that I demonstrated to you when we were looking at the binary classification one. We did some training on the validation set, before we actually created the validation set. So that's basically, notice that the error was significantly lower. You can try that out, but the problem when you actually do that is that well, your validation is no longer useful as a validation data set because you have allowed your neural network model to see it. And the other example is you have the same picture of the same cat, exactly the same picture in both your training as well as your validation as well as your test, either or. This is in a real world analogy, this is basically cheating. You know, it's like a teacher giving the student sample exam questions and then testing the same questions in the exam. All right, so that's really what's the traps that you do need to be mindful of, and it's critical to pay attention to that. With that, I'm going to stop. In the next video, we're going to go into data pre-processing. Welcome back, everyone. Good to see you here again. In this portion, we're going to look at overfitting as well as underfitting for your neural networks. Now, there is always a trade-off between underfitting and overfitting. The goal of training your neural network is so that it can learn from the pattern of the data. If it's underfitting, it's a waste of the data, so we tend to continue to fit the data. The only problem is that it can overfit your training data and it's not able to generalize. So that part is important. Now the fitting process, there's another term for it, as mentioned here, is called optimization. Your model will always start off with being underfitted. Now as you continuously expose your data, your model to the training data many times, it will continue to improve, but there will come a tipping point whereby your model will overlearn and will overlearn from the training data and wasn't able to generalize. And at that point is actually you should and ought to stop the training. Now, underfitting is when your model has not learned fully from the training data. In this situation, both the training and test loss will be falling on each epoch. So we demonstrated that in some of our examples. In fact, all of our examples that we talked about that. This is for the loss score. Now, in order to improve both your training and test score, you can increase the number of times your model epoch see the data. Each epoch it sees all the data. This process is also called optimization. Overfitting is when the loss score in the training and test start to diverge. The training loss score continue to fall while the test score start to rise. So rising is bad. Okay, so that means the errors is going up. So in this situation, the model is starting to overfit your training data and unable to generalize. It will not perform well with data it has not seen before. The data that it hasn't seen before is also called test score. How do you overcome overfitting? There's a few ways. You can get more data. You can also perform what's called regularization, meaning forcing your weight to be within a range. Okay, so that is actually constrained. So regularization, there's a few ways. There's reduce your network size, meaning don't have too many neurons or don't have too many layers. Weight regularization is pertaining to the weight, meaning constrain it to within a range. Dropout is something that we will look at. Essentially, as we are running our training, from one level to another level, we drop some of the nodes or the neuron data and don't pass it on. But it's randomly dropped. Doing so improves the model's ability to generalize. Okay, so these are the few key points. Reducing the network size, I covered before, either manage the number of layers or manage the number of nodes per layers. These are also called learnable parameters. This dictates the capacity of the model. Now this part is more art than science, hence it's a good idea to have a GPU or use cloud-based computers to improve that. With this part, I'm going to show you two examples, I should say, when the model is undersized and the model is too big. and using a benchmark as a reference. And for weight regularization, you force the weight to be restricted to within the range or constrained to within the range. This is done by applying a cost term to the loss function. What is this cost term? There are two types of cost term. There is the L1 regularization, and the other one is called L2 regularization. The difference between the two is that L1 is the absolute value, L2 is the squared value. So let's look at L1 regularization. The cost term is proportional to the absolute value of the weight coefficient, meaning it is constraining it based on the absolute value, whereby the second one is relative to the squared value. But dropout is the more common and much more popular method. This is created by Hinton. Again, it's also called the godfather of AI. And he's the one person that has been persistent in pursuing his goal. I guess you can call him dogged as well, but without him, we will not have AI today. Dropout is the most commonly used. It applied to a layer. Basically, you're randomly dropping, meaning zero setting, meaning setting the weight to zero. A number of output features of the layer during training, sorry, not weights, it's in the output, not the weight. The weight is retained, but the output from layer to layer is not passed on, meaning it's zero before we move on to the next layer. Now, according to Charlotte, dropout rate usually is set between 0.2 and 0.5. During the test time, however, no dropout is applied. All right, so look at some examples here of the so-called validation loss that I have extracted for you. And let's look at this. What do you see? You have the blue plus is the original model. When you look at the blue plus, it's consistently low. And you notice that the smaller model is consistently higher, meaning it has a larger validation loss. What that is saying is that the smaller model, smaller neural network, is not able to learn the features or the richness of the features in the data itself. Hence, there's always a gap. It wasn't able to learn. Not only was it able not to learn from the training data, in the validation data, it wasn't able to actually generalize as well. It just wasn't able to provide a better prediction. So that therein lies, hence I'm using validation loss rather than the training loss. Let's have a look at an example of a bigger model. If you look at this bigger model, this is zooming in. It's the same original model that we're looking at, except the scale is a bit different now. If you look at this, what you can see is that the larger model started off with a better validation loss because after the initial few epochs. And it's able to actually, well, if you look at this, what you can see is that, let me just use a pen so that you can actually follow along my argument. Let me just change the color to black because we have, let's use black. Right, this is the original model and this is the larger model. Okay, so the larger model starting off with a better validation loss. And then we have the crossover here, where the original model goes down, the validation loss for the larger model goes up. And that's when the larger model start to overfit the training data and wasn't able to actually predict as well on data that is not seen. But that's not the key point of this slide. The key slide that I wanted to actually highlight is that the larger model is able to learn the features better. Hence, it actually has a better loss up to around, let's just call it 8 epoch. Okay, so that's the benefit of having a bigger model, is that it is able to learn the data better and also able to predict better. So therein lies the contrast between the smaller model, the original model, as well as the larger model. Now, if we look at the original versus the larger model training loss, you will notice that they are continuously falling. It continues to adapt and learn from the actual training data itself. From here, you cannot tell that it is actually overfitting. We know from this previous slide, from the number 9 onwards, epoch 9 onwards, the larger model is already overfitting. And hence, you always have a validation data to inform you of that. Okay, I also want to show you how you can actually perform weight regularization as well. Ignore those commented code. If you look at the data, or rather the line of code, this is an L2 regularization. And how you actually apply the regularization is that you have this line here called kernel underscore regularizer equals to regularizers dot L2. This is L2. Okay, so that's L2, and the value that you use is 0.001. So this is L2 0.001. Okay, and the rest are exactly the same. And notice that this is obviously a larger model with 2048 nodes. Basically, it means that, you know, in your neural network, so let's just say you have 3 input, and you have 2 layer, and then you have, let's just say, 3 output. And what you have here is, it's basically 2000 neural nodes. Okay, neurons here. So let's just from 1 all the way to 2048. So that's how many there is here. Now, so that's an example of L2. What about L1? This is an L1, and the actual difference between the both line and this is just that for this you have L1, but you have to write it as lower cap, okay, not upper cap when you're actually writing the code. I'm just changing it to upper case so that you can actually see that easily. So that's basically for L1. And for L1 and L2, this is what you do. L1 underscore L2, and for L1 is equal to 0.001. So basically you're actually providing the L1, the value that you want to regularize it for. So that's pretty much it. And you do apply regularizers for each of the layer as well. And apart from that, the rest are exactly the same. I hope that it's clear. Let's have a look at the application of weight regularization on the larger model. And if you look at this carefully, this is validation lost. You have the L2 regularized model here, and you notice that it's well, it's basically being forced, constrained. So, oops, sorry. Okay, this is the, let me just bring on the pen. So this is the L2 regularized model, and hasn't actually overfit the data, in contrast to the larger model, which is around here, and it jumps, it has overfit. But in this situation, what happened is that because the regularization that's applied here has constrained the model so much, is that it did not perform as well as either the original or the regularized model. And this is the part whereby you need to tune. The regularization here is what's called a hyperparameter. It's not part of the neural network parameters, hence it's called hyperparameters. So if I look at dropout as an alternative to applying weight regularization, what do we see? Right, so we have a couple of models once again. So let me just bring up my pen. You have the green one is your larger model. You have your dropout. Let's look at the larger model there. This is the asterisk or plus is your larger model. Okay, let's just change color. Okay, so let's just draw this. This is our larger model, unconstrained, without any regularization or dropout applied. So let me just change to the pen color, and this time just use yellow. This is our dropout model. Started off, didn't perform as well. Okay, and then the validation is better than the larger model, and around here is still better, it's worse, it's better, and notice that it continues to do better even as we allow the data, more data is being applied. In fact, when you look carefully, and actually perform as well as the original model. And it seems to be stable. Of course, you can continue to run this, but this requires a fair bit of tuning, a fair bit of playing around with it until you actually get an ideal optimal neural network. That part takes time, and I hope that this portion on dropout, weight regularization has been useful, and I hope that you've gained much out of this and how to manage and understood also what is overfitting and underfitting, and how to actually and what to do with it when you actually do come across this situation. Thank you once again for watching. I look forward to seeing you in the next video. Welcome back, everyone. Good to see you here again. In this slide and lecture, I want to cover machine learning workflow. This is one of the key slides that I have to help you in terms of developing a successful and also working machine learning model that works for you. Now, the first and foremost is this is one of the most crucial steps. Is to define the problem that you are facing, and your definition of the problem define how big a data set do you need. If you do not define your problem properly, you may come across a situation whereby you need to collect a lot of data, and the actual training itself will take a long time. I'll just give you an example as to help you understand and appreciate this point. If I'm training a neural network to distinguish between cats and dogs and pandas, then all I need to do is collect data for these three types of animals. But if I want a neural network model that's able to actually tell or distinguish all the different animals in the world, you can very quickly see the scale of the problem and how much work you do need to do, and whether it is, of course, there's the secondary the second consideration that you need to think about is that why do you need to actually have a neural network that actually able to distinguish all the animals in the world, including animals in the sea and also deep sea as well? If you put it in that perspective, then it might not make any sense to actually pursue that line of model constructions. So you need to actually be very clear of the problems that you're actually trying to define here. If you are just trying to build a model to distinguish cats and dogs for a pet or for a veterinarian, then it's a different story altogether, and that will actually be a substantially easier model to build and much faster, and to put it into production in a much shorter time as well. So therein lies the key part here, is to define your problem definitions, what kind of a problem it is, which is the second step. Is it a binary classification, a multi-class classification, regression, clustering, or reinforcement learning? Understanding your problem is crucial on how to determine what the next step is. So also, do you have the necessary data, and is it easy to get hold of these data? Some data, and often a lot of data, are really expensive and difficult to acquire. Do you have the means to do so? If it's for business, then it may make sense, but you also have to consider other issues such as data privacy and the ethics of it, and also regulatory constraints. And these are all the things that you need to keep in mind. The next thing is you have to choose a measure of success. What kind of success performance measurement or matrix do you use Do you use accuracy, which is what we have been doing so far, or is there other better means such as precision and recall, ROC, AUC? These all apply in different situations, so those are the things that you need to keep in mind as well. And the next one is decide on an evaluation protocol, holdout validation set, or K-fold cross-validation. We already covered this at length, so I won't draw that out anymore. And the next part is data preparation and pre-processing. That part is also clear. The fifth one is develop a model that performs better than baseline. And the next step, step 6, is to scale up, develop a model that intentionally overfits. That's when you start to regularize, step 7, and tune your hyperparameters. So those are the 7 steps in building machine learning, and this is a workflow that is as a reference, and that's useful. This is provided by Charlotte, and I hope that has been useful. Thank you once again for watching, and really appreciate you for following me all along this journey. Welcome everyone to the course on Introduction to Convolutional Neural Networks. This is a fancy term for basically computer vision. This is a really exciting course that's coming up ahead in front of you. I'm really looking forward to it because there's so much to actually show you in terms of what the state-of-the-art technology is able to do right now in terms of the artificial intelligence as well as deep learning that can enable you to automate and also expedite your business processes. So the underlying technology that can tackle this computer vision problem really is called convolutional neural networks. So let's dive into the outline and have a look at what we are going to cover in this course. So first of all, we're going to cover some basic from previous course, which is the neural network. I'm going to revise some of the key concepts, and we're going to dive straight into the motivational example first before we look at the portion on how does convolutional neural network actually see. What does the computer actually see, or how does these deep learning architecture actually see? And it's clearly not going to be the same as how human visualize things and how we actually make sense of the world around us. So we're going to have a look at it and get some intuition out of that. The next portion is that we're going to dive into some of the key underlying architecture, which is understanding convolution, which is this portion here, followed by training your own CNN, followed by some more advanced concepts such as transfer learning. Rather than using one that you train yourself, we can actually make use of some of the state-of-the-art architecture and expedite the process or make use of what others have worked on and use it for your specific situation. You'll be surprised that CNN or deep learning is transferable, and that's where it's really exciting and that saves you tons of time. And the last two parts is really visualizing network layers. Once again, we'll look at how do you actually peel back the layer in terms of what the CNN actually sees. This is a little bit different from this second portion here. The second portion here really talks in depth about how the so-called different layers work, and the last part here is actually show you how to extract the actual layer itself. So the first part 2 shows you what it sees. Second last part, just to wrap it up nicely, is I'll teach you how to actually extract those filter or the layer, what's in there. And finally, I'm going to wrap up with where to from here. This is really an introduction course on CNN. We will cover the architecture until around 2015, 2016. There are more advanced, there are advancements since then, and those will be in a separate course. It's just too much to cover within this one course alone. I really want to actually give you a sense of how CNN actually work and start to build those foundations for you to actually well, start working on projects that is useful to you. With that, let's start this journey together. Thank you once again, and I'm looking forward to seeing you in the class. Welcome back, everyone. Let's do some revision on neural network. That's what the NN stand for. Let's look at the basic architecture of what it looks like. So let's look at this. So for a start, when you look at this, what you have is an example of a standard artificial neural network, also called neural network for short. If you look at the basic architecture, you can identify some basic characteristics. The first being input and also output. So you have your input, which could be pictures, could be features, could be a two-dimensional data. And this is the input layer, and this is the output layer. And then you have three layers of three hidden layers. Now these are what's called fully connected, because every one of these neurons are connected to the next layer of neurons, and this is connected to the next layer of neurons. Now the secret source to all of these neural networks lie in the actual hidden layer itself. And what we're going to look at is the so-called convolutional neural networks, where the distinguished features are. The distinguish or the difference lies in the actual hidden layer. So for now, let's revise some of these key concepts, and then in the next and future lecture, we're going to go into the architecture of CNN. Now, what have we learned so far from the previous course is that machine learning is really about learning the rules that link inputs and also targets together. So if you provide the computer with pictures of cats, it needs to learn some features of the cats to be able to identify that this is indeed a cat, which is targets. And if you provide it with pictures that it has never learned from before, a brand new picture, for example, a mountain cat, for example, which it hasn't seen before, and hopefully from the features that it has learned in the past, it is able to identify that the actual target or the prediction is indeed a cat. It will give you the label that this is actually a cat. Now the question is really finding that features or the three question mark there to link the inputs to the actual target output. I provided the picture and or rather the flow diagram below just to establish or just to illustrate to you the link itself. Now in order to do that, neural networks require many examples to achieve this, to learn this, very similar to how humans learn. If you have ever watched a child of 2-3 years old, how they learn in terms of the naming apples, oranges, and identify objects, it's the same process. Right, from the previous slides, we can see that there are many layers to deep neural learning network or deep learning neural networks. And now these layers learn the relationship between the input and the target from being exposed to many examples. That's really the basic ideas of all of these. So in this portion, we're going to continue to look at some of the example here in terms of the CNN or the convolutional neural network example. So let's dive into it. So this is VGG16, also called Very Deep Neural Network. Now this has been around for quite some time. It's still considered one of the more established and well-known neural network architecture or CNN architecture. It's from the paper by Simonia and Zierman. The name of the paper is called Very Deep Convolutional Networks for Large-Scale Image Recognition. This is published in 2014. It is still used today as the backbone for some of the object identification algorithm that's being used today. So let's look at the example of neural network architecture. I provided a link here. Feel free to actually browse through that. We won't actually go through that for now. What I have not removed or not shown here is the last few layers, which is the fully connected layer, and it has been removed. When we look at the so-called layers here, you can see how deep this neural network or this CNN example is. You have the input layer, you're followed by block 1. If you look at the block 1, you notice that there's 1, 2, 3. It has convolutional layer, another convolutional layer, and then a max pooling layer. Followed by block 2, you see that there's convolutional layer, followed by a max pool. Block 3, you have another convolutional layer, followed by another max pool. Block 4, convolution, followed by max pool. Block 5, convolution, followed by a max pool. I intentionally go through that repetitively to hopefully allow you to see the pattern. You notice that the first 2 blocks is 2 convolution followed by a max pool. Second block is 2 convolution followed by a max pool. And then the following block 3, 4, 5 is 3 convolution followed by a max pool. This is 5 blocks. Ultimately, if you look carefully, it's actually a lot deeper than 5 blocks. It's actually 16. That's why this is called VGG 16. This is an example of CNN. I'm going to start calling CNN now. I'm having a problem pronouncing convolutional layer. CNN as an example of CNN architecture. Let's again revise one last key concept before we move on. You will recall from our previous course lecture is that we provide the neural network with inputs, and there are some weights that needs to be trained. Initially, it's just randomized weights, followed by 2. In this example, we have 2 hidden layers or 2 layers for this neural network, followed by a prediction. From the prediction, I compare against the ground truth or the actual label, and then measure using the loss function to measure the loss score. Loss is another way of saying errors. And obviously, initially, the neural network hasn't learned yet. Okay, it needs to actually go through an iteration, a loop to actually continuously learn. Where it made mistakes, they need to actually make some adjustment to actually learn the actual features to be able to correctly identify and also in the future predict what the actual image is. And that process of continuous loop is called learning. And the method or the instrument or the mechanics used to teach the neural network is called the optimizer. Okay, these are all revision concepts. Hopefully it's not too foreign to you. If not, please go back to the other course, Neural Network Foundation or Introduction, to actually build those foundations before you carry on, because this whole course is actually built upon that. With that, I'm going to stop. Thank you once again for watching. I look forward to seeing you in the next lesson. Welcome back. In this segment, we're going to look at a motivational example. Now, this is from the other course as well, called Foundational Neural Network or Introduction to Neural Network. So what I have is the example 1, and example 2 is this one here. Okay. All right. Let me just walk through these codes just to refresh your memory, and then we're going to go into a comparison between the neural network, an artificial neural network versus CNN, and compare them in terms of performance. Right, so the process is as usual. You import the data, or rather you import NumPy, you import Keras, and from Keras we are using the MNIST data set, and then we split our data sets into training set and also the test set. This is the basic usual data exploration. There are 60,000 rows of data, and each of them are 28 by 28 rows and 28 columns. And they are all in the NumPy array, and this is what it looks like. It doesn't make any sense. Hence, what we do is that we usually convert it to an image format that looks like this to make some sense out of it. So looking at the training, Y-train, previously is X-train. This is the Y-train, which is a target variable. The shape is also 60,000. We're looking at the second, which is the third item, remember the Python start counting from 0. So we're looking at 4. The actual target here, or the label is 4. And if you look at the corresponding X-train 2, is the image looks like this. It's a 4. It's a handwritten digit. Right, and then if you look at the X-test and the Y-test, there are 10,000 rows of data that we're using to actually test the accuracy of the neural networks. In terms of the architecture, we're using Keras here, and the actual model is a sequential model, and there are 2 dense layers. There are 512 neurons, so you can see that this is quite a massive neural network. It's very wide, but it's not very deep. And so breadth-wise is 512, but depth-wise is only 2. Because we have 10 classes or 10 digits, so that's why we actually have 10 dense so-called outcome here. And we're using the softmax as our predictor rather than sigmoid. Sigmoid is for binary, softmax is for multiclass. So those are the basic steps. After that previous portion is really just reshaping our data in such a way that there's 60,000 row. We're combining, reshaping rather than 28 by 28 in terms of the 2D. We convert it into one vector, and we convert the data, normalize it into between 0 and 1, hence we divide it by 255 because the numbers here is between 0 and 255. And we're using an optimizer which is RMS-Prop, the more advanced version, instead of stochastic gradient descent or SGD, and we're using categorical cross entropy rather than binary because we have 10 digits here. And the training shows that in terms of the performance, accuracy starts from 91% and reach a peak of 99.63%, and in terms of the prediction is 98.15. Right, so that's really a really quick tour, a revision of what we looked at. If we go over to the motivational example, the first portion here is exactly the same. Okay, well, I'm just combining all the codes into one, and instead of calling it model, I call it ANN. And if you look at the performance, it's exactly the same, 98. And in terms of the prediction, it's 98.01%. You can see that the architecture, it should look familiar to you. It's 512 in terms of the number of neurons of breadth, and the depth is only 2 rows, 1 densely connected layer and another one. So there's actually 2 of them. Now let's have a look at CNN, convolutional neural networks. If you look at these first cell here, they are exactly the same. If you are looking at the, I put a note here, this is without padding. Just take note of that. That's not important for now. We will actually cover the actual details of the architect a bit later on. Right, so in terms of the architecture of the CNN, we have a convolutional layer followed by a max pool, another convolution layer followed by a max pool, convolution layer followed by a flatten, and then another 2 densely connected layer, and that's it. That's all that we have. So we have 1, 2, 3 convolution layer, 2 max pool layer, and then flatten it so that the so-called softmax, the classifier, can actually make prediction out of it. This is an important process or step that they actually need to flatten it. Otherwise, the softmax will not be able to perform what it needs to do. So the rest is exactly the same. We need to compile it, we need to fit it, and then follow by prediction. So if you look at the training score, this is the highest, is 99.807. Already is actually outperformed against the ANN. This is 98%. And this is the actual print of the architecture itself. You can see convolution max, convolution flatten, 2 dense layer, and if you look at the prediction, it's 99.16. It's far outperformed the 98.01 of ANN. And that's the basic idea of CNN. You can see that this is really an exciting space. This is where you can see that the CNN outperform the ANN in terms of the prediction, and it actually able to learn, not just because the actual prediction is more accurate, but what's more important is that it's actually, you can see that it actually learn distinguish the key features that the ANN weren't able to learn before. And therein lies the problem with fully connected layer, is that it just learns the universal features, but it doesn't actually learn the intricacy of some of the key difference in terms of the shapes of the underlying pictures that we fed through. Okay, so that's really to motivate you to understand why we actually embark on the journey to learn CNN, which is the state-of-the-art architecture for object detection and image recognition. And when we come back, we're going to start get another perspective or intuition of how CNN actually view images. This time around, a lot more visual rather than code. And I look forward to seeing you then. Welcome back, everyone. It's good to see you here again. In this session, we're going to move into visualizing CNN. Let's start with the architecture itself. What you see here is a VGG16. VGG16 stands for, the title here is Very Deep Convolutional Networks. So VGG. If you look at this architecture, there are 16 layers here. The layer count is based on 1, 2, the convolution layer, 3, 4, another 2 convolution layer, 1, 2, 3. So we've gone to 4 plus 3, now 7. 7 plus 3 more makes it 10, and then plus 3 more makes it 13, plus 3 more fully connected layer that is not shown here. But I'll show you in the actual so-called paper itself. If you look at C, that's the configuration that you are looking at here. In terms of the C, this is the 16 weight layers. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, plus the 3 fully connected layer down here. The next max pool layers are not shown. What we are interested in, and specifically, are the convolution layers. Is designated as CONV2D. It's always a mystery for the longest time how neural network actually see the world, or what kind of images does it see. So the best way to actually visualize this is to understand how each layer actually work. So that's really the purpose of this session. We will start with, just to gain an appreciation of the actual kernel itself. What exactly is a kernel? Let's come over to satosa.io, which I've opened up beforehand. Now, an image kernel is basically what is called a small matrix. This is used to apply effects on the actual picture itself. Could be blurring, could be sharpening, and many various so-called effects that you're trying to apply to the picture itself. In machine learning, it's called feature extraction, and we convolute through it. And in future session, we're going to look at the mathematics beside it. Now, first of all, let's start with an image. Now, you can see that this is a blur image. As you move your mouse along, and you notice that as I'm moving along, it follows along on the left-hand side, the actual so-called numbers to go with it. You can see that white is 255. When I move to the black spot, the number approaches 0. So the number designate or represent the actual color as from white all the way to black, and all the shades in between. Now let me move out. Now if you apply a kernel, let's just pick a blur kernel, and you will see that the images becomes more blur. That's because of the red cubes. Can you see the red cubes? The 9 red cubes that's moving around on the left side. So when you actually choose this blur 3x3 matrix, which is a 9 cubes here, as we're moving along, we're actually applying the so-called blurring effect on it. Now these 3x3 red cubes are called kernels. Every time when you actually apply this kernel, and the actual so-called operation is called convolution, it actually changes the underlying pictures. On the left-hand side is our input image. As we apply the so-called kernel, you get the output image on the right. So there are other so-called handcrafted kernel. We can choose bottom Sobel, and this is what you get. The bottom Sobel, this is what the 3x3 looks like. It's -1, -2, -1, 0, 0, 0, 1, 2, 1. Okay, so as you take the actual picture and apply the kernel to it, the right hand pictures is the output that you receive. Of course, you can choose a whole lot of others. You can emboss it and a few others. That's the basic concept of kernel. You have your basic image, you apply a kernel, outcome, which is the output image, will have the effect applied to it by the kernel itself. Now, as you can see here, there are a few common ones that's being listed. What we actually wanted to look at is how does these kernel actually work. You can actually do more playing around with these pictures. As you can see, you can actually change the 3x3 kernels a little bit to obtain the effects that you want to actually obtain. So that's really the basic ideas. You can actually look at a few other guidance down here. Like image kernels here is quite a good guide as well. And there is also a good guide in Wikipedia on the CNN, how does it work. Now let's come back here. Other things that I do want to show you is we can actually visualize and understand the actual convolutional network itself. So if you look at the layer 1, this is what you actually see. It's a 3x3 and each cube here, each block here is another 3x3. So the layer 1, you can see these are all edges. You know, they are fairly simple patterns. As you go to deeper layer, so this is layer 1. As you move to layer 2, you can see that the patterns start to get more complicated. And then as you get to layer 3, it gets even more complicated. The right hand side are the input images. The left hand side is how does the actual CNN actually see. You can see some of the wheel which of the cars come through. You can see some of these honeycomb comes through from the original picture. And this is the original layer 2. You notice that the layer 2, these are more straight edges. As you come to layer 3, the actual pictures or the patterns, the filters, kernel start to actually pick up more and more complex structures and patterns. As you go to layer 4, it starts to become more abstract. You can see some of the patterns of the nose and facial features of the dog. And that's really the idea. Once you get to layer 5, it's even more complex. You start to have curves and circles and whole lot of patterns start being actually observed here. This is the basic idea of CNN. You start off with the simple shapes, the edges, the corners, and start to build up more and more and more complex pattern the deeper you go into the layer itself. This is a link that I provided here. I would highly encourage you to actually watch it. I won't go through that here myself, but I'll provide that link so that you can actually open it up in your PDF to observe or at least watch his talk. This is done, if I remember correctly, last year. Yeah, might even be the year before. Yep, this actually here you can actually see, yeah, last year during the AI conference. Octavio works for Google. He is also a founder of a company. Later on was bought over by Google. He basically demonstrates to you how convolutional layer actually or CNN architecture actually work. Do watch that video just to help you to develop some intuition of it. What I wanted to do is actually show you Adam Hartley's website. Again, this is the link provided for you, and we're going to go straight to it. This is where you draw your number here, and you can actually see each layer's visibility. Okay, so what we will do here is that we will actually start drawing. Let's just say we want to draw a simple number, 1. Okay, immediately you can actually see the different layering. Okay, different so-called how each and every one of these kernel actually works. So if we show the input layer or hide it, the input layer is gone. The convolution layer, this is the first layer, we'll hide that. If we look at the downsampling, which is the max pool layer, that's now gone. If we look at the hide layer 2, so if I actually come over here, let's see if I can change it to 2D. Okay, not that it's gone too far. Okay, what we were looking at are the 3D. Let's have a look at the 2D visualization. It's easier to visualize using these. Okay, so if I draw one here, okay, so this is, the first one is the input layer. The second one, that's the convolution layer. If we look at layer number 2, you notice that, let me just hide these so that you can actually see where we are looking at. Notice that the patterns is substantially more complex as you get to convolution layer 2. And downsampling and fully connected, as you can see, is actually just one row. One row of pixel is no longer a matrix, it's just one row of pixels. That's how fully connected layer works. It's just basically one row, and that's the output layer. And notice that it did pick up correctly that it is indeed a 1. So let's start that over again. We'll start 2 now. Let's have a look at our convolution layer 2. Again, you can see that there are a few things that's being picked up here. So this picks up the bottom layer. Okay. If we look at this one, it picks up the left edges. If you look at this, it picks up the top edges. This one pick up the right edges, and this pick up the left edges. This again pick up the bottom edges. The glow, the lighten up part, are the actual edges that this layer, this kernel here actually picks up. You notice that that's basically, each of these kernel, kind of like a filter. In fact, that's the name that is also used to describe these, either a kernel or a filter. It picks up different things. Okay, you notice that there are different so-called edges are being activated or excited. You can see, as I mentioned before, this is the bottom layer, the edges, the horizontal edges, but from the bottom up. This is from the top layer, from top down. This is from right edges. This is left edges, and this is right edges, but towards the right a little bit, and also towards the left a little bit. So that's kind of like how convolution layer works. But it's substantially different when you come to the layer 2 of CNN, convolution layer. You can't really discern what it actually picks up anymore. So if we go back to this and look at how it actually connects, again, you can't really see what is actually being picked up. It comes from, notice that there are 4 sources. This comes from 4 sources, this comes from 4 sources. Yeah, so that's this comes from 3 sources. And the actual downsampling is just, instead of, if I roughly guess this is more like a 20 by 20 matrix. This go down to maybe half 10 by 10 matrix. Short of counting the matrix itself. The downsampling just reduced the number of pixels, and then the convolution layer perform another filtering over the so-called downsample layer. So that's another visualization technique to highlight to you how CNN actually works. You have the input layer, which we talked about, the input layer. Then you have 2 convolution layer, which apply different filter to it to extract key features. Max pooling is to reduce the so-called features, reduce downsampling, followed by you have another 2 convolution layer, and then further and further as you go. Right, there are other links here for you to visualize. Just now was Adam Harley's website. I also provided 2 other links for you to actually play around with it to develop further intuition. For now, that's really what I wanted to cover. Hopefully from this lesson you actually get some appreciation and understanding of how each of these convolution layer works, and then when we come back, we're going to go into the more technical part, understand all the different available types of layers and how they all work together. Welcome back everyone. In this session we're going to start digging into understanding convolution and also its neural network structure. This lesson we're going to look at a couple of properties of CNN and also how to work with images. So let's get started. One of the key characteristics of CNN is that it's called local invariance. Now once the CNNs have learned the pattern, it can recognize it anywhere, and it's also called a transitional or translational invariant. And also the other second feature is that it's compositionality. It learns spatial hierarchicals of patterns. Now let's use an example. Those are fancy words. The first layer may learn simple patterns such as vertical and horizontal edges, as we looked at in the last lesson. The second layer may learn more complex patterns that are made up of features from the first layer. This ensures that the CNN learn efficiently and doesn't duplicate what was learned before, so each layer actually picks up different features. Those are the two key properties of CNN. And others is that it operates with what's called three-dimensional tensors, or also images. If you look at it, how it works is that it has height, the first column, or rather the first input is called height, followed by the width and channels. Channels depends on the input pictures that you provide. If it's a black and white picture, then the channel will be equal to 1. If it's a red, green and blue images, or RGB, then the channel will be 3. In the example that we looked at, which is the MNIST example, it's really only black and white. The example there is 28 height, 28 width, also called 28 by 28. The channel is only 1 because there's no color for that. It's only one scale, or 8-bit, which starts from 0 and maxed out at 255. And followed by the actual filter that's being applied to it is the 3x3 filter, or also called kernel in the previous lesson that we looked at. The number of filters that was applied to it was 32. So as a result of that, what comes out at the other end is that it's 26 by 26 followed by 32 channels. And that's how a filter actually works, because there are 32 filters being applied to the same image. The output then must then be 32 filters. So what you have now is that the depth has gone from 1 to now 32 stacked together. Again, I'll show you a picture later so that you can actually see visually how it looks like. The question then is, why is it that the output feature is only 26? The reason lies with the filter. In this situation, because we didn't pad any numbers around the edges, what happened now is that the filter is only 3. It can't go hanging out at the edge. So as a result of that, you've lost 2 columns and also 2 rows. Again, I'll show that to you in the picture format so that you can visualize it. But if you can actually just work through that in your mind, it's a filter of 3 by 3. You will always lose the so-called height, or if height, for example, is n, you will actually lose all of it minus 1. The same goes with the row. Now, when you're working with pictures, this is a slight repeat of the previous slide, is that there are a few things to bear in mind. The MNIST image just now was really small. It's 28 pixels by 28 pixels, and it's only one channel because it's grayscale. So when you actually multiply 28 by 28, there's actually 784 values that you're looking at. And each of those values range from 0 to 255 because it is grayscale. However, if you're working with color images, typically they are substantially larger. And a simple image, a VGA image, kind of like pixel size, is 640 by 480. Well, not quite, it's actually 800 by 600, so this is slightly sub VGA, 640 by 480 by 3 channels. Then suddenly you find that this is 921,600 values here. And that's substantially in multitudes of scale larger than the 784 values. And 640 by 480 is not even high at all. It's not what we call a high resolution picture. And if you convert it, usually the neural network, you have fully connected layer at the end. And if you have two fully connected layers, what you have is 640 by 480 by 3 to the power of 2, and you have that astronomical number, not gastronomical, astronomical number, and that's why the computational strain on or placed on your laptop or your PC is really high when you actually start playing around with pictures, let alone videos. And what I've shown here is that this is an example of black and white scale, and below here is an example of a color scale, color image. Right, so when we come back, we're going to look at the different layer types and deconstruct them and look into them a little bit more details to help you to understand CNN altogether. Thank you again once for watching. I look forward to seeing you in the next video. Welcome back, everyone. In this segment of the video, we're going to go into the different layer types of the convolutional neural network. So there are a few types. I've listed them here for your reference. It starts from convolutional. In Keras, it's called conv2D. And then you have your activation layer. Sometimes the activation function used is ReLU. There are also a few other types as well. We will look into that. There is the pooling layer. The common pooling layers used is either max pooling or average pooling. And you have your fully connected layer. These are typically towards the end before the so-called output. There are two other layer types. Technically, these are not really layer types. They are more computational that operation that's been conducted. So they are not typically counted as layers. But nevertheless, I put it there so that as you come across them, you won't be surprised. These are batch, normalization, and also dropout. Right, so let's look at an example of a CNN architecture. If you look at this, you have your typical input followed by convolutional layer 2D and then a max pooling layer followed by another convolutional 2D layer and then another max pooling layer followed by another convolution 2D plus 2 layers of fully connected layer and finally the output. Let's dive into these one by one. We will start with input. Now this is a typical example of an image. This is a little bit contrite. It's a 10 by 10 pixel with a depth of 1. So this is an example of a grayscale or black and white picture, but with grayscale. The grayscale range from 0 to 255 in Python. In other words, 256 value to it. Now the height here is 10 pixels, the width is 10 pixels. The numbers there designate the so-called intensity of the grayscale. Let me just illustrate as an example. We looked at this and in our previous lesson. Let me zoom in. You will notice that there are numbers that comes with each of these cells here. As you move along, let me zoom over. Okay, as you move your mouse along, some reason it's not following. Okay, there you go. As you move along, you notice that it actually tracks the number. Each of these is a pixel. Each pixel has a number. That number designate or represent the actual value, determines the intensity of the grayscale of the picture. So this is a black and white or grayscale picture. White here, as you can see, is a small number. Black is actually, let me just, for some reason there's actually a delay here. Okay, let's refresh that, zoom out. Okay, there you go. Seems like when you zoom in, it doesn't work so well. Black is a small number. White is actually closer and closer to 255. So the larger the number, the closer it is to white. The darker it is, the lower the number, the closer it is to black. Right, so that's really what I wanted to highlight to you. If you can imagine, this is a little bit like the features under the machine learning. So these are what we actually feed into the neural network. Every picture you feed into the neural network, and the neural network will actually start to decipher the so-called characteristics, distinctive edges, and the characteristics of each of these input image. Now, this is an example of a picture that has color. It consists of 3 channels, the R, G, and B channel. And if you look at this 1, 2, 3, that is also represented as depth. Again, this is still a 10 by 10 pixels picture, except the difference now is that you have 3 channels. Now, each channel represents each of the R, G, or B, and the value determines the intensity of the red, the green, and blue. And when you combine them, it gives you a different color. So that's really how the 3 layers or 3 channel actually work. So you can pay attention to this picture here. You can see it's 10 by 10 followed by 3 layers deep. So this is a typical example of an image, color image. Let's move into max pooling, convolution 2D operation. So we're looking at convolution 2D operation now. And what we will do is that I think it's best that we cover this. We will move into convolution 2D layers in the next video. Thank you for watching. Welcome back. Let's dive into convolution 2D and the actual operation of it. Alright, so this is an example of a convolution operation. You can see the kernel, which is designated by the light purple, where the top row is represented by -1, -2, and -1. The second row is 0, 0, 0, and then the third row is 1, 2, 1. So in this case, this is our kernel that's being applied to the image. Well, this image is a 4 by 6, 4 by 6 in terms of the dimension, and is grayscale. You will notice that the height is 4 and the width is actually 6 in this case. Now, the other thing that I do want to highlight, if you keep looking at the so-called details here, is that the operation works like this. You apply the kernel onto the 3 by 3 filter or kernel onto the image, the top. Start with the top corner, the 3 by 3 portion of the image itself, and then you follow by element-wise multiplication. So the -1 multiply 10, which I've actually laid out here as an example for you, followed by -2, which is from the kernel, multiplied by 12 from the image, -1 multiplied by the 3, a value of 3 in the image. And notice that these are all individual element-wise multiplication, and then you sum them up. So that's why this descriptor here says sum of element-wise multiplication. I've provided this as a convolution operation spreadsheet in the form of a spreadsheet under stride is equal to 1 worksheet. If you look at this, so basically we have this kernel applied to this portion, okay, of the image, and the output here is 19, which is the value that we received here. So let us flip over to the spreadsheet that I've provided here. Stride is equal to 1, and this is the actual computation. And if you look at the formula, which is pretty much the example that I've shown you earlier, including the actual working itself. So if you move to the next cell, it shows you that the kernel, the filter now has been slide along. Okay, the stride is 1, so it's been slide along to the next column. And you keep repeating this until you come to the end of the image. And you'll notice very quickly that we can only go as far as 4 in terms of the output. Although the image has 6 in terms of width, but the output is only 4. The reason, as you can see, pretty obvious really, is that the 3x3 cannot be applied outside. Okay, once you actually move one more, slide along by one more pixel, then you actually start applying it to outside of the image, and that will not work, and it's not possible to do that. Hence, the image dimension or the output size has been reduced from 4 times 6, 4 is our height, 6 is our width, to 2 times 4. Height is now 2, 4 is the width. And every time when you actually apply 3x3, you will lose 2 columns and 2 rows. And if you apply 5x5, you will lose 4 columns and 4 rows. So that's basically how the actual calculation in terms of the output works. Now this is also an example of applying the kernel filter without padding. What we did just now is essentially this is the same as the previous slide. There's no difference here. I just wanted to highlight that this is an example of applying the kernel filter without padding. Okay, and I also want to illustrate to you what it looks like when you actually apply padding. But before we go there, let's look at what happens if you apply multiple filters. In this example, we only apply one filter. What happens when you apply multiple filters? Quite often, in CNN, the architecture itself, you apply multiple layers, and quite often somewhere between 32, 64, or even higher. And in those situations when you apply multiple filters or multiple kernels, you will obtain multiple outputs. Let's take an example first of all and look at the CNN that we actually looked at earlier for one of some of our examples. You notice that this is convolution 2D. It's started off with 3x3. This is the kernel. Okay, the dimension of the kernel is 3 pixel high and 3 pixel wide. And just pay attention for now to the first two values, 32, and then bracket the tuple 3, The 32 is the actual number of filters being applied. So in this case, the first convolution layer applied 32 filters. So you will receive 32 outputs. Okay, and the next convolution layer, you can see it says 64 followed by a 3, 3. So there's still a 3x3 kernel matrix, and the difference now is that you have 64 kernels or 64 filters being applied, so the number of layers will increase by 64. And let's look at the so-called output that's provided by Keras. Couple of things I want to highlight. Notice that the input picture is 28 by 28. After we apply the 3x3 matrix, the filter, what you receive is 26 by 26 in terms of the output dimension. Okay, now you notice that the number, remember that the picture is only a grayscale, so it's only one channel. After you apply the kernel, 32 kernel, activation map is also called, what you receive now is that you have a dimension of 26 by 26, but now you have 32 layer deep of output. And if you continue to go to, I just want to highlight this, so this is a 26 by 26 shape, and we have 32. Recall that when we actually applied the image before, it was only 1. Okay, the input shape is 28 by 28 and only 1 grayscale. But the output, after going through this convolution layer, is that you receive now 32 in terms of the so-called 32 output layers. Ignore the max pooling for now, we'll cover that in future lesson. And when you actually apply another convolution layer onto the output of the max pooling layer, you notice that we reduce by 2 rows and reduce by 2 columns. and now the convolution increased to 64, and on it goes. Now if you want to maintain the dimension, input dimension is 28 and the output dimension is still 28 by 28, and then you use padding is equal to the same, okay, in Keras. So, and this way you actually put it in here, there's another comma, padding is equal to the same. Right, so this is a pictorial example of what we discussed. If you look at this, in the code example provided above, 32 filters were used. There will be 32 output. Hence, we have 32 copies of the 26 image, but the copies aren't the same because of the different kernels being applied to it. So you actually get a 32 activation map. And so this is an example of when you apply one filter. This is only example of one, but if you apply 32, you will get 32. There isn't a 32 here, by the way. It's just as it is just an example of the output ought to be 32 activation maps. There are some common filters or kernels that you have seen before. You have sharpen, you have blur, and you have bottom Sobel. And there's actually a link here I provided here for you to actually refer to. In fact, you've seen this before. Here are some of the examples. There are a few here. In fact, I borrowed the examples of those numbers that actually from here. So we were looking at sharpen. So let's look at sharpen. If you select sharpen, so this is sharpen. If you apply, let's just say blur. Did we choose blur? Yep. These are the numbers or values in blur. And yeah, and on it goes. So these are the common filter, but of course these are handcrafted, and it's time consuming to handcraft it, manually craft it yourself. And if you leave it to the CNN, it will actually design according to the input image, and it will learn by itself. That's the beauty of deep neural network. All right, let's look at how you use this in Keras. There are a couple of things that I do want you to take note of. The depth of the outputs relates to the number of filters. Recall that in the code that we look at, it was 32. There's also another parameters that's important, which is strides. Right now the default is 1, 1, meaning height of 1 and the width of 1. Quite often people just leave 1 there, meaning it's 1 for both height and width. You can actually have different numbers, 2 for the height and 1 for the width if that's what you want. But generally it's just left as a scalar value. Scalar meaning just one value, and that will mean or translate to it's the same for both the height and width. Now you can also apply a number that is greater than 1. That will mean that you actually start skipping pixel now. 1 basically means move to the next pixel, but if you put 2, it starts skipping 1 pixel. If you put 3, it's skipping 2 pixels. And the outcome of that is that it will reduce the size of the output. And padding, or more accurately zero padding, adds 0 to the external dimension, okay, so that you can actually recover the same dimension as the so-called output. Now if you look at some examples on the strides, I've chosen height of 1 and width is equal to 2, and this is an example of stride of 2. If you look at this, initially we are applying to this, but the next one no longer apply to 12, instead is skip 1 pixel and go over to 3, this column here. That this is an example of height is equal to 1 and width is equal to 2. The width 2 here meaning that we are skipping 1 pixel. So essentially it skipped column number 2 here. Again, I've provided this in the form of an Excel spreadsheet. You can actually go to stride 2 equal to 2 tab, and this is the actual calculation itself. You can see that it's applied to 10, 12, and 3. If we come over to the next one, the output it doesn't actually apply to 12, it's just go to 3, 4, and 3. And it's stopped there, it doesn't actually continue on because the next one is supposed to skip 4 and then go to 3, but there's not enough you're starting to move outside the picture, so it no longer works. Okay, so play around with that. So this is kind of like a, well, in a way, a slow motion picture that I want to show you. You can actually go back to the spreadsheet to actually see how it's done. So we are applying a 3x3 filter, okay, to a 10x10 matrix. The stride is 1. So, right, so the green highlighted matrix, the 3x3 matrix, is where the filter is being applied to. The next slide shows you it's moved to the next one, and the next one, and the next one. Notice that it's just stepping to the next, then the next, and the next. Okay, now you have output of 8 times 8. Okay, so that's the basic idea if you move along in terms of the stride is equal to 1. So let's look at an example with stride is equal to 2. Now instead of green, the filter now is purple. Take a moment, have a guess. Where should it move to? Yes, if you say the column that starts with 3, you'll be right. Okay, it will continue to actually move to the next, but skipping 1 pixel continuously. Right, in terms of the output size, there are some things to actually take note of. This is a formula that's continuously, or rather commonly used in papers. The N is the so-called number of columns in terms of width, minus F, F is the filter, divided by the stride plus 1. So that's essentially how it works. And here's the example of N is equal to 10, F is equal to 3. So if the stride is 1, then you have 10 minus 3, the answer becomes 7 divided by 1 plus 1, you get 8 is the output size. And if you have a stride of 2, your output size becomes 4.5. Of course, you can't have 4.5, so it becomes 4. Okay, so it goes down, it rounds down. All right, the next slide that I want to cover before we stop this video is zero padding. Zero padding is this is our original 10x10 pixels. The slight variation is that we've added 0 on the edge. Okay, the 0 on the side. Sorry, this is not the 10x10. This is the 4x6. My apologies. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. And notice that we added 0 all around it. And now we can recover the original size of 4x6. Okay. And that's the critical part of zero padding. In Keras, you put padding is equal to same, and that's how you actually recover the same dimension as per your input. Again, I provided it in terms of the zero padding tab. You can actually look at this. The calculation is the same. It's still element-wise, and then you sum them up. The difference now is because there's an extra. These are the so-called layer that's being applied, the zero padding. Let me just highlight that so that it's easier for you to visualize. The zero padding there allows you to actually recover the original size of the input picture. The original size is 4x6 and the output is also 4x6. Right, that's really the end of our lesson. When we come back, I'm going to dig into the activation function a little bit to help you to understand what it is and how it works and what's the purpose of using it. Thank you once again for watching. Welcome back, everyone. In this segment, we're going to look at some of the common activation function. A lot of these should be quite familiar to you in some ways, hopefully. Let's start with the sigmoid function, and notice that it squeezed the output to 0 and 1, to between 0 and 1. Hence, sigmoid is quite often used in binary classification. Tangent H, on the other hand, squeezed the output to between -1 and 1. And ReLU, for those who come from finance background, will look at this and say, that looks a lot like a call option. But you are indeed right. It basically looks exactly like a call option with a strike of 0. anything less than 0, it will just convert the value to 0 in terms of the output, and after that it just increase in a gradual manner. Leaky ReLU, on the other hand, notice that there are some negative values being leaked, double quote, through, and followed by ELU, okay, exponential linear unit. And let's look at some example. In terms of the mathematical formulation, is equal to max bracket 0 or B3. So anything less than 0, it will default to 0. If it's greater than 0, it will be the value in B3. So that's basically how this actually works. So as you move along, that's basically the actual ReLU function is being applied to each and every one of these scalar value here. Sigmoid is the same in terms of the formula is 1 divided by 1 plus exponent of minus x. That's essentially the sigmoid function. And ReLU, on the other hand, applies the same. And then you have leaky ReLU. We already saw ReLU, so let's look at leaky. The leaky ReLU has 0.1 multiplied by the x input. This is the leaky part, but the 0.1 is up to you to set. Quite often it's being set to 0.1. You can actually have a lower value if you want to, and the basic idea here is so that there are some value being leaked through here. In the spreadsheet here, I've provided all the pictures. Well, if you want black and white, there's that one. If you want color, it's that one. You can actually go in and look at how I actually calculate all of these. The leaky ReLU is provided here as well, and then as well as the ELU. Okay, so with that, that's really what I wanted to highlight. Thank you again for watching. I hope this really quick run through gives you a sense of it. I won't go into the equation itself. You can actually find that quite easily just doing a simple Googling deep learning activation function and then type the one that you're looking for, whether ELU, leaky ReLU or ReLU. But the basic idea here is to look at the output function, the output of the activation function, and get some sense of what these functions attempt to do with your input. And what this does is actually it expedite the process and actually help you to actually convert it to 0 if it's negative, so that the layer that's being applied to your input data later on can perform the computation better. And some of these, in particular ReLU, which is extremely popular, is used quite a lot more now because it actually allows backpropagation to be calculated quickly instead of using the original tangent H. Right, a little bit more on the activation function. If we pass the output layer that's shown on the right through a ReLU activation function, so the output layer, this one here, you will obtain the same result. That's because ReLU is, how ReLU works is that it zero any negative numbers and leave positive numbers alone. Usually it follows straight after convolutional layer. Often that is not specified in the architecture itself. If we go back to the Keras, let me just see if I can go back here, this one here. Notice these are the activation is equal to ReLU. You can specify others if you want to, but in essence, this is actually straight after the convolution layer. It's usually not treated as a separate layer. It's just as the output that comes out of the convolution layer, a ReLU function is applied to it. You notice there in this summary of the CNN architecture, there's no mention of ReLU. Okay. Right, these are the other so-called activation function. These are the output plus the activation function with the different values that come out of it. I've given a couple of examples here. The first one is the one that you've seen earlier. The second one is to illustrate to you when you feed negative value into ReLU, you get 0, 0 because there are negative values here. If you apply these to sigmoid, it squeezes it to between 0 and 1. And if you apply this to leaky ReLU, this is actually the output that you see. No longer does it actually convert it to 0. It does allow some of the negative values being leaked through. Alright, that's pretty much what I wanted to cover when it comes to activation function. When we come back, we're going to look at the pooling layer. Welcome back everyone. In this segment, we're going to start looking at a few more distinguished and unique characteristics of several types of layers. This is towards the end of the different type of layers. In this segment, we're going to look at pooling layer, the fully connected, and the flattened, just to wrap it up. So let's start with pooling layer. This is an example of max pooling. There are two common types, average pooling or max pooling. The idea here, it applies to each activation map independently. The purpose of pooling is to reduce the size or spatial size or the representation. It speeds up the computation layer so that there's not so many calculations that needs to be done, and it helps control overfitting as well. Now, if you think about what is the purpose of max pooling, the basic idea is that you take the maximum value in this case in the 2x2 matrix. What that is doing is that you are actually just taking the most outstanding value and take that as the representation of that small 4 pixels or 2x2 matrix. Looking at the pictures that we have here, there are two outputs. The top one with the stride of 2, the bottom one with the stride of 1. So let's look at the one with the stride of 2. And you do need to follow along with the color. The color represents the original or origin of the maximum value. So if we take this portion here, this is the first application of the max pooling. Within this 2x2 matrix, you can see that value is 12 is the highest, hence you have that. Because the stride is 2, you skip this and you come over here, and again you look at this 2x2 matrix and take the highest value, which is 5. And now because the stride is 2, you skip this row and you come to this row, you're looking at this, then you'll notice that the maximum value here is 22 followed by 32. So that's basically max pooling with 2x2 filter with the stride of 2. What happens if the stride is actually 1? So the first one will be the same, but you move along to 12 and you're now looking at this matrix here. Okay, this matrix, the highest value is 12, hence it's 12. And you move along by 1, the highest value here is 5, hence you have 5. And you move down here, within this 2x2 matrix, the highest value is 22, and it's 22. And then let me just move along one more, just basically finish this row. And you look at this 2x2, the highest value is 12, hence it's 12. And if you look at this 2x2, the highest value is 10. Then you move down by 1 pixel, looking at this, the highest value is 22. So looking at a stride of 1, you get a lot more overlaps. That's why when you look at the so-called output, there are a few 12 that's being repeated there. There's a few 22, there's a few 32. These are all repetition. If you really want to reduce the size, then you choose a larger stride like the one on top, whereby all the highest value is represented. Those are the so-called high intensity, I suppose you can call it from a slightly different angle. But the idea here is that it picks up the key features. So that's basically what I want to cover regards to pooling. Let's move to the next one, which is flatten. The basic idea of flatten is that the classifier that we will apply next, which could be a sigmoid, could be a linear regression, logistic regression, or softmax and the likes. This allowed the classifier to convert it into class. Otherwise, if you have a matrix structure, then these functions can't handle it. So hence we actually convert it into a one-dimensional format. So where you have, let's just take this instead of 2 by 2, which is 12, 5, and then followed by another row 22, 32. It becomes 12, 5, 22, 32, one long string of numbers, and you apply the sigmoid or the softmax depending on your intention, or whether there's actually multiple classes or only binary classification. Okay, so that's pretty much for the flattened layer, and we have the fully connected layer, which is very common right throughout artificial neural network, ANN. And if you look at this fully connected layer, it's also called dense layer, whereby every neuron from previous layer is connected to every neuron in the current layer and the next layer, and on it goes. If you look at this, you can see that it's extremely busy in terms of the picture. So this connects to all the neuron. Likewise, this connects to all 4 neurons. If you have 52 neurons, you can see what it means, or why do they actually call this dense layer, and also the rationale of calling it fully connected, because they are connected to every single one of them. Normally in the modern day architecture of CNN, you usually observe this at the end of the neural network. Right, so we come to the end of all the different layers. There is this convolution neural network, but this one is written in JavaScript by Karpathy. Karpathy was the professor in Stanford. He still pops in every now and then, I believe. But now he's, if I follow along correctly, as of in 2018, he is in Tesla working on their self-driving or autonomous cars. So this is what he created when he was actually teaching in Stanford. This is based on the CIFAR 10, which is 10 classes datasets. It's all pictures. And this scripts here, or the JavaScripts, demonstrate to you how CNN actually work. It's quite a good visualization technique, allows you to see end-to-end how it works. You can, let me just zoom in here. In terms of the loss functions, this you can choose the learning rate. You can also choose the actual momentum, which we haven't talked about. It's instead of stochastic gradient descent, it applies momentum trainer to it, and then you can choose the batch size. You can also change the weight decay. This is to actually allow the so-called finer grain training as well. This is training from ground up, meaning starting from 0. You can also load pre-trained networks just by clicking this and wait for a while. It will just refresh and start again. And the pre-trained network has accuracy of approximately 80%. This is what the so-called layer look like, neural network architecture look like. You have the input, you have the convolution layer, convolution, pooling, and then softmax finally. In terms of visualization, you have the input, okay, and this is what the activation function or pictures looks like, and you notice that these are the different filters, and these are the gradients, these are the weights, and these are again the ReLU, again an activation gradient, and this is the max pooling, this is convolution, and on it goes. It actually highlights all the multiple layers and what it looks like, and to help you to actually see that. And these are the so-called example prediction. Okay, it got the truck correct, the dog correct. There's the dog, yes. This is the ship, and also shows you how confident it is. Something like this is not very confident. This is a horse. Notice I got it wrong. This is a frog, but it actually called it a ship. Yeah, so it tells you the first 3 classifications, the top 3 classifications, whether they are right or wrong. Green means it's actually correct. That's the correct class. If it's top, that means it actually classified that correctly. Yeah, so there are a whole lot of intuition that you can develop out of playing around with this, I highly encourage you. I mean, it's not a very complicated architecture, CNN architecture, but it definitely will help you in terms of developing your intuition with it. So it's really screaming. My Mac is screaming now because it's actually using my the CPU to actually do the calculation. So 1, 2, 3 convolution with pulling in between, and the activation function all ReLU. So 1 convolution, 1 ReLU, and then you have a pulling convolution, ReLU, pulling convolution, ReLU, pulling, and then fully connected layer and softmax. Right, with that, let me just close that off because it's really heating up my Mac. And yeah, so this is basically what we've covered right throughout this whole series of lessons in terms of the different layers. Let me go back to the architecture that we looked at. We covered the input layer, which is the image that is made out of pixels. If it's grayscale, then it's only 1 layer. If it's color, then you have the RGB, 3 layers or 3 channels. We talked about convolution. We talked about pulling layer. We talked about the flatten, the purpose of flatten. And we also talked about the densely connected layer. And yeah, that's pretty much everything that we've covered. I hope you have found that extremely useful. These are all the different layers we covered. Thank you once again for watching. I look forward to seeing you in the next lesson. Welcome back, everyone. Let's get started with training your own CNN. Instead of learning all the contents only, or the principles and concepts, we're going to dig right into training your own CNN right now. So before we get started, the first thing that we need to do is get some data. The Kaggle is where we're going to head to for the data. It's called Dogs and Cats Redux. If you actually click onto the link, which I provide as a PDF, will bring to you this website here by Kaggle. Now, Kaggle is owned by Google now. What they have done here is that they provided images of dogs and cats. As you know, in our previous lessons, is that if you're going to train any deep learning neural network, you must have data. So we are heading to Kaggle for this data. Now let's walk through the Kaggle dashboard so that you are comfortable with it. This is the Kaggle Dogs versus Cats Redux. This is the kernel's edition. So you have the overview, which provide the background in terms of what these tasks entails. You have the leaderboards, the kernels, as well as discussion topics. So you can actually have a look at the kernels. There's a few people who are happy to share their results with codes as well for you to look through. In terms of the data, this is what we are interested in. You can actually click download. And the download, before you download, you do need to actually sign in to the Kaggle account that you have. If you don't have an account, feel free to actually register one. You do unfortunately need to register before you can actually obtain a copy of it. Now, the next thing is that there are kernels. There are a few that people are happy to share. I have my own work here and some favorites. There are a few discussion boards that people want to discuss. This is always a great way to actually get started with learning. And finally, the leaderboards. If you look at the public leaderboards, and you can look at some of the scores and benchmark yourself against that. Right. Now, for this exercise, what I have done is actually I've already downloaded this for you. If you go to the folder, there will be the directories. There is actually a folder called data. If you go into data, the actual download the data from Kaggle, which is these data source here. You have the test and then you have the train. What I have done with the data is that I've downloaded these two, the test and train. I only place the training data here. The training is the full set of data. where that's provided by Kaggle. It does take a wee while to open because there are a lot of data in there. Okay, let me just go there from another direction. This is the folder. Let me bring it across. Okay, and if you go into the data under training, these are all the pictures. Okay, and what I have done there you go, this has come up. These are all the data. You can actually scroll to the pictures if you like. Let's go back to data. Let me just close that off. You may ask that why is there two other folders? These two folders are the sample data that I extracted out of the training original data sets from Kaggle. Now this is too large, rather it's not too large, it's just quite large, and it takes a while for the training to be completed. What I wanted to do is actually just to illustrate to you in terms of the process of how this can be done. And so there's no point, especially when you're actually performing the investigation part, to actually use the whole data set. It's better that you actually get your model up and running before you actually run your complete training, your training on the complete data set. It's better to use a small sample, a couple of thousand pictures, to play around with your neural network architecture. And once you're happy with it, then train it on the full data set. The reason is that loading these pictures, especially when you have a lot of them, the training time can be quite substantial. In fact, it can take up to weeks if you are not mindful of that. So optimizing your time and being mindful of that is really important. So let me just Control B to minimize that, or Command B in Mac. So let's walk through these codes that I've provided. This is called 101 Cats and Dogs .ipython notebook. So if you look at this, some of these comments are originally from Kaggle. I'm going to leave it there. We've imported NumPy. This is for linear algebra and also computation. We've imported pandas and also CV2. This is computer vision 2. I won't actually walk through and explain what is CV2. It's an API on its own. It's actually an open source library. There's a lot of useful information in there, especially when it comes to manipulating images and videos. Of course, we make use of the usual matplotlib.pyplot for plotting purpose. The style that we're using is ggplot, popularized by R. And we're importing scikit-learn model selection to split our data into training as well as test set. And we are gonna work with images that has height of 128 pixels and width of 128 pixels. You can ignore these comments. We're importing two more packages. One is import OS, the other one is import shutil for file copying. Right, if you're running, and when you're running this for the first time, you do need to actually copy these into these two folders. Now you don't have to do that yourself. I've already written the code for you. First thing you need to do before you copy the file is that you do need to create the directories. That's what these are for. The source data underscore dir here, which is this line of code, points your code or inform Python that the source folder is within data and the folder called train. The next thing is try. When you actually try to create a directory that already exists, you will get an error message. Okay, that's why I used the try. If there's an error, it basically means that the directory already has been created. Then don't skip that whole portion altogether, skip those steps altogether. So I have 4 things here. One is basically using the OS package, operating system, to make directory. We are trying to make training set, or split our data into training set as well as the validation set. We have within the training set another subfolder called cats and a subfolder called dogs. That's where we're going to place all of the images of our cats and dogs. And the validation set is for validating our model. Again, we have cats and dogs for that. So this first portion of the code is try to make this directory. That's what the mkdir stands for, is try to make the directory. Failing that, meaning under the situation whereby the directory is already created, an error will be thrown up, then this is where the catching of the exception comes in to pass. Meaning the meaning of pass is that don't perform the above codes at all. The next thing is we perform listing of the directory, the files in the data folder, the subfolder trainings underscore set, and cats folder. This list directory is such that we're running this line of code if OS list directory is equal to blank, all right, meaning that folder doesn't have any pictures, then perform the following. Again, what you don't want to do is that every time when you run the codes, this get run and then you're copying many pictures, and quite often the same pictures being copied over. You don't want to do that. Hence, I have this if statement. If the copying has already been done, then don't copy anymore. So hence the comment there that says if the folder contains no picture, then start copying. Right, what are we doing? Let me just minimize it. We are copying 2000 cat pictures and copying from the source data directory, data which is defined here, data underscore or backslash train. We're copying cat's picture from the source directory to the training directory. Again, we'll copy another 2000 pictures of dogs, all right, from the source directory to the training set directory and the subfolder called dogs. Again, we copy 500 pictures, all right, the pictures that has the name from 2000 to 2500, copying from the source directory to the cats validation subfolder or validation subfolder cats. Again, we do the same with the dogs. So essentially, what are these few line of codes as doing? What we are doing here is that we're copying 2000 pictures, put it in the training directory under cats and dogs respectively, and then we're copying another 500 for cats and dogs and park them under the validation. Then the question is, what is this line of code mean? Right, this is basically a for statement for I in range 2000. When you use the range command, basically it will provide iteration of 0, 1, 2, 3, essentially a list. So when you actually run the for loop, I becomes 0, 1, 2, 3. And this part here is just basically creating the file name called cat.0.jpg, cat.1.jpg, cat.2.jpg, on and on it goes for the first 2000. So we're creating these. This will become, because you can see here there's a bracket, so that's a list comprehension. So you have created a list containing cat.0.jpg, comma, cat.1.jpg, on and on it goes for the first 2000. It will stop at cat.1999.jpg. So basically we have 2000 file names there, and we're running another for loop here, looping over the list. So basically the next part here is asking or telling Python to copy these files from the source directory to the training directory with cats. If we come over here, you notice that the name is indeed cat.0.jpg, so we know what the file names looks like, and then we copy it over. Let's go to training set. You notice the directory structure is that there's two subfolders, cats and dogs. If I click cats, you notice that the pictures has been copied over, and there are 2000 items in this folder. For the dog, likewise .dog.0, likewise 2000. It's always good to visually check this just to make sure that everything has been done in accordance to your wish and what you require. And that's basically what I want to cover here. This is really the preparation before the data pre-processing. What we've done here literally is create the data set for us to start training our model, but there are some more things that we need to do in terms of preparing our data as well as creating the neural network. We'll do that in the next video. Thank you once again for watching. Welcome back. In our previous session, we downloaded the data from Kaggle and followed by splitting our data in our local directory into training as well as validation. In the training, we have cats and dogs folder, and then also in the validation, we also have cats and dog folder. Now the question that you might ask is that why do we do that? Why don't we just leave them all in one big giant folder and zip through it when you're training your CNN? The reason is quite simple. When you're actually processing images, they are quite large. Each image may be 2 megabytes or even up to 5 megabytes, depending on the so-called quality that you took the picture in or with. Now, when you actually have 2000 of these pictures, and you can actually quickly see how quickly this will actually run out memory. Okay, and of course there's also the training portion, the computation portion, all the overheads involved. It will run out memory very quickly. 2000 pictures is not a lot. Quite often people work with 10,000, 100,000 pictures, and you can quickly see that this is just not gonna work. You just don't have enough memory to actually process all of these. So what people have come up with is that they actually organize it into directory structure like this, so that when you actually come around and start training all of your CNN with all the data, then you have the proper directory structure to actually sample some of the data in batches instead of trying to actually sort it out within your codes. Right, let's get started with the definition of our CNN. This is our architecture. We are using Keras, of course. Now from Keras, if you look at this, we are importing layers. From layers, we're importing convolution 2D. We are also importing max pooling, again 2D, flatten, and also dense. We talked about this in previous session. If you find that you're not familiar with them, please go back and pull up the notes. From Keras, we're importing the models to actually define our CNN, our architecture. Right, so we're instantiating a model is equal to models.sequential, so we're using a sequential model. Right, so the first line of code here basically say we are creating a convolution layer, and for the convolution layer we're applying 32 filters or kernels, and it's 3 by 3 in terms of the kernel size. And also after that's done, they apply an activation, a ReLU activation layer. And also the input shape was defined earlier. Remember, I defined rows and columns as 128 by 128. And 3 here basically say it's a channel of 3, which is RGB. And then the followed by, we are working with a max pooling. Okay, the next layer that we're adding is max pooling 2 by 2. Let me go back a little bit, take a step back. Previously, when we're looking at MNIST data, is the grayscale, hence the channel is 1. But we're working with colored pictures, as you saw the cat picture earlier, is in color. So for that, you will have to actually, well, basically if this is color, it has to be in RGB. All right, so that's why the channel is 3 here. Right, so we have 2 layers defined. We have a convolution layer. At the output of the convolution layer, there's an activation function being applied to it. The next layer will be the max pooling layer, and then we're applying a convolution, another convolution, this time 64 filters, and each of these filters have a dimension of 3 by 3, Again, the output of this, we apply another ReLU activation layer, and then another max pooling, again to shrink the size, followed by another convolution with 64 filter, 3x3 matrix, activation is ReLU, again another max pooling layer. Finally, we applied the flatten function to convert our 2x2 matrix into, or actually is 2 by 2 by how deep our channel is, and then we flatten it, followed by applying two densely connected layer or fully connected layer, also called dense. The first dense layer we apply ReLU to actually expedite the so-called processing, basically convert all the negative value to 0, and then we apply a sigmoid function because we have a binary decision here, either it's a cat or a dog. Right, that's it. That's really our architecture for the CNN, and we are defined, or rather we print the model summary out to this screen here. This is a very simple CNN. The reason we've chosen this is so that we can actually have a reasonable training time for learning purpose. I don't want to be babysitting this a day later. When you start defining architecture that's quite deep, it can take a week, 2 weeks, depending on the hardware that you have, and also how much data you have and how deep the architecture. Recall that let's quickly summarize this. This is a very simple architecture. It's not based on anything. It's just a very simple convolution, just so that we can actually get a really good feel of how CNN works. Recall that our input image shape is 128 by 128. Right, this is after the first convolution layer. The output is now 126 by 126 because we have a 3x3, and we have 32 because the filter is 32, and then followed by a max pooling layer to reduce the size because it's a max pool with 2x2, 2 heights and 2 width, so basically the stride is 2, so it basically halved it. Followed by another convolution layer, again because it's 3x3, so you lose 2 for the height and width, and we apply another 32 filter, so that becomes 64, max pooling, and on it goes. Right, so that's really the architecture. Right, the next thing, of course, we need to actually have an optimizer. So from Keras we import the optimizer. This is a binary decision, so we're using a binary cross entropy, and the optimizer we're using RMS prop. Followed by the performance measurement matrix is accuracy, which is ACC here. Right, having done all that, we of course need to compile our image. We haven't done that yet. We'll do that a little later. Sorry, that's the compile. I should just highlight that part is the compilation part. Okay, right. The next thing that we need to do is do some pre-processing with our image. Recall that we talked about the neural network requires data, or works best with data that's between 0 and 1, or between -1 and 1. And these images, because they are color, even grayscale as well, it will range from 0 to 255. So that's why we need to actually rescale them to between 0 and 1. So first of all, from Keras we import pre-processing image. And specifically what we're actually interested in is in image data generator. We're splitting our data into training and validation, and in terms of the so-called rescaling we're doing here, this is the part here we just divided by 255 so that it's between 0 and 1. So for the training data, we call it train data generation and x_train_ data gen. We are actually flow_flum directory. This is directly from Keras library. It has this function called flow_from directory, meaning as we need the data, okay, retrieve from the directory. This is really good. Instead of you having to actually write a for loop, this has already been done for you. So we are extracting the data from the training set folder. And the target size is, as we defined earlier, 128 by 128, 128 rows and 128 columns. And each time we're gonna draw a batch of 40 samples, and let the CNN train on it. And the class mode defined here is binary because we are working with binary decision whether it's a cat or a dog. Right, so that's really the so-called using Keras flow from directory. If you are not using Keras, you basically have to do a for loop to retrieve the number of pictures. Right, so we repeat the same with the validation. This time around, we specify the data folder being data, backstroke, backslash, validation set. Again, the target size is 128 by 128, batch size 40, and class mode is 40. All right, so that's really how we actually define all of these, and Keras discovered that it's 4,000 images, and that's for the training. That's the output from the train underscore data gen here, and found another 1,000. Remember, it's 500 for cats, 500 for dogs. That will be for the validation. Okay, so the next portion really is the training. We start with the training. So for here, we have epoch equal to 30. So we're allowing our CNN to see the data 30 times, all of the data 30 times. And in terms of the fitting, it's a little bit different from what we used to do. We used to just use fit. This time we're using fit generator because we are using the data generator from before, which is flow from directory, the image data generator. Essentially, this image data generator does two things. One is, notice the rescaling part, dividing the data to 255, that's the first part. Second part is that it, from the data directory, it draw the samples for training. Okay, so what we have here, we're providing the training data gen, which is defined here, training data gen or train data gen, and the steps per epoch is 100. The reason is 100 is that we need to explain, because the problem now is that Keras does not know when is, how do you count one epoch. We want to do 30 epoch, but it doesn't know how many images that we have, so it does not know. So we need to define it for Keras. Remember, we're drawing a batch size of 40. We have 4,000 images. If we're drawing 40 at a time, how long would it take, or how many times, how many iterations before you use up all the images? 100, correct. That's where the 100 steps comes in. After 100 steps, meaning 100 loops through, every time we're drawing 40, then we've finished using all of the training data, at least in the sample training data. Hence, this will be counted as one epoch. This is to let Keras know how to actually count epoch. And for the epochs is equal to epochs, which is 30 here. Validation is equal to val data gen, which we created here, and the validation steps is equal to 50. All right, so this is the actual training. You notice that the so-called accuracy starts at 55%, validation is higher, and it ended around 98% accuracy, but validation basically stopped rising, plateau around 77 to 79%. All right, let me run through a few more line of codes before we look at the result. Now, h.history is basically, when we're actually running this training, we store it into this variable called h. This is to allow us to extract a few important values. One is the accuracy of the training. The other one is the validation accuracy, which is what this first two line is, followed by the history of the loss, the training loss, and the validation loss. So we're storing all of these variables so that we can actually plot it later. Right, so this line of code basically to allow us to actually draw the x-axis. The epochs here basically defined by range, starting with 1, and the length of the ACC, the length of the accuracy, which is defined here. So if we have run 30 epochs, it means that we will have 30 accuracy values. So literally we are telling the epochs, or storing in epochs, there will be a range from 1 all the way to 30. 30 here in this case, instead of 29. So we take the length, which is 30, and then plus 1. Remember, Python when it generates this range, which is a list, it will stop with the last value minus 1. The last value here, because it's 31 minus 1, meaning it will stop the number at 30. Right, we're plotting this, okay, using Matplotlib, plotting the epochs, which is the x value, followed by the accuracy, and it's blue dot, and we label this training accuracy. We're plotting the validation accuracy, and the x is the epochs, the y will be the validation accuracy, and the line will be green, and we call this title training and validation accuracy, and then plot the legend as well. So this is the first chart here. The blue dot as defined here is the training accuracy. As you can see, the more times that it sees the data, the accuracy improves as it goes. But of course, when you're actually training a neural network or any machine learning for that matter, you are interested in whether it is accurate out of sample in the test set. In this case, we are not touching the test set, we just want to validate it before we actually move on to a test set. So for now, because we're tuning our model, so we're interested only to see the validation. And you can see that the validation, as I mentioned earlier, plateau. Okay, it's not rising any further. What that really means is that after about 5 epochs, that's it. Our model has already learned all the characteristics, or the capacity has already been reached in terms of learning the nuances of the training data. So after that, anything beyond that is basically overfitting. All right, it's not able to predict the pictures as accurate outside of sample using the validation data that we've created. Right, the second picture is to plot the loss. The first one is accuracy, the second one is loss. Again, plotting training loss versus validation loss. The blue dot will be our training loss. The green line will be our validation loss. Okay, so that's the second picture here. As you can see, in the training loss, it continued to drop. But the validation loss dropped until around 5th epoch, and after that it just plateaued. In fact, the error started going up. And the reason for that is very simple. It's because it's overfitting, that's one. And it's just not able to generalize. That's the second reason. When it comes to data that has not seen before, it's just not able to predict, really is overfitting the training data. That's really how you actually run or train your own CNN. It's a very simple model. It's really quick. It allows you to get up to speed very, very quickly. Now, one other thing though is that after you finish training, you are happy with your model, what do? Do you actually have to run training every single time? The simple answer to that is no, you don't. Then the next question is, can I save my model? And I'm sure you know the answer by now is yes, you can. And this is how Keras made it really simple. It's just model.save within the bracket and apostrophe, you provide a name for your model. We call it cats_n_docs.h5 so that we can retrieve it later and start forecasting and infer from our picture whether it is a cat or a dog. Right, so that's pretty much the end of this lesson on how to train your CNN. I provided a few more links there for you to actually get started, or if you want more materials, feel free to refer to those. And if you can see that there's only 9 code of cells, a little bit more in terms of the number of line of codes, but you can see that once you actually play around with this a little bit more, you will get comfortable with it and you'll realize that Keras has made your life very, very easy. With that, I'm going to stop. Thank you once again for watching. Welcome back everyone. Good to see you here again. I mentioned that in the last video you can save your model, and I've shown you how you can save it. In this lesson, I want to cover how do you load your model. Again, Keras have a very simple method to load your model. From keras.models, you import load models, this little simple package, and you just use load models, provide the file name, and basically store it into whatever you want to call your model. In this case, I call it model. You can call it something else if you like. You can call it CNN or anything else. And that's it. And when you print the model summary, you get or receive exactly the same the model that you've trained with the exact weights as well. So you can actually provide it with pictures and obtain inferences or prediction with the image that you provide to it. And that's really how powerful it is. And the file that we use to create in terms of the model is right here, catsanddogs.h5. That's pretty much it. That's how easy it is to load your model. I just want to walk that through with you, and thank you once again for watching. Welcome back, everyone. So let's review a little bit of what we've done so far. We've shown you how to get the data from Kaggle, and I've shown you how to train your own CNN, and the code is provided in this file called cats_and_dogs.ipython notebook, followed by how you actually save it. That's the last few lines of codes in cats and dogs, and also how do you load your model. So let's extend a little bit further. We've built some really fundamental understanding of how to train your CNN, but let's go one step further. The one step further is what happens if I don't have enough images? That's the first question. The second one is, I've got this many images, can I actually make, extract more out of it? The answer is yes, you can indeed. This technique is called data augmentation. Basically, instead of just relying on the only data source that we have, which is what we have just now, which is 2000, you can actually create more data from the existing images that you have. The technique that we're going to talk about is called data augmentation. It's under the image data generator, and I have codes that I'm going to show you in a minute. But essentially, the basic idea here is that you can actually perform all of these so-called transformation with it. So let's just start with the so-called documentation. If you have a look at this, it actually provides a few, or rather a fairly extensive explanation. Basically, you can actually perform from a start, feature-wise underscore center. This is a Boolean. Okay, so 0 means no, 1 means yes. And then you have, what this does is that it set input mean to 0 over the dataset feature-wise. And then on it goes. Some of the specific one that I want to talk about is rotation range. All right, degree range for random rotations. So this rotation basically means that you rotated 10 degrees, 20 degrees, or the other way, -10, -20. You can set the range yourself. The next one is the width shift range. What this is doing is that it shifts the images, right? And the float here, fraction of total width if less than 1, or pixels if it's greater than 1. So it allows you to shift the images left or right. Okay, so that's the width shifting. You can also perform the height shifting up or down. All right, if it's less than 1, then it's a fraction. If it's more than 1, is how many pixels you want to shift. And then you follow by shear range, the shear intensity, so the shear angle in counterclockwise directions in degrees. So let me just show you this. Let me just, in Google. Okay, so image shearing. Okay, this is what image shearing actually means. So let's borrow this. Okay, you can actually, these are the examples of shearing. So you kind of like, instead of a cube, you shear it. This is kind of like, I don't know what you call it actually, trapezoid. And then, and this is a more example of shearing. Okay, so that's really the basic idea of shearing of images. Again, what we're doing here is really simple transformation so that the image is not the same as what you have originally, and it allows the CNN to learn all of these. From the CNN perspective, these are just new data set, and indeed it is, because the angle is a bit different, or it's been sheared, or been zoomed in, or the pixel has been shifted up or down. What you really want to do using this data augmentation technique is to actually forces the CNN to learn the general feature rather than learn pixel by pixel or memorizing the pixel by pixel. There's two more that I want to mention: horizontal flip and also vertical flip, basically flipping the image either horizontally or vertically. Right, so those are the few that I wanted to touch on. So now let's go into our codes within Jupyter Lab. All right, so we start with, this is our original cats and dogs. Okay, and I also want to cover the other part, which is the data augmentation. Now, before we actually go into the data augmentation, I've done a little bit more here in terms of the code itself. Let me just highlight the difference. All of these are the same. Okay, so importing of data, the source data, these are all exactly the same, unchanged there. Okay, so processing is the same in terms of the CNN, architecture is exactly the same. What then is different? Okay, I want to highlight to you this part here. Right, so if you look at this, this is the portion that's different. You will remember when we were looking at the image data generator, previously we don't have this portion. There's no rotation range, there's no width shift range, there's no height shift range, there's no shear range, zoom range, horizontal flipping. Now, this is application of data augmentation in reality now. So everything else is exactly the same, and the only difference are these, you can say, 6 line of codes. Yep, 6 line of codes. By the way, just one word of warning, you don't ever perform data augmentation with your validation data. You don't, okay? Only with the training data, because you want the CNN to learn. So if you look at this, these are all that will change. Nothing else changed. The difference now also is that we're running 100 epochs instead of 30. Okay, I want to run a longer epochs to illustrate to you what actually happened. Okay, so let's go down to the so-called performance. Everything else the same. So this is the 2 key chart that we use to assess the performance of our model. If you look carefully, what do you see? Let me just put side by side the previous one, which is 101 cats and dogs. Okay, let me stack it side by side so that you can actually see. Okay, let's go all the way to the bottom. Notice that previously the training, the validation accuracy plateau and doesn't extend beyond 80%. And if you compare this to the training and validation accuracy, notice that the validation continues to climb. Even at 100 epoch, it continues to climb. And the actual accuracy is actually going up in tandem with our training data. And this is the key important lesson here, is that the data augmentation forces the CNN to learn general features, to actually focus on some of the key characteristics of the image so that it actually can generalize. In fact, you notice that the green is actually, which is the validation, is generally higher than the training data. All right, so the validation data or the performance accuracy is generally better than the training accuracy. And that's really what you want to see, is that this is not an example of overfitting, neither is an example of underfitting. It just shows you that there are more room to grow. Likewise with the loss is exactly the same conclusion. The validation loss continue to drop, and the blue dot, which is the training loss, continue to drop. They are going in tandem. So this is not a sign of overfitting at all. And this is encouraging. Reason for data augmentation is to do precisely that. It's so that our data or our model can continue to learn the general features and perform better out of sample. Okay, so all right, well, I'm gonna stop there. In the next video, I'm gonna show you some examples of images of data or images that have been augmented, meaning we've performed data augmentation, so that you can get a general sense of what it has done. Welcome back, everyone. We're going to look at data augmentation. We talked about this, so I want to show you some randomly generated examples of data augmentation, just so that you can actually get a good idea of how it works. So these are the line of code that we used earlier, And just wanted to highlight that we used this earlier, and we're going to move on now just to see what it looks like. Okay, so from Keras we import image, and we're going to use one specific file called data, and in the folder called src source of visualization, and I'm using .2 JPEG for the purpose of this exercise. We're loading the image, and the target size is 128 by 128. The original picture is not 128 by 128 in terms of size. I just want to, again, this line of codes here, a few lines of code here, is just showing the image is 128 by 128 in terms of the size has been reduced to that size. And the next thing we need to do in order to manipulate this is that we need to convert our image to array and reshape it to 128 by 128. In front is one sample, at the end is 3 channels. Okay, and basically the next thing is we loop through our batch. Okay, loop through our flow. So data gen is what we defined earlier, which is the data gen here is equal to image data generator. And now every time we're drawing batch 1, meaning only one picture being drawn out, and we plot the picture. Okay, so after we've gotten 8 pictures, then take a break, meaning just basically stop the whole thing. So this is, recall that this is our original picture. Notice that it's been flipped, it's been shared, and then, okay, so that's really the data that's been augmented or generated by using this generator. So play around with it. Every time is likely to be a bit different because it is randomly generated, and that's the basic idea of this data gen flow here. So it allows you to create a whole lot of data, or data augmentation is the technique, and allow the CNN to see something different every time to force it to learn the general feature. And that's it. That's really what I wanted to cover, so that you can actually have little codes for you to play with to basically learn what or how the data augmentation is done, and get some intuition out of it. With that, thank you once again for watching. Welcome back, everyone. In this session, we're going to move into transfer learning. Right. One of the things that we've done so far is that we've trained a model, a simple one at that, and we've trained it to identify cats and dogs. That's all very well. Of course, you can start using it to apply to other pictures of dogs and cats. The natural question then is this: if others have run similar training, and if they have done training on massively large image data set and obtain state-of-the-art accuracy, can we use their model for predicting pictures or classifying cats and dogs and all the other animals as well? The answer turns out to be a resounding yes, and that's called transfer learning. That's what we're actually going to go and dig into. This is a really exciting field because now you get the benefit of utilizing trainings that's been done by Google's, Facebook, and utilize the model that they share out in the open or open sourced for you to actually apply to your day-to-day use or your business use. And it turns out to be highly effective. So that's where we're actually going to have a look at it now. So that's the basic ideas of transfer learning, and the file that we're going to look at is called cats and dogs, but underscore transfer underscore learning. So let's dig into that right now. So this is the file. We're still working with cats and dogs, and let me just pull up our previous training so that you can actually have a reference. Recall that we last did the data augmentation. Let's pull this up. Let me pull out the performance so that you can actually have a comparison. After 100 epochs, we reach about 80% in terms of, more like 84% in terms of validation, 83, 82. Okay, just 83 is the highest we were able to observe in terms of validation accuracy. So let's see if we can actually do likewise, if we actually apply this. Now, remember we did talk about VGG 16, And we're going to make use of that. Once again, the usual. Let me just walk through the codes with you. Import NumPy, import pandas. Again, CV2, matplotlib. All these are exactly the same. The rows is 128, and importing OS and SH utility for data copy. So these codes are exactly the same, no change. We're still working with 4,000 data sets, training data sets, 2,000 cats, 2,000 dogs, and 500 validation for both cats and dogs. So that means 1,000 pictures of cats and dogs. Right. From Keras, the good thing about Keras is that there are some built-in models. VGG16 is one of them. And we're going to instantiate a model called using VGG16 that's already available in the Keras. So we're going to call that model is equal to VGG16. And have a look at the so-called VGG's architecture. All right, so this is a summary of the architecture. All right, we have the input layers. The original size is 224. That's okay. And then we have 2 convolution layer and a max pooling layer, another 2 more convolution layer, another max pooling layer, 3 convolution layer, 1 max pool, 3 convolution, 1 max pool, 3 convolution, 1 max pool. Finally, flatten 2 densely connected or fully connected dense layer and prediction. There's 1,000 class here because the VGG was originally trained on 1,000 data sets or classes of pictures. Right. Okay, so we are removing the so-called top. The top are the so-called 2 fully connected layer, including the prediction. So when we actually now look at it, notice that it stops at the block 5 pooling layer, and there's no fully connected layer or flattened fully connected layer at all. Okay, so right. Again, this part is we are importing the from Keras. Actually, this line of code is unnecessary. From Keras, we import the VGG16. We are using from the layers import convolution 2D, max pooling 2D, global average pooling, flatten, dense, and dropout, and also Keras import model. Right, if you look at this, this is the key part here. We are, in a way, you can call it performing a surgery on our models. Looking carefully, what you notice is that we are actually removing a few items. We have removed the flatten, the fully connected layers. Okay, and the question now is that if we have removed those, how does our model actually perform predictions of the cats and dogs? And this is where we actually, I'm going to show you. But the base model is going to be based on the VGG16, and the weights of the neural network is based on what was the originally trained on, which is the ImageNet. Okay, the ImageNet is the massive data that's provided by Stanford to train all the images, and we are removing the top, meaning those 2 connected layer has been removed, and the input shape is designated as 128 by 128. So that's the model, and we store the output to the variable x, and then we're performing what's called global average pooling, and basically after the base model we apply a global average pooling instead of max pooling, and followed by a densely connected layer, and followed by the prediction layer, which is sigmoid in this case rather than softmax, sigmoid being 2 class problems, or the binary one that we've looked at before. And that's it. And we instantiate our model by input being the base model, which is the VGG16, and the output is the prediction that we've defined based on these 4 lines here. All right, so let me just connect this 4 so that you can actually clearly see they are connected this way. And we have to loop through each of those layers that we looked at before, all of these block 1 to 5 here, and set it to no training. Okay, so we're looping through them and have all the weights that's already been pre-trained frozen. Okay, so that's what this layer.train equals to false means. Do not train them, because we want to retain or borrow the learnings that was done from the original ImageNet. Okay, so the next thing is that we do need to compile our model. This is the same as what we have done so far, followed by these. We're not doing any data augmentation here. So everything is just exactly as it was before. And now it's the training. Okay, we're training instead of 30, now 50 epoch, just to compare. And let's have a look at the performance down here. All right. Right, so looking at this, I'll let you take a moment to breathe that in. Look at the validation accuracy. The training accuracy is almost 100%. The validation accuracy is around 95%. Yes, 95%. And that's really why this is so powerful, and it's so crucial to actually take note of the so-called validation accuracy in terms of the predictability or predictive power prediction of this transfer learning. The training loss is around 0.8. It's a little higher than the model, but that's okay because we actually have a very large model with lots of flexibility, so that the so-called loss bound to be a little bit on the higher side. But more importantly is this accuracy score here. Both the training accuracy is really high and the validation accuracy is really high as well. And the conclusion that you can only draw out of this is this. It means that prior training, prior learning that's done by this architecture, which is VGG16 here, 16 stands for 16 layers, is useful in the task that we're trying to solve here, which is trying to separate out cats versus dogs. And therein lies the one key lesson that I want to share with you is this. This is a really powerful technique called transfer learning, and hopefully that impresses upon you to actually use this technique even more. A big part of it is because most of us don't have the computational power or ability like Google, Facebook, and the likes, the tech companies. They've done all this training, they've outsourced it. If you are a small, medium enterprise, you can actually leverage on this and run with it, and it will solve most of the problems that you have. Of course, there are some constraints. If these are all trains of animals, and you try to use it to identify cars or machine parts, it might not perform so well. It ought to be that they are in similar field, and I highly encourage you to look into this a little bit more, just to actually learn how you can potentially use this in your day-to-day problem and some of the business problem that you may face with. With that, I'm going to stop. Thank you once again for watching. Welcome everyone. Last portion we talked about transfer learning. In this segment, we're going to move away from transfer learning, but borrowing the same concept, and moved into feature extraction. What exactly is feature extraction? One of the beauty of deep neural network is that it's able to actually extract or pull out the salient key features of images, as we've learned so far. And the question is that, can you actually use the neural network architecture that we've been using so far to extract features, much like feature engineering that you do in machine learning, classical machine learning, and solve it that way? So use the neural network that you've built, extract the key features, and then apply very simple shallow machine learning to classify the pictures. The answer again turns out to be yes, you can do that. The technique is called feature extraction. So I'm going to show you how to do that right now. We are again working with the cats and dogs datasets since you're comfortable with it. So let's continue to work through with this. and I'm going to show you that as a demo. So the first few blocks of codes are exactly the same. There aren't actually any changes with those. So we're going to skip through them. We're still going to make use of VGG. The difference is there's no major difference. They're still removing the top, meaning we don't have the flattened layer nor the fully connected layer. Right, the variation comes in here. Notice the data augmentation that we are doing. All right, so that's the first part, and we are actually providing in terms of the binary request that we are doing. All right, so other things that we are doing here is this. We are actually setting the sample size, providing the features, and basically loop through them all one by one. So let me walk through these in terms of what we're looking to do. From the train data gen that we did earlier, this which is this one here, and the train data gen, we save it as a training sample size, which is 4,000. Second thing is the feature. We store a whole bunch of zero. Okay, so we have train sample size. So essentially, we're creating a tensor here. So 4,000 is the first number, comma 4 by 4. All right, and then followed by 512. We're creating a shape that has that shape. All right, so followed by the training labels, which we will save. So these are all creating a whole bunch of zeros. Okay, so these are using NumPy to create zeros for both the feature that we're going to feed as well as the label. The next thing is that we loop through the data, which are the images, and extract both the features as well as the labels. And we run them one by one. Okay, so we extract the features and store it into the features. The extracted features here is based on, let me find that. Extracted features is this one here, sorry. Okay, this extracted features is based on the so-called images that we have, the data that's generated, and we feed it through our neural network, which is the VGG without the head, removing the flattened layer as well as the fully connected layer, and just basically taking the output of the model, which is called, and we save it in extracted features, and then we run it through and save it into our trained features, and the labels of these features are stored in trained labels. So the basic idea is that we are looping through all of the data, all of the images. In other words, the images are being fed in. We perform data augmentation, but we already know the label of these, so we stored it in the variable called train labels. And the features, which are the images, we feed it through the neural network, the CNN that was done before, which is the VGG. And then the output of the image plus the CNN is stored in trained features. And then we increase I by 1, and basically once we reach the data size or batch size and the total size is greater than the training sample size, we stopped. Okay, that's what this break is for. Right, the next thing is that we need to scale our data into divided by 255, and then again we need to have the data flow from the directory as well for our validation data. Okay, so this is the part whereby again we need to do the same with our validation data set. So with the validation, again, we need to know how many samples do we have. Again, we create the features. The shape is the number of samples that we have, and then 4 by 4, and then 512. And we create the number of zeros based on the label, how many sample size that we have. Again, we perform the extracting features, store the features, store the labels, and continue until we finished all of our samples. All right, so the next part here is training our features. We'll need to reshape it. Instead of 4, 4, 512, we are reshaping it to become 4 training sample size, which is 4,000. 4 times 4 times 512. Essentially, what are we doing here? We're actually flattening it. Okay, we're reshaping it to become a 2D, except that it is 2D, but the first so-called value is actually the sample, each sample itself. Okay, so we do that for the training, we do that for the validation as well. All right, come next is to define the so-called classification part now. So we import the models, optimizers, the dense, and the dropout, and we create our sequential model. We first of all add a layer called dense 512, which is the input dimension, and then we actually apply a densely connected layer. The input layer is basically, you notice that it's 4 by 4 by 512. It's basically is actually a flattened layer. And we applying a densely connected layer, but with dropout 50%, and finally apply a sigmoid for classification, which is a cats and dogs that we're looking at. And the next one is the familiar compiling our data, followed by training our data for 50 epochs, and this is the outcome that we get. Right, so if you look at it, the model in terms of the validation accuracy hover around 87%. So it's range bound from 85 to 90, and the so-called loss actually start to pick up from 20 onwards, and in fact it didn't improve from after 10 epochs. So if you look at this carefully, around 10 epochs we're already overfitting our data, and we should have probably stopped training our model at that point. There's no need to continue on for another epochs. But again, you can see that this is a really attractive way of using neural network. It's an ingenious way of using a neural network. Basically what you've done is actually you have used the CNN to extract the key features, and then apply a slightly different layout, dense layout with a dropout with a dense layout for the problem that you are trying to actually solve here. Okay, so I guess the one question that you might have when you look through this VGG network, and then later on you see that I have provided certain shapes, such as this one here, 4, 4, 512, I have a sneaking suspicion that you probably don't know what this is, or you'll be asking that question right throughout. So let me put you out of your misery and come back to this model. This is the output of the base model of the VGG. Our input, remember our image size, we reshaped to 128 by 128. Take a look at the output. The output through this VGG16 is a height of 4, width of 4, and depth of 512. And therein lies where the 4 by 4 by 512 comes from. So in this situation, at the max pooling, the block 5 pool, max pooling 2D, you have a height of 4, a width of 4, and depth of 512. Basically, it's kind of like a cube, but not quite, because it's 512. It's not exactly a cube. And what we usually have is that we reshape it and flatten it. And essentially flatten it is basically 4 times 4 times 512. And that's technically what we did here when we actually reshape it here to 4 times 4 times 512. Of course, you don't have to apply these sequential models, which is plugging the neural network at the end of it. It is quite common and quite normal for people to actually apply logistic regression, which is of course a sigmoid function, rather than applying the all of these other techniques that we discussed here. That's one way to do it. You can, of course, logistic regression is one way. There's a few others that you can actually apply to it. But I'll leave that to you as an exercise for you to experiment with. I hope you found this useful, and thank you once again for watching. Welcome back, everyone. It's good to see you here. In this session, I'm going to talk about where to from here. It's been a really exciting journey so far. And what we've done so far is that we've covered some of the state-of-the-art models all the way including VGG, which is very deep convolutional networks for large-scale image recognition. In fact, I do have a notebook in there called ResNet 2016. Now, the question that you're naturally going to ask is that what happened between 2016 until now? There's quite a lot of development, and there are quite a lot of state-of-the-art design and the CNN that's been created. I just want to give you a brief overview of it. Right, so if you look at this, what you can see here is that you have top one accuracy, so meaning the higher these are, the better it is. Inception is the highest, followed by Inception v3, ResNet 152, ResNet 101, and ResNet 34. I encourage you to go and have a look at the ResNet. I won't be walking through that. That was under the feature extraction. The notebook is there. It's just that I haven't actually walked through it with you, mainly because it's actually very similar to VGG 16. And then you have the ResNet 16, GoogleNet, eNet, and then you have some of the LXNet over here. The VGG 16 is the one that we spend a fair bit of time on. And one thing that this picture doesn't show is that as you move towards the right, the length of time it takes to train the model goes up substantially. Okay, so there are a couple of things that's been it's a massive advancements. There's the fine-tuning networks. There is also the adaptive learning rate. Now, what exactly is fine-tuning networks? What we've done so far is actually feature extraction. We've left all the weights that's in the model untouched, meaning we didn't actually touch it at all. But what you can do is actually start opening up the layers one by one for fine-tuning. That's the basic idea there. What about adaptive learning rate? So far, Keras does allow you to change your learning rate. What we've done so far is that we just use a pretty standard learning rate, and we didn't actually alter it. And one of the ways that you can actually do this, it's a more advanced technique, which require a lot more babysitting of your model, is to change your learning rate as your accuracy start to get better and better. And you ought to and should slow down your learning rate so that it doesn't overshoot the so-called ideal or the lowest loss. Okay, because ultimately all the models are looking at the lowest loss or minimize the error. There are a lot of advancement that's been made on the optimization model. The one that we talked about a little bit is SGD, or stochastic gradient descent. We use RMS prop quite a fair bit, although I didn't actually dig into it and explaining what they are. For now, it's sufficient for you to actually just use the model to actually train your neural network. There are some more advanced or state-of-the-art architecture. We talked about VGGNet rather than just using build it up from ground up. You have the LXNet, you have the GoogleNet, which is also called Inception, and ResNet. So the picture source here is an analysis of deep neural network models for practical application. So please do look up that if you want to actually find out a little bit more. There are some of the state-of-the-art tools that I just want to highlight so that you can actually look them up. H2O, these aren't endorsement, it's just really to highlight to you that they do exist, and do have a look at them. Some of them does make your life a lot easier, and so it will help immensely. So H2O, deep cognition, meaning you don't actually have to code at all. You can actually start building a neural network without writing code as we did so far. RapidMiner is another one where it's completely GUI based. You have KNIME, Alteryx, and DataRobot. There are some free compute that is provided that you can actually make use of. If you don't have GPU and you want to actually expedite your training process, you can use Google Colab, Colab Research, Kaggle, as well as notebooks.azure. With that, I'm going to stop this video. Thank you once again for watching, and I look forward to seeing you in future lessons.